Hi everyone, welcome to PrepFusion. So first in this video we are going to study about LTI system, then we will study about filters. After that we will see some miscellaneous points. Okay, those will be helpful for sampling. So those miscellaneous points we are going to see. After that in the next lecture we are going to study about sampling. So this will be the flow of the lecture. So first let's study about LTI system in frequency domain. So we have done that time domain analysis of LTI system, right? Let's just say I call this as LTI system. This is my LTI system. So what it is known as? HT is known as impulse response of LTI system. I hope you remember it. So HT is known as impulse response of LTI system. XT is the input, YT is the output. So output YT is given as XT convolution HT. So what will be your Y of omega? If I want to write down Y of omega, what that would be? Convolution in time domain will result in multiplication in frequency domain, and there will be no factor of 1 by 2 pi. There you go, that's it. So if you are having the Fourier transform of xt and you are having the Fourier transform of ht, that means if you know the frequency spectrum of xt, if you know the frequency spectrum of ht, if you multiply both of the frequency spectrum, then you will get the frequency spectrum of output. So frequency spectrum of input, frequency spectrum of the impulse response, multiply both of them, you will get the frequency spectrum of output. That's it. This is the only concept. So let's see the question. So there is an LTI system whose impulse response is given by ht and the frequency spectrum of ht is given by h of omega, which is something like this. And then there is the input. Input is given as xt. The frequency spectrum of xt is given as x of omega, which is something like this. You need to draw the frequency spectrum of yt, which is given by y of omega. So how will the output spectrum look like? So you know that y of omega will be equals to h of omega into x of omega. So simply you need to do the multiplication, that's it. What you will do, you will just do the multiplication. So can you draw y of omega? Yes, surely I can draw y of omega. Simply I need to do the multiplication, nothing else. So this is 0 between -1 to 2. Everywhere it is 0 when it is non-zero. Between 2 to 4. So between 2 to 4 it is providing a gain of 1. So between 2 to 4, this is 2, this is 4. Rest all the places it is 0, only x of omega is having an impulse of 2. So 2 will be multiplied with 1. Simply I am doing the multiplication, nothing else. So at the frequency 3 radian, per second, there is an impulse of 2 which will be multiplied with 1. Rest at all the frequencies between 2 to 4. At 2 it is providing 0, this is providing something. 0 into something will be 0 only. At 2.5 this is providing 0, this is providing 1. 0 into and 1 will be 0 only. At 3.5 this is providing 0, this is providing 1. 0 into 1 will be again 0. So between 2 to 4 it is providing a gain of 1. Between 2 to 4 it is providing a gain of 1. So only 1 is multiplied with 3, that's it. So only one common frequency is there, which is 3. Now this 1 at omega equals to 1, you are having an impulse of -1 area. But here what is the amplitude? 0. So anything multiplied with 0 will be 0 only. Anything multiplied with 0 will be 0 only. Now between -1 to -3, this is also non-zero and this is also non-zero. So result will be non-zero. Now between -1 to -3, this is a line, straight line. This is a straight line. Okay, which is having a peak amplitude of 1.5, and 1.5 will be multiplied with -2. So the amplitude will become 1.5 minus 2, the amplitude will become -3. So basically what is happening, till -1 everything is 0, till -1 everything is 0. Here also everything is 0 only then there is an impulse. After that also everything is 0. From -1 to -3, 1.5 will be multiplied with -2. That means you will get -3. This is how you will get. Basically here what is the slope? Here the slope is, negative slope is there. Minus 1.5 divided by 2. This is the slope here. Basically this slope is being multiplied with -2. So slope will become +3. So this is the +3 slope at -1, -3. What is the amplitude here? 1.5 minus 3. So this amplitude will become, at -3 the amplitude was 1.5, right? So Here the amplitude will be 1.5 minus 1.5 into 1.5 into 2. Forget about this, forget about the slope. Just see the amplitude, 1.5 into minus 2. So this point will be minus 3. Right? After that, what is happening? Between minus 3 to minus 4, this is non-zero, but this is 0. So non-zero into 0 will be 0 only. Non-zero into 0 will be 0 only. And after that, everything is 0. This point will be minus 3. Right? Here, what was the slope? Here the slope was minus 1.5 by 2, which is being multiplied with minus 2. So this was multiplied with minus 2. So slope became 1.5. So here the slope is 1.5. You can check here, the slope is 1.5 only. But slope and all you don't need to care. Basically the thing is we are just multiplying two graphs, and you know how to multiply two graphs. So this will be the frequency spectrum of y of omega. So what do you understand by this question? That this is acting as a filter. H of omega is acting as a filter. What is the meaning of filter? Filter means it will pass a certain range of frequencies and it will not pass a certain range of frequency. Basically, this H of omega, what it will do, whatever that you apply at input, I don't care whatever that you apply at input, I will only pass the frequency range from 2 to 4 and from minus 1 to minus 3, or you can say minus 3 to minus 1. What it will do, H of omega, no matter whatever the input you apply, what I will do is that I will only pass the frequencies from 2 to 4 and minus 1 to minus 3. Now at the input that you applied, there you are saying that I am only having the component at omega equals to 3. I am not having any component from 2 to 3, I am not having any component from 3 to 4. Only I am having a component at 3 only. So only this 3 component will be passed. This one component will not be passed because this is saying that I do not pass component of omega equals to 1. I only pass the component from minus 1 to minus 3. So from minus 1 to minus 3 it will be passed, but from minus 3 to minus 4 I do not pass. So this will not be passed. Are you able to understand this point? So this is known as filter. So every LTI system is a filter. Why is that so? Because the impulse response, the frequency spectrum of impulse response will be multiplied with the frequency spectrum of the input. So, and what does frequency spectrum shows? Frequency spectrum shows that this much frequencies are present. So let's just say in the input, I say that 3 radian per second was present, 3 radian per second was present, 3.5 radian per second was present. This is some different input, okay? And 3.8 radian per second was present, and 4.5 radian per second was present, and 1.3 radian per second was present. So how much frequency component would pass? This would pass? Yes, because between 2 to 4 it will pass it. 3.5 would pass? Yes. 3.8 would pass? Yes. But 4.5 would not pass, 1.3 would not pass. So it is acting like a filter. The user is saying that at the output I only need this much frequency range. I only need 3, 3.5, 3.8. What user will say, that user will come up with the particular signal. In this signal I am having 3 radian, 3.5, 3.8, 4.5, 1.3. But actually for my requirement I only need 3, 3.5, 3.8. So you will design a filter like this, which is only passing these frequency range only, 3, 3.5, 3.3, 3.5 and 3.8. It is not passing 4.5, it is not passing 1.3. So every LTI system can be termed as a filter, okay? And what is the definition of the filter? Filter means it will pass a certain frequency range and it will attenuate the other frequency ranges, okay? So this is what I have written. What is a filter? An electronic circuit designed to selectively allow or block specific frequencies with an electrical signal. Specific frequencies within an electrical signal. Specific frequencies within an electrical signal. Okay. So it is like an electronic circuit which is designed that will pass or reject a particular frequency. So we will understand it one by one, so you will understand it more. So and then there is a note that every LTI system can be considered as a filter. Okay. Now there are 5 kind of filter, mainly 5 kind of analog filters are there: low pass filter, high pass filter, all pass filter, band pass filter and band reject filter. So we will study one by one. Although in analog electronics we have already studied it, but let's study it again. What is the meaning of low pass filter? Low pass filter, by the name only it is clear that it will pass only lower frequencies. That means it will pass the frequencies which are below than a particular frequency, and that particular frequency is known as cutoff frequency. So if I am saying that my cutoff frequency is 10 radian per second, that means it will pass, I am saying that my cutoff frequency is 10 radian per second. That means it will pass all the frequencies which are lesser than 10 radian per second. All the frequencies which are lesser than 10 radian per second. Okay. So what it will do? It will pass all the frequencies which is lesser than the cutoff frequencies, which is lesser than omega c. So it will provide gain 1. Ideally it should provide gain 1, but it can provide any gain 0.5, 2, 3.5, 4, but ideally it should provide gain 1. But one thing I told you, always our frequency spectrum will be having negative frequencies as well, because a real world signal will have the even frequency spectrum, and to make the frequency spectrum even you need to show the negative frequency as well. So basically what does it mean? That it will pass all the frequencies lesser than omega c, but h of omega should be even. H of omega, mode of h of omega should be even. That's why I need to show the negative frequency as well. So this is the frequency spectrum of the impulse response of an LTI system which is working as a low pass filter. Again, let me repeat the statement. This is the frequency spectrum of the impulse response of LTI system. Frequency spectrum of the impulse response of an LTI system which is working as a low pass filter. Is that okay for you? So if someone asks you draw the frequency spectra or frequency spectrum of a low pass filter, then will you be able to make it? Yeah, surely you will be able to make it. Now there are some terms defined which is known as cutoff frequency. So cutoff frequency I told you, this is our omega c, which is the cutoff frequency. Now there is something called bandwidth. Bandwidth, that means how much frequency range it will pass. So it will pass the frequency range from 0 to omega c, right? It will pass the frequency ranges from 0 to omega c. So how much frequency range it will pass? Omega c minus 0. So what will be its bandwidth? Omega c. Basically how much frequencies it will pass. So from 0 to omega c, everything it will pass. So lower will be 0, highest will be omega c. So omega c minus 0. So this is known as bandwidth. So this is the bandwidth. And whenever we talk about bandwidth, we do not see at the negative frequency, because negative frequency is just there to make the signal even, nothing else. So only I will look at positive frequency. So this is the bandwidth, omega c. Well and good. Yeah, so this was about low pass filter. What about high pass filter? What do you think? It will pass the frequencies higher than the cutoff frequency, higher than a particular frequency, and that particular frequency is known as cutoff frequency. Okay, so what it will do? It will pass all the frequencies which is higher than the particular cutoff frequency. Let's just say my cutoff frequency is 10 radian per second. Now at the input, 3 radian per second is there, 7 radian per second is there, 11 radian per second is there, 15 radian per second is there. And now this input is exposed to a high pass filter, or you can say this input is exposed to a LTI system which is having a impulse response in this manner, which is having a frequency spectrum of the impulse response in this manner. So frequency spectrum of the impulse response is a high pass filter. That means it is having a cutoff frequency of 10 radian per second. So it will pass all the frequencies which are greater than 10 radian per second. That means it will pass 11 radian per second and 15 radian per second. So it will not pass 3, it will not pass 7. Are you able to understand this point? Okay. So 11 and 15 radian per second will be passed. What do you think? What is the bandwidth? Yeah, one more thing. We have to make it even. So similar thing will be repeated here as well. What do you think? What is the bandwidth? How much frequency range it is passing? From omega c to infinity, right? So bandwidth is infinity minus omega c. That is infinity only. Here cutoff frequency and bandwidth was same. But for high pass filter, the cutoff frequency is omega c, but the bandwidth is infinity. So this is known as high pass filter. What do you understand by all pass filter? It will pass everything. So it will pass all the frequencies. So everything it will pass. It will pass everything. So whatever that is there in the positive side, the same will be there in the negative side as well. So it will pass everything. So is there any concept of cutoff frequency? No, there is no cutoff frequency. Basically, whatever the input was applied, the same will be the output. Now it might happen that it can give you a gain of A. So your output will be A into xt. Whatever the input was applied, same would be the output, just with the gain of A. So it might happen that it can give you a gain of A. Nothing else it will do. It will not kill any frequency, or it will not kill any frequency. It will allow all the frequencies. So this is known as all pass filter. What do you think? What is the bandwidth? Again, from 0 to infinity, it allows everything. So bandwidth is infinity only. Okay, all pass filter. The name is all pass filter. Band pass filter. Band pass filter. So it will pass only a specific frequency range. What your low pass filter was doing? It was passing lower frequencies. High pass passing higher frequency. Now band pass will, what it will do? It will pass only a specific band of frequencies, or you can say it will pass a specific range of frequency. So this is known as lower cutoff frequency, and this is known as higher cutoff frequency. So it will pass only this much range. So what it is written? The LTI system which passes only those frequencies which lies in a specific frequency range. So what will be given? This is known as lower cutoff frequency. This is known as higher cutoff frequency. Okay, so what will be given? That there is a band pass filter. There is a band pass filter having lower cutoff frequency of 5 kilohertz and higher cutoff frequency of, you can term it in the radian as well. I am writing it down in terms of kilohertz. Okay, and higher cutoff frequency is 7 kilohertz, or you say 8 kilohertz. Now at the input you are applying 2 kilohertz, 5.5 kilohertz, 6.5 kilohertz and 8 kilohertz and 8.5 kilohertz. So at the output what you will have? This was the input, this was your impulse response. So at the output what you will have? 2 kilohertz will be passed? No, only between 5 to 8 it will be passed. So whatever that is there between 5 to 8, only those will be passed. This will be passed, this will be passed, this will be rejected. So at the output you will have only 5.5k and 6.5k. Okay. So this is the meaning of your band pass filter. So this is known as lower cutoff frequency, this is known as higher cutoff frequency. The thing is, the same should be reflected to the negative side as well. Okay, what is the bandwidth? What do you think? What is the bandwidth? It is passing this much range, you know. So what is the bandwidth? FH minus FL. So this is known as band pass filter. What do you think? What is band stop filter? Band stop filter means it will not allow only a specific range. It will allow everything. It will allow everything, but it will not allow a specific range. This is known as band stop filter. So I am allowing everything, but not this range. Which range? This range. FL to FH. So there is a band stop filter. There is a band stop filter. Band stop filter, or it is known as band reject filter as well. Okay, band reject filter as well, or it is known as notch filter as well. Notch filter, different names are there. Okay, band reject filter, notch filter, anything could be there. So band stop filter, band stop filter. So what it does? Band stop filter, it doesn't allow a specific range of frequency. I am saying that my FL is 3 kilohertz and my FH is 6 kilohertz. Now at the input what I am having? 2.5k, 3.2k, 3.7k, 5k, 9k and 10k. So at the output what you will have? Between 3 to 6 nothing will be allowed. This will not be allowed, this will not be allowed, this will not be allowed. So 2.5k will be allowed, 9k will be allowed and 10k will be allowed. So at the output you will be having 2.5k, 9k and 10k. Okay. So lower cutoff frequency is FL, higher cutoff frequency is FH. The similar should be reflected to negative side as well. Let me know the bandwidth. It is allowing this much frequency, FL, 0 to FL means FL. Basically FL minus 0 plus it is allowing this much frequency, infinity minus FH. So infinity minus FH will be infinity, infinity plus anything will be infinity only. So what is the bandwidth? That is infinity. So these are some standard type of filter. Low pass filter, lower allowed. High pass filter, higher allowed. All pass filter, everything is allowed. Band pass filter, only a specific range is allowed. And band stop filter, only a specific range is not allowed. So these are the filters. Okay. And what do you understand by filter? Any LTI system is a filter only, because I know that in case of LTI system, my frequency spectrum of the output will be the multiplication of the frequency spectrum of the impulse response to the multiplication of a frequency spectrum of the impulse response and frequency spectrum of the input. If both are being multiplied, then you get the frequency spectrum of the output. Here we have seen it, right? Now see this question. Find the type of filter and comment on the cutoff frequency and bandwidth. So whenever you think about filter, your mind should go to frequency spectrum. That means your mind should go to Fourier transform. Fourier transform means frequency spectrum only. So by looking at the time domain, ht is equals to delta t, can you comment anything? Ht equals to delta t. What you can comment? That what kind of filter it is? For finding the filter, you need to see the frequency spectrum. This is your impulse response, right? H of t, here in the question it should be given that h of t is impulse response of LTI system. So what this impulse response will allow? Let's see that. So we have to make the graph of h of omega. So if h of t is delta t, then what will be h of omega? What is the Fourier transform of h of what is the Fourier transform of delta t? That is 1. Fourier transform of delta t is 1. So this will be your h of omega. So what do you think what it is? All pass filter, right? All pass filter. So first one is all pass filter. There is no cutoff frequency. What is the bandwidth? Bandwidth is infinity. So option A is done. What about option B? H of t is sinc t. Sinc t. Can I write it down in this manner? Sin pi t upon pi t. What will be your h of omega? Because I need to see h of omega only. So what will be your h of omega? Sin 80 by pi t. Sin 80 by pi t. So that means between minus pi to pi it will be rect, otherwise it will be 0. So what do you think? What it is? It is passing only this much frequency range, right? Forget about the negative part. It is passing only this much frequency range, right? Lesser than pi. So what is the cutoff frequency here? What is the cutoff frequency? Cutoff frequency is pi radian per second. And what kind of filter it is? Low pass filter. And what is the bandwidth? Bandwidth is also pi radian per second. So this is about your sinc t. What is the third one? H of t is delta t minus sinc t. Basically, from if you find out the Fourier transform, so delta t will have a Fourier transform of 1, and this will have a Fourier transform of rect omega minus center upon complete width. Basically, what will be the Fourier transform of this thing? We don't remember the final answer, but we remember this diagram. So from this diagram, can I write it down? My Fourier transform, yes. So 1 minus rect omega minus center upon complete width. So basically from 1, this will be subtracted. What will happen is that from 1, this rectangular pulse will be subtracted. So what will be the answer you will be getting? One minus rectangular pulse. Right? So 1 minus rectangular pulse if you do, then what you will be getting? So between minus pi to pi, this is providing a gain of 1 and this is also providing a gain of 1. Here what was the gain? Gain of 1. So 1 minus 1 will be 0. So what you will be getting? And 1 minus 0 will be 1. Basically 1 minus 0 will be 1. So till pi you will get 1 minus 0, that would be 1. Then 1 minus 1 will be 0. And after that 1 minus 0 will again be 1. So this is the impulse response you are having. So what do you think? What kind of filter is that? This is your high pass filter, right? So if you subtract all pass filter, from all pass filter, if you subtract low pass filter, then what you will get? High pass filter. So it is a high pass filter. What is the cutoff frequency? Cutoff frequency is pi radian per second. And what is your bandwidth? Bandwidth is infinity. All good? All fine? Okay. Let's see this one. Sinc t dot cos 2 pi t. Sinc t dot cos 2 pi t. So multiplication in time domain, or what we can do? Okay, let's see d ht sinc t dot cos 2 pi t. So it can be written as, let's just say I call this as pt. Okay, so it can be written as pt e to the power j 2 pi t plus e to the power minus j 2 pi t divided by 2, right? What I will be getting? pt into e to the power j 2 pi t plus pt into e to the power minus j 2 pi t divided by 2 here, divided by 2 here. So what I can write down? P omega minus 2 pi, right? Because pt is having a Fourier transform of p of omega. So pt into e to the power j 2 pi t will have a Fourier transform of p omega minus 2 pi divided by 2 plus p omega plus 2 pi divided by 2. So you clearly know what will be your p of omega. You clearly know what is your p of omega, right? P of omega will be this only. Now what will happen? The center will be shifted to 2 pi and center will be shifted to minus 2 pi, and then amplitude will be divided by 2. So what kind of response you will be getting? This center which was at 0, it will be shifted to 2 pi. Here also the center which was at 0, this will be shifted to minus 2 pi. The width was here, the complete width was 2 pi only. Basically you just need to shift this waveform. So this minus pi will be reaching to pi plus pi, and this plus pi will be reaching to 3 pi. Plus pi and 3 pi. And here it will be shifted towards this side. So this minus pi minus 2 pi will be reaching to minus 3 pi. And this plus pi minus 2 pi will be reaching to minus pi. And the amplitude will be half. So what do you think, which kind of filter is that? This is only passing this much range. So what kind of filter is that? Band pass filter. What is the cutoff frequency? Cutoff frequency, there is no concept. There is a concept of lower cutoff frequency, pi radian per second. Okay, am I writing f? No. Okay, good. So this will be omega L, no? You can write down in terms of f as well. Basically omega L is pi radian per second. So what will be your FL? That would be 1 by 2 hertz. Because just divide by 2 pi, just divide by 2 pi, what you will get? 1 by 2 hertz. What will be your omega H? 3 pi radian per second. What will be your FH? That would be 3 by 2 hertz. And what will be your bandwidth? What is the bandwidth? 2 pi radian per second. And here what will be the bandwidth? 3 by 2 minus 1 by 2, 1 hertz. There you go. Okay. What about E option? E option. Delta t minus sinc t cos 2 pi t. What is your E option? Delta t minus sinc t into cos 2 pi t. So from 1, this all will be subtracted. Okay, this is actually wrong. If it is being subtracted from 1, then there is an issue, no? So because 1 minus 1 by 2 will throw 1 by 2. 1 minus 0 will throw. So here there should be a change. There should be a change. Here it should be 1 by 2. Here it should be delta t by 2. Okay. So there is a change. Here it should be delta t by 2. Right? Why I am doing so? Because if I directly write down delta t, that means delta t will have a Fourier transform of 1. So from 1, this will be subtracted. So 1 minus 1 by 2 will throw 1 by 2. 1 minus 0 will throw 1. So what kind of response you would get? 1 minus 0 will be 1. Then 1 minus 1 by 2 will be 1 by 2. And then 1. Then again 1 by 2. So it is passing all the frequency range, you know. Although here you are getting a gain of 1, here you are getting a gain of 1 by 2. But you cannot say that at the output these frequencies will not be present. Yes, these frequencies will also be present at the output. But if I want these frequencies should not be present at the output, that means I want the gain to be 0. So what I need to do? I need to put delta t by 2. Now what will happen? From 1 by 2, these will be subtracted. So 1 by 2 minus 1 by 2, it will be 0. 1 by 2 minus 0 will be, so basically what will be the output? 1 by 2 minus 0 will be 1 by 2. Then 1 by 2 minus 1 by 2 will be 0. Then 1 by 2 minus 0 will be 1 by 2. Then 1 by 2 minus 1 by 2 will be 0. And then 1 by 2 minus 0 will be 1 by 2. So this kind of response you will be getting. These will be your cutoff frequencies. Sorry, these will be your lower cutoff frequency and higher cutoff frequency. What will be your complete bandwidth? Bandwidth will be infinity, and this will be a band stop filter. So this you can do on your own. Very easy it is. So this will be your band stop filter. Band stop filter. Lower cutoff frequency will be pi only, and higher cutoff frequency will be 3 pi only. But what will be the bandwidth? Bandwidth will be infinity. Okay, so this was about the filter. These are the basics of filter. Important part is the questions. We need to solve the questions. So previous one was also a question only. This is also a question only. So try doing it on your own. X of t is a square wave that is given. You need to comment on the nature of yt. So you don't need to find out yt. You just need to tell whether yt will be a DC or it will be sinusoid, or whatever it would be. Sinusoid of what frequency, cosinusoid of what frequency. So whatever it would be, that you need to tell. Are you able to understand this point? Right? And these kind of filters are there. So first you need to pass your xt with this impulse response having this filter. Okay, the impulse response of LTI system. This is your LTI system. The impulse response of LTI system is delta t. This is equation 1. This is equation 2. This is equation 3. This is equation 4. This is equation 5. Okay, only on the nature you need to comment. We are not talking about amplitude or anything. We just need to comment on the nature. That's it. What can you comment about xt? What can I comment about xt? Is it having 0 DC value? Absolutely not. It is not having 0 DC value. So it is having a DC value non-zero. So what is the DC value here? DC value is, this point will be 3 by 2. What is the time period here? Time period is 3. So a into 3 by 2 minus 2a by 3 into 3 by 2 divided by 3. So a by 2 minus a by 3. A by 3 into 3 by 2. So a by 6, this is what we are getting. So a by 6 we are getting. So the DC value is a by 6. This is the C naught value. All good. Let me check back again. DC value a into 3 by 2 minus 2a by 3 into 3 by 2. So 3 by 2 is coming common. 1 by 2 it would be, by cancelling out, then a by 3, a by 6. This is the DC value. So let's see the first question. I just calculated the DC value, just like it will not be of any use, I guess, but let's see the first question. HT is equals to delta T. What does that mean? It is all pass filter, because H of omega is equals to 1. So this is your all pass filter. So what will be your output? YT, same square wave, because it will pass everything, no? It will pass everything. It will pass the complete whatever the frequency component this is having. This is made from some frequencies component, no? Right? How this is made? How XT is made? In XT, what all frequency components are present? Just let me know this thing. First, you let me know whether it will be made from sinusoids or cosinusoids. It is a odd function or even function. XT is a odd function, right? It is a odd function. That means it will be made from sinusoids, right? Is there any half wave symmetry? Apparently you feel like that if I shift by t by 2 and then I take the mirror image, I will get the amplitude to be minus a, but here the amplitude is minus 2a by 3. But I told you, whenever you check half wave symmetry, you need to subtract the DC value. So if you subtract the DC value from a, what you will get? 5a by 6. Then you subtract the value from here as well. What you will get? Minus 5a by 6. So after subtracting the DC value, what you are getting to know is that yes, it is having the half wave symmetry. So yes, your XT is having a half wave symmetry. And if there is half wave symmetry, this is known as hidden half wave symmetry, because after subtracting the DC value, you are getting to know that yes, there is a half wave symmetry. So there is hidden half wave symmetry present. Hidden half wave symmetry, what does that mean? That it will only have the frequency component of omega naught, 3 omega naught, 5 omega naught, 7 omega naught, and so on. What is the value of T naught here? 3. What is the value of omega naught? 2 pi by 3. So what all frequency components are present here? So XT is actually having a DC, that means 0 frequency component, then omega naught frequency component, 3 omega naught frequency component, 5 omega naught frequency component, and so on. So DC value, 0 frequency component. What is the DC value? A by 6. What is the DC value? That is A by 6. And what is the meaning of omega naught frequency component? The meaning of omega naught frequency component is it is having 2 pi by 3 frequency. It is having 2 pi frequency. It is having 10 pi by 3 frequency. That means 2 pi by 3 multiply with 3, 2 pi. 2 pi by 3 multiply with 5. That will be 10 pi by 3 and so on. Next would be 7 omega naught. Then 9 omega naught and so on. So 7 into 2 pi by 3, that would be 14 pi by 3. Next would be 6 pi, right? So these frequency components it is having. XT is having these frequency component. Also it is having a DC value. But first one is all pass filter, that means it will pass everything. So same kind of square wave you will be getting at the output. What about the second one? Second one is HT sync T. So this we have already seen, sin 80 by pi t. Sin 80 by pi t. So what it is? It is a low pass filter with the cutoff frequency of pi radian per second, right? It is a low pass filter with the cutoff frequency of pi radian per second. This we have already seen. That means what it will pass? It will pass 0 frequency and 2 pi by 3 frequency. After that nothing will pass. What is the scenario here is that at the input side, you are having 0 frequency. You are having 0 frequency. You are having 2 pi by 3 radian per second. You are having 2 pi radian per second. You are having 10 pi by 3 radian per second. And after that it keeps on increasing. Now then there is a low pass filter with cutoff frequency of pi radian per second. That means it will pass all the frequencies which are lesser than pi. That means this will not be passed, this will not be passed, only this will be passed and this will be passed. So at the output what you will have? DC and 2 pi by 3 radian per second sinusoid, right? It will be sinusoid because components are sinusoid only. So you are having at the output what you are having at 2 pi by 3 radian fundamental frequency sinusoid with the DC value of a by 6. What is the DC value? DC value is completely passed, that is a by 6. So at the output what you are having? What is your YT? Your YT is sinusoid of fundamental frequency of 2 pi by 3 radian per second and DC value of a by 6. So basically your YT is some DC value a by 6 plus a sinusoid of fundamental frequency 2 pi by 3. And then there is some amplitude A1 which I don't know. I don't know the amplitude A1. I don't need to comment on this amplitude A1. I just know that there is a sinusoid of fundamental frequency 2 pi by 3 with the DC value of a by 6. What is the DC value of this sinusoid? That would be 0 only. Any sinusoid with any amplitude will give you 0 DC value. But plus you are adding up a by 6. So this is your output. What kind of nature you will see at the output? That sinusoid but shifted upward. Sinusoid but shifted upward. So this kind of nature you will see. Sinusoid shifted by a by 6. So this point will be a by 6. Because at t equals to 0 you are having a by 6 value. So this point will be a by 6. So sinusoid shifted upward. Say yes or no. Are you able to understand the point? So if someone was coming with a square wave, someone was having a square wave, but sir, for the analysis purpose I need sinusoid with the particular DC value. So what I can do, sir? So you were intelligent, you were smart enough, you said that you design a filter which is having a lower cutoff frequency, which is having a cutoff frequency of pi radian per second. And at the input side you are having 2 pi by 3, 4 pi by 3, 2 pi by 3, 6 pi by 3, all these frequency ranges you are having. So you designed a low pass filter with the cutoff frequency of pi radian per second, then only sinusoid of one component was passed. So these kind of questions are very, very important, and surely in the upcoming future these questions will be introduced in your examination. Let's see the option C. Okay, here again there is an issue that this should be delta t by 2. Yeah. So third one, delta t minus sync t. Delta t minus sync t. Then they are asking what is the fundamental frequency of this particular output in the case of C. So delta t minus sync t. Delta t minus sync t. What it is? It is a high pass filter with cutoff frequency of pi. This we have already seen, right? Delta t sin pi t by pi t. So high pass filter with the cutoff frequency of pi radian per second. At the input side, what all things you are having? What we can do is that we can just copy this circuit. Now at the input side, what all things you are having? DC you are having 2 pi by 3 radian per second, then 2 pi radian per second, then 2 pi, then 10 pi by 3, 14 pi by 3, 10 pi by 3, 14 pi by 3, and so on. All these frequency ranges you are having. Now cutoff frequency is pi. That means it will pass everything above pi. It will pass everything above pi. Right? So above pi it will pass everything. That means it will block this one and it will block this one. So at the output what you will be having? What will be your YT? So at the output what you will be having? You will be having some amplitude A3 sin 2 pi t plus some amplitude A5 Any amplitude it could be. Let's not write down A5A. Just let's just write down this amplitude would be A, this amplitude will be B, sine 10 pi by 3. This amplitude will be C, sine 14 pi by 3, because next was 14 pi by 3, then 6 pi by 14 pi by 3, then some amplitude D, sine 6 pi by t, and so on. Basically, at the output you will have this square wave minus the DC value minus one sinusoid, and one sinusoid of frequency 2 pi by 3. Your Yt is, what is your Yt? Your Yt is equals to square wave minus DC minus a sinusoid of some amplitude that was A1, which I don't know, having a fundamental frequency of 2 pi by 3. Now, can you let me know what is the fundamental frequency of this Yt? What is the fundamental frequency of this Yt? What you need to do? You need to take the HCF of 2 pi, 10 pi by 3, 14 pi by 3. But deep inside you know that this is your 3 omega naught. Say yes or no. Deep inside you know that this is 5 omega naught. Deep inside you know that this is 7 omega naught. Deep inside you know that this is 9 omega naught. So what you need to do? For fundamental frequency, what you will do? HCF of, well, let me write down here. For fundamental frequency, what you will do? You will take HCF of 3 omega naught, 5 omega naught, 7 omega naught, and so on. And what will be the HCF of all these things? Omega naught only. And what is the value of omega naught? 2 pi by 3. So it will be a summation of sinusoids having 0 DC value with the fundamental frequency of 2 pi by 3 radian per second. So these kind of statements could be written in the options. There is very rare chance that they will be interested in this value. It will be very rare chance that they are interested in this value. No, they are not interested in this value. They are just interested, they are not interested in finding out the Cn value here. They don't want you to find out the Fourier series coefficient. No. They just want you to know that if you know that what all frequency component this particular signal is having, okay, these frequency component it is having. Now there is a high pass filter. Now from this filter, what all frequency components will be passed? High pass filter is there, low pass filter is there, all pass filter is there. What will be the next one? Next one will be band pass filter or band stop filter that you need to see. So it is a band pass filter, right? So D option also you already know, which is a band pass filter. So let me add a page. So what is that D option? HT is sinc t cos 2 pi t. So which is a band pass filter with lower cutoff frequency of, it was between minus pi to pi, then 2 pi was the origin. So pi and 3 pi. Lower cutoff frequency was pi radian per second, and higher cutoff frequency was 3 pi radian per second. Well and good. Now input at the square wave, these components we are having. So again you can make the block diagram. Band pass filter with omega L equals to pi radian per sec and omega H equals to 3 pi radian per sec. At the input side, what all frequency components you are having? DC 2 pi by 3, then 2 pi, then 10 pi by 3, then 14 pi by 3, then 6 pi, all these components you are having. So it will pass only between pi to 3 pi. So it will not pass DC, it will not pass this thing, it will not even pass this one, because 10 by 3 will be 3.3, 10 by 3 will be 3.33, 10 by 3, 3.33. So anything it will not pass, these only it will not pass. So only what will be passed? Only this particular component will be passed. So at the output what you will be having? Only 2 pi. So what will be your output? Yt will be some magnitude alpha sinusoid 2 pi t. So output will be a pure sinusoid with a DC value of 0 having a fundamental frequency of 2 pi. Because in the previous example there was a lot of fundamental frequency. So what you do? You take the HCF. But here there is only one sinusoid of only this frequency. Right? So output will be a pure sinusoid having the 0 DC value with the fundamental frequency of 2 pi. So this was D. What about E? So here it would be delta t by 2. Otherwise it will not make any sense. So HT will be delta t by 2 minus sinc t into cos 2 pi t. So what it will be? Band stop filter. You know lower cutoff frequency is pi radian per second and higher cutoff frequency is 3 pi radian per second. So in the output everything would be there. DC value to everything. DC value a by 6 will pass. Along with that some alpha cos, not cos, sorry, sinusoid is only there. Alpha sine 2 pi by 3 t, this will also be pass, plus beta, only 2 pi will not pass because it is a band stop filter. So between pi to 3 pi, whatever the frequency component is there, which is 2 pi, that will not pass, rest everything will pass, right? Plus beta sine 10 pi by 3 t will pass, plus gamma sine 14 pi by 3 t will pass, rest all the things will pass. Now what will be the fundamental frequency of this particular thing? Fundamental frequency. Deep inside you know that this is my omega naught. This is my 5 omega naught. This is my 7 omega naught. What you need to do? You need to take the HCF of omega naught, 5 omega naught, 7 omega naught and so on. What that would be? Omega naught only. And what is your omega naught? 2 pi by 3 radian per second. So at least 10 questions can be framed from this one question. And this is the meaning of filter. Are you able to understand the meaning of filter? There was a time domain circuit. This was also time domain. In the output also I needed the answer in time domain only, but everything I did with respect to frequency domain. In the input was time domain. Everything is time domain only, but we are doing the analysis in frequency domain. Now it is also clear that why we need to study frequency domain analysis, because it is very easy to do the analysis. In time domain, you don't know, you will convolve xt with sine to sinc t. Basically, what will be your yt? If I consider the case B, let's just take the case B. So what will be your yt? Sinc t convolution with xt. So you do the convolution of these two. It will be very tough. But in the frequency domain, this analysis became very easy because they are simply the multiplication. So if you know the frequency spectrum, you just need to multiply. And we get to know that in the frequency spectrum of x of omega, we will have DC value, omega naught, 2 omega naught, sorry, omega naught, 3 omega naught, 5 omega naught and so on. We are not interested in the value. We are not interested in the magnitude. No, we are not interested in the magnitude. We are only interested what all frequency component will be present at the output. So in that manner we analyze it. So these kind of questions I am expecting in near gate examination. It could be 2026 or it could be 2027. Surely these kind of questions are coming. 100% I am telling you. Okay, because this is the topic which is left. IITs have not asked question on this particular topic. So this is any day could be coming in your examination, any day. Let's see the next question. Input xt is sine 40 pi t, 5 sine 20 pi t plus 2 sine 45 pi t cos 20 pi t. You need to tell the output yt. This time you are interested in the magnitude as well. So complete output yt you need to tell, magnitude and everything, frequency component, everything. Basically what will be your pure output yt? So one thing you can do, ht convolution with xt will be your yt. Will you do the convolution? No, very tough process. So what you will do? Frequency domain analysis. So now we need to do the frequency domain analysis. Do you know h of omega? Yes, sine 80 by pi t. Sine 80 by pi t. So what is my h of omega? This is my h of omega. Sine 80 by pi t. 80 by pi t with the amplitude of 1 by 5. This is your h of omega. At the input side, what all frequency components you are having? Just let me know what all frequency component you are having at the input side. 40 pi, 20 pi, 45 pi, 20 pi. Is that correct? Absolutely not. 40 pi is correct, 20 pi is correct. But what about this? This is 2 sin a cos b. So you need to break it down, no? What is 2 sin a cos b? Sin a plus b plus sin a minus b. Are you able to understand this point? What is your xt? Xt is sin 40 pi t. Sin 40 pi t plus 5 sin 20 pi t. 5 sin 20 pi t plus 2 sin a cos b. Sin a plus b plus sin a minus b. Sin a plus b plus sin a minus b. So it is having 40 pi radian per second, 20 pi radian per second, 65 pi radian per second, and 25 pi radian per second. But what all frequency component it is passing? Till 30 only. So what all will pass? This will pass, and this will pass. This will be rejected, and this will be rejected. But important thing is, what is the important thing? That it will give a gain of 1 by 5. So what will be your output? Your output yt will be, whatever the gain is there, it will give a gain of 1 by 5. So 5 into 1 by 5 will be 1 only, and here also you will get a gain of 1 by 5. So this is your output. So what is the way? The way is, first you need to see which all frequency components will pass, and then you need to see the gain. Look, basically, can you draw the graph of x of omega? Let's draw the graph of x omega. This is the answer which I have written, but let's draw the graph of x of omega. This is my x of omega versus omega. Okay. So let's first draw sin 40 pi t. That means it will have an impulse at 40 pi. Impulse at 40 pi. Right. Do you remember the Fourier transform of sinusoid? Yes. Sir, I don't remember the Fourier transform, but I know that 1 by 2j and minus 1 by 2j. This will be multiplied with 2 pi. Multiply with 2 pi. So here it will be pi by j, and at minus 45, at minus 40 pi it will be minus pi by j. At minus 40 pi it will be minus pi by j. And what is the amplitude here? Amplitude is 1 only, so this will remain 1. What about the second one? This is 20 pi t. So at 20 pi t, what you are having? Pi by j and not pi, I am writing 20 pi t. And here you are having minus pi by j. But it will be multiplied with 5. It will be multiplied with 5. This I am drawing x of omega. Right? X of I am not doing pi del omega minus omega naught. I just told you one thing. If you remember C of n, 1 by 2j minus 1 by 2j, then you can draw x of omega very easily. Just make your amplitude multiply with 2 pi, and your sequence will be converted to impulses, and then the job is done. So your sequences is converted to impulses, and your amplitude is multiplied with 2 pi. Nothing else is changing. Now other component is 65 pi. 65 pi. So 65 pi would be somewhere here, and minus 65 pi would be somewhere here. Amplitude being 1, amplitude being 1 only. So minus pi by j you will be getting here, here plus pi by j you will be getting. Minus pi by j plus pi by j. 25 pi t. So 25 pi t would be somewhere here. What is the amplitude? Amplitude is 1 only. So one thing I am messing it up here, that is this area I am making 5 pi by j. So this area should be a bit bigger, right? Because this is having more area, no? 5 pi by j, this is having more area. So this area should be a bit bigger. This area should be, this area should be a bit bigger. Minus 5 pi j plus 5 pi j. This was plus 5 pi j minus 5 by j. So minus 25 pi, here also minus 25 pi. This is also having minus pi by j. Minus pi by j plus pi by j. Now there is a filter. This x of omega will be multiplied with this filter. That means all these will be scaled by 1 by 5. All these scaled by 1 by 5. All these will be scaled by 1 by 5. Let me use different color of pen. This will be scaled by 1 by 5. What this was? This was minus 25 pi. This will be scaled by, this will also be scaled by 1 by 5. But what will happen to this one? 40 pi, 0 gain is there. So this will be multiplied with 0. This will also be multiplied with 0. This will be multiplied with 0. This will be multiplied with 0. So this was scaled by 1 by 5. This was also scaled by 1 by 5. So whatever the sinusoid was there, these sinusoids, these two sinusoids, these will come out as it is. Just the amplitude will be divided by 5. Just the amplitude will be divided by 5. Are you able to understand this point or not? So everything will come as it is, just the amplitude will be divided by 5, nothing else. Are you able to understand this point or not? So here I am not gonna do that, sir, 5 pi by j into 1 by 5, and then I am having an impulse omega minus 2 pi plus minus 5 pi by j, then amplitude is 1 by 5, then I am having an impulse omega plus 20 pi. So now I take the inverse Fourier transform. So all these things I am not gonna do. You can do in this manner as well. You take the inverse Fourier transform. It will be sinusoid only, right? Because 5 is getting cancelled out. What you are getting? Pi del omega minus 20 pi minus pi del omega plus 20 pi and divided by j pi. What is the Fourier transform? What is the inverse Fourier transform of this particular thing? That is e to the power j. Here you need 2 pi divided by 2. Why you need 2 pi? Because 1 is having a Fourier transform of 2 pi del omega. So e to the power j omega naught t will have a Fourier transform of 2 pi del omega minus omega naught. So what this would be? E to the power j 20 pi t. And what this would be? E to the power j minus 20 pi t divided by 2j. So what it is becoming? Sine 20 pi t. This is coming at the output. So basically nothing happened. Only the thing that happened was it was multiplied with 1 by 5 and this was multiplied with 1 by 5. 1 by 5. And then your x of omega became y of omega. So this is something that happened. So directly I can write down that my sinusoids will be going through a gain of 1 by 5. I am just telling you with respect to diagram as well, so that everything should be clear. Who knows, in the examination you might have to draw the diagram, and we will deal one question where you will have to draw the diagram. Because what I will do there, I will introduce a shift. So there you will understand that what will happen if I introduce a shift. So this is a revision question, that you draw the frequency spectrum of this one, then you draw the frequency spectrum of this one. What is the difference between these two? I have introduced a shift. So introducing a shift, what changes it will make in its frequency spectrum, that you need to check. Okay, so do it on your own, draw the frequency spectrum, which are very easy, and then we will solve this question. So let me show you this question, try doing it on your own. If you are not able to solve, then also it is fine, because this is a very good question. xt is the input, ht is the impulse response, and yt is the output. For impulse response, I am giving two graphs. One is the magnitude spectrum, other one is the phase spectrum. This is your xt, you need to find out yt. So this is the answer which is already written, but try doing it on your own. Try it. I know you might not be able to solve it, but you will learn a lot of new things here. So first do this question, then try this one. Okay. I will take a break because it's been more than 1 hour. So I will take a break and then I will come back and we will study all these things. Thank you. Yeah, so did you try this one? x1t, you need to draw x1 omega. So you know that for sinusoid we are having c1 value of 1 by 2j and c of minus 1 value of minus 1 by 2j, right? So 1 by 2j and minus 1 by 2j. So when you make the frequency spectrum, what do? You make the sequence as impulses and your frequencies as, here it would be omega naught and minus omega naught. And what is the value of omega naught? That is 5 pi. So this will be 5 pi minus 5 pi. 1 by 2j multiply with 2 pi. So pi by j and minus pi by j. There you go. This is your x1 omega. What about y1 omega? So y1 omega is cosinusoid. 1 by 2, 1 by 2. So it will become 2 pi by 2. So there will be an impulse of area pi, and there will be another impulse of area pi. At frequencies of omega naught, what is the value of omega naught? 5 pi and minus 5 pi. So this was your x1 omega, y1 omega. We have seen the derivation as well. Let's write down x2t. What is your x2t? Sine 5 pi t plus pi by 4. So it can be written as e to the power j 5 pi t plus pi by 4 plus e to the power minus j 5 pi t plus pi by 4 divided by, okay, it is a sinusoid, so there will be a negative sign, divided by 2j divided by 2j. So basically e to the power j pi by 4, this is a constant value, divided by 2j, e to the power j 5 pi t minus e to the power minus j pi by 4, this is also a constant value, e to the power minus j 5 pi t. Are you able to see something? What will be your x2 of omega? X2 of omega will be same, ditto same it would be, nothing changes would be there, just whatever the phase was introduced, here the phase was introduced, that was pi by 4, that will be introduced here, and here there will be negative phase. Are you able to understand this point? In the area of the impulse, only the phase would change. Let's see it here. Divided by 2j. What will be the Fourier transform of e to the power j omega naught t? That would be 2 pi del omega minus omega naught minus e to the power minus j pi by 4 divided by 2j 2 pi del omega plus omega naught. So what do you see here? What is your x2 of omega? X2 of omega. So impulses will be there at 5 pi and minus 5 pi. There will be an impulse of amplitude, sorry, impulse of area pi by j into e to the power j pi by 4, and here it is pi by j into e to the power j minus pi by 4. Right? The similar thing will happen to y2 of omega as well. What will happen to y2 of omega? Can you do the derivation in the same manner? Yes, you can do the derivation in the same manner. What you will see there? You will see that if I ignore the phase shift, then this will be the graph I will be getting. This will be the graph of y2 omega if I ignore the phase shift. So what will be my y2 omega? Here you can see that this graph and this graph is same. Only there is a difference of phase shift. This phase shift is e to the power pi by 4. This phase shift is pi by 4. So e to the power pi by 4 this guy is getting, and e to the power minus pi by 4 this guy is getting. So positive frequency will get the same phase shift, and negative frequency will get the negative phase shift. So here there was positive, so this is also getting positive phase shift. Let's derive it in the case of cosinusoid as well. Let's derive it. Okay, let's not write it down directly, let's derive it. No issue. Let's do the derivation. So I will add a page. What was your y2t? Your y2t was cos 5 pi t minus pi by 3. Cos 5 pi t minus pi by 3. That would be e to the power j 5 pi t minus pi by 3 plus e to the power minus j 5 pi t minus pi by 3 divided by 2 divided by 2. So here you are getting e to the power j minus pi by 3 divided by 2, and I am taking the inverse Fourier transform. So this factor would be there. What will be the inverse Fourier transform? What will be the Fourier transform of this one? That would be pi 2 pi del omega minus omega naught, then plus e to the power j pi by 3 divided by 2 into 2 pi del omega plus omega naught because of the negative sign, omega plus omega naught. Okay, so if you draw y2 of omega, what you will be getting? y2 of omega versus omega. So there will be an impulse at 5 pi and there will be an impulse at minus 5 pi. So pi e to the power j pi by 3, pi e to the power j pi by 3, and here also you are getting the same thing, pi e to the power j minus pi by 3, pi e to the power j minus pi by 3. So what do you see here? If you compare this graph, with this graph, so positive frequency has got the, just a second, here it is negative, here it is positive, really sorry, here it is positive. This phase shift is e to the power minus j pi by 3, right? And here it is positive. So what do you see here? When you came from here to here, then phase shift you provided was minus pi by 3. So the positive frequency will get the same phase shift, and negative frequency will get the negative of this. And same goes here. I just draw the diagram of pi by j. Here, what was the shift? Pi by 4. So positive frequency will get the same phase shift, which was pi by 4, and negative frequency will get the negative of this one. So from now onwards, if you see any sinusoid or cosinusoid with the phase shift, then will you do any derivation like this? Which derivation? Let me erase it. So will you do any derivation like this, or you will do this derivation? No, you don't have to do any derivation. What you need to take care that if there is a phase shift, that will be completely reflected. Directly it will be reflected to the positive frequency. You need to take care of the sign. Here the phase shift was of a positive sign, here the phase shift is of negative sign. So it will be reflected to the positive frequency, and to the negative frequency, negative of this will be reflected. That's it. Or you can do the derivation as well. In the examination, in the worst case, if you forget, it will take you hardly 30 to 40 seconds to do this particular derivation. So you can do the derivation as well. Now, the otherwise process should also be clear. Like if this diagram is given, then you should know what will be your x2t. Because what really happened here, this did not change, pi by j. You will remember, sir, 1 by 2j and then multiply by 2 pi. So pi by j. Yeah, this is showing complete sinusoid. This is also showing sinusoid at the frequency of 5 pi. But you see that at a frequency of 5 pi, you see that there is a phase shift of pi by 4, extra phase shift of pi by 4. So this is a sinusoid at 5 pi frequency, but another phase shift is there which is of pi by 4. So just by looking at the diagram, you should also have the habit of writing down x2t. Basically, looking at the diagram, you will get this expression. From there, you will calculate inverse Fourier transform. From here, you will get here, and then you will get here. So this process you need to do, or what you can do, just by looking at the diagram, you should have the ability of writing down this particular expression. How will you write down? Sir, pi by j minus pi by j, I am comfortable at the frequency 5 pi minus 5 pi. Just the extra thing is that this is giving you a phase shift of extra pi by 4. So only at the positive frequency I will see the phase shift. At the negative frequency, just the negative phase shift would be there. At the positive frequency, I will see the phase shift, minus pi by 3 phase shift is there. At 5 pi minus 5 pi, that means my fundamental frequency is 5 pi. What is this? This is your cosinusoid. Pi, pi. Okay. So what I will get? Cos 5 pi t plus, sorry, cos 5 pi t minus pi by 3. Cos 5 pi t minus pi by 3. There you go. Okay. So let's solve this question. Let's try solving this question. Here, the thing is, h of omega is given with the two waveform, magnitude and the phase. Okay, magnitude and phase spectrum both are given. You need to find out y of t. And x of t is given here. This is your x of t. So what would be your y of t? So I will not be interested in y of t. Why is that so? Because I will have to do the convolution and I don't even know the inverse Fourier transform of this one. Basically, I don't even know what is ht. So directly, just by looking at the question, I would get to know that. I will apply the frequency domain analysis. So my y of omega will be equals to x of omega dot h of omega. So I can find out my x of omega, then I'll need to multiply with h of omega. But h of omega is directly not given. How h of omega is given? H of omega is given as magnitude and the phase. Do you agree to this point? So x of omega as it is, magnitude and the phase. Well and good. Okay. Now let's see your xt. What is your xt? Xt is 2 sine 5 pi t plus pi by 4 plus 4 cos A cos B. So this can be written as 2 cos A cos B, no? 2 I am taking outside, 2 cos A cos B. So what is the formula of 2 cos A cos B? Sin A minus B minus sin A plus B, right? Sin A minus B, this is the formula, no? Sin A minus B minus sin A plus B. Because sin A cos B minus 2 cos A cos B, cos A plus B plus cos A minus B. That, sorry. The formula is cos A plus B plus cos A minus B. Cos A plus B plus cos A minus B. What is cos A plus B? Cos A cos B minus sin A sin B. And what is cos A minus B? Cos A cos B plus sin A sin B. Yeah, so this is the formula, cos A plus B plus cos A minus B. So the formula is cos A plus B cos A plus B. So A plus B, so 25 plus 10, it will be 35. 25 plus 10, it will be 35t plus pi by 3 plus cos A minus B. Cos A minus B. So what you will be getting? 15 pi t minus pi by 3. There you go. And multiply with 2 too. So this I can write down in this manner, that this is multiplied with 2 and this is also multiplied with 2. So this is having a fundamental frequency of 5 pi, 35 pi, 15 pi. Now this will pass till 20 pi only. This will pass till 20 pi only, because after 20 pi it is providing a zero gain. So this is gone. So I need to study this and this, right? So this will give you some gain and some extra phase. Are you able to understand this point? Let's draw the diagram of x of omega. Can you draw the diagram of x of omega? X of omega. Sinusoid at 5 pi. Sinusoid at 5 pi. So at 5 pi and minus 5 pi, you are having sinusoids. And extra phase pi by 4 will be added. Extra phase pi by 4 will be added. And then cosinusoid at 15 pi, extra phase pi by 3 will be added. Cosinusoid at 15 pi, extra phase cosinusoids 15 pi and minus 15 pi. In case of sinusoid, what is the extra phase? E to the power j pi by 4. So for the positive frequency, it will be getting e to the power j pi by 4. Here I am not writing down the amplitude. Whatever the amplitude is coming, I don't care about that. Why is that so? We will see it. And here extra phase is, here what will be the extra phase? The extra phase will be e to the power minus j pi by 3. For cosinusoid, it is minus j pi by 3. And here it will be plus j pi by 3. Now whatever the amplitude is there, I don't care much about that amplitude, because I know that it will be set up with the mode of h of omega. Basically now what will happen, in this x of omega, h of omega will be multiplied. Here what will be the amplitude? Here the amplitude, since it is sinusoid, so it will be pi by j, and then there is a factor of 2, so 2 will also be multiplied, right? But I don't need to write down that. I don't need to think about it. Now h of omega will be multiplied. So here there will be some factor which I don't care. Here there will be some factor. Here also there will be some factor. Here also there will be some factor, and here also there will be some factor. Whatever that factor is, that will make sure that this is my signal. because I am drawing x of omega. Whatever the factor is, that is making sure that this is my signal. But now what will happen? H of omega will be multiplied. So h of omega at 5 pi frequency, h of omega at 5 pi frequency is giving you an amplitude of 3 and phase of 2 pi, sorry, 5 pi frequency. So phase of 3 pi by 2, because you can see here, if you are going from 0 to 10 pi, then it is increasing by 3 pi. So if you go from 0 to 5 pi, then it will increase by 3 pi by 2. Are you able to understand this point? So at 5 pi frequency, it is giving you a gain of 3 and a phase of 3 pi by 2. So if I write down h of omega at omega equals to 5 pi, that would be giving a magnitude of 3 and a phase of 3 pi by 2. So this will be multiplied, no? Your impulse, this impulse will be multiplied with this particular value. Are you able to understand this point, what I am saying here? This impulse that you are having, this will be multiplied with h of omega, and your h of omega is mod of h of omega into phase of h of omega, e to the power j phase of h of omega. So this impulse e to the power j pi by 4 will be multiplied magnitude and the phase of 3 pi by 2. And thus here at minus 5 pi, what is the phase? At minus 5 pi, the phase is minus 3 pi by 2. This value is minus 3 pi by 2. And here this value was plus 3 pi by 2. Say yes or no? And magnitude is 3. So now this sinusoid, and what about minus 5 pi? What about minus 5 pi? Here the magnitude was also plus 3. So at 5 pi frequency, the magnitude is 3. So this sinusoid will be multiplied with 3 and the phase will also be multiplied, which is 3 pi by 2. So for this one, the phase is 3 pi by 2, and for this one, it will be multiplied with 3 only, but the phase is minus 3 pi by 2. Do you understand this point? You need to have some patience in the examination hall while solving some problem. 3 minus 3 pi by 2, 3 plus 3 pi by 2. So phase here is e to the power j 3 pi by 2, magnitude is 3. Phase here is e to the power minus j 3 pi by 2, magnitude is 3. Well and good. What about 15 pi? At 15 pi, what is happening? At 15 pi. So when you are going from 10 to 20, it is decreasing by 1. So if you go from 10 to 15, here the magnitude will be 1 by 2. This is your 15 pi. And here also the magnitude will be 1 by 2 only. This is also your minus 15 pi. Why I am caring about 15 pi? Because this impulse will be multiplied with h of omega. So magnitude is 1 by 2. Magnitude is 1 by 2. What about the phase? So when you are going from 10 to 20, it is decreasing by 3 pi. So if you go from 10 to 15, it will increase by 1.5 pi. That means here also I will get 1.5 pi. That means I will get 3 pi by 2. And same goes here. Here also I will get minus 3 pi by 2. So what do you see here? What do you see here? This is being multiplied with the factor of 1 by 2. With the factor of 1 by 2. And the phase that is there, that is phase is e to the power j 3 pi by 2. And this is being multiplied with magnitude of 1 by 2 only, but the phase is e to the power minus j 3 pi by 2. So what is the new thing that is coming? That here the amplitude will increase by 3. Sorry, here the amplitude will become 3 times, and here the amplitude will become half time. In y of t, this is not just your x of omega, now it is becoming h of omega as well. So in y of t, what will happen? In y of t, what will happen? If I talk about the amplitude, so this was having 2 amplitude. At 5 pi t, the amplitude will become thrice. So this was having 2 amplitude, now this amplitude will become 6. 6 cos 5 pi t plus, now we need to see the phase. Initially my phase was pi by 4, here plus pi by 4 I can see. Now in pi by 4 what is added? 3 pi by 2 is added. And what has happened here, this side? Here it was minus pi by 4, and in that as well 3 pi by 2 is also added. Basically the phase has to be same. Here it was in plus, here it is in minus. What I mean to say is that e to the power j theta 1 plus e to the power minus j theta 2 divided by 2. This will not make anything. But if I say this is theta 1 and theta 2 is, this is the scenario. If this is the scenario, then it will make cos theta 1. So whatever the positive part was added this side, the same negative part was added to the other side. So this was positive angle of pi by 4 plus 3 pi by 2, and this is the negative angle of pi by 4 plus 3 pi by 2. So whatever the positive angle this got, initially it was pi by 4, but now it has got another 3 pi by 2. There you go. Are you able to understand this point? With good amount of patience you need to solve these problems. Now what is happening with this amplitude? Here the amplitude is becoming half, which you can directly see from here. Amplitude will be very easy for us. In the examination hall, amplitude will become very easy. Amplitude is becoming half. You need to see the phase. So once there is a phase shift already in these sinusoids and cosinusoid, the phase shift was pi by 4 and minus pi by 3. This we already know how to show it. In positive side, in the positive frequency, you give the same phase shift pi by 4 and minus pi by 3. Don't care about amplitude and anything. Like don't even care about this negative. You can make it positive as well. Even in case of sinusoid, you make it positive. Doesn't matter. Because here we are not caring about amplitude. Here we are not caring about sinusoid, cosinusoid. Here only concern is magnitude and phase. Sinusoids and cosinusoids are not changing. Nothing is changing. Only concern is magnitude and phase. So here magnitude became 3 times, here it became half time. So now it will be half, that means you will be getting, this was sine, sorry, this was not cos, this was sine. So now 2 will be multiplied with half, so it will be 1 only, cos 15 pi t. Now the initial phase was minus pi by 3, in that 3 pi by 2 is added. Say yes or no? Initial phase was minus pi by 3, in that 3 pi by 2 is added. So here the phase is kind of something like this. And here what was the scenario? Initial phase was pi by 3, and in that 3 pi by 2 is subtracted. So this is the positive part, this is the negative part. Basically one is positive part, one is negative part. That means yes, this will be again same cosinusoids only. So basically previously the phase was minus pi by 3, now plus 3 pi by 2 is also added. Are you able to understand this point? Initially this was the phase, now plus 3 pi by 2 is also added, and on the negative frequency what is happening? Pi by 3 minus 3 pi by 2, or you can write it down in this manner, in this manner. So whatever this phase is there, e to the power j theta, so this is e to the power minus j theta, right? So I was having an initial phase of minus pi by 3, but I am adding 3 pi by 2 as well. So this is my final answer. Now I can convert it. So this will go into fourth quadrant. In fourth quadrant sine is negative, and since 3 pi by 2 is there, so it will convert to cosinusoids. So minus cos 5 pi t plus pi by 4 plus 3 pi by 2, cosinusoid is positive, so this will become sine 15 pi t minus pi by 3. A very good question, and you can expect these kind of questions in future, okay, where there are shifts. So nowadays I am seeing one common thing in Fourier transform questions, that is they are introducing shift in all the signals. In 2025 as well there was a question where there was a shift involved. In 2024 as well there was a question where there was a shift involved. So they are shifting the signals now. So in XT as well I made a shift, and here also there is some phase. Here also it is having some phase, and this is also having some phase. So if they are having the phase, then how will you analyze? Is that clear to you? So this particular question is having all the combinations, everything that is required. So if there is a phase, you know how to draw x of omega. Yes, I know how to draw x of omega. I will not care about the amplitude much. I will not care about the area much here. Whatever the value is coming, I don't care about that, because it is already making sure that this is sinusoid, this is complete cosinusoid. Whatever the sinusoid and cosinusoid that I am having, that is being reflected here. But now the problem will be, I will be multiplying it with h of omega. So now what new factor is coming? That is the matter of concern. So new factor that is coming here, it was multiplied with 3. So our sinusoid was being multiplied with 3. So our sinusoid amplitude will be increased by, it will be 3 times. Now the important part is phase. So positive frequency is having a phase of 3 pi by 2. So now the phase will be increased by 3 pi by 2, and negative frequency is having a phase of minus 3 pi by 2. So yeah, it is all okay. So phase will be increased by 3 pi by 2. What about 15 pi? So at 15 pi you are having a gain of half. That means amplitude will be reduced to half. So amplitude will be half. So initially my amplitude was 2. So now it became 1. Now positive frequency is having a phase of 3 pi by 2, and negative frequency is having a phase of minus 3 pi by 2. That means whatever the phase that positive frequency is getting, 3 pi by 2. So the same phase your cosinusoid will get. Same phase your cosinusoid will get. Is that clear to you? All fine. So always look at the positive frequency when you are writing down the expression of sinusoid or cosinusoid. Only you need to look at the positive frequency. So amplitude will become 3 times. Now look at the phase, pi by 4 plus 3 pi by 2, pi by 4 plus 3 pi by 2. Now look at the phase, minus pi by 3 plus 3 pi by 2, minus pi by 3 plus 3 pi by 2. And this is the same thing that I taught here, that if you need to go from here to here, then how will you think? Pi by j minus, here it is pi by j and here it is minus pi by j. So it will convert into sinusoid only, that doesn't matter. But if I need to see the phase, so I will look at the phase of only positive, that is plus pi by 4. And here if I need to look at the phase, I will only see the positive frequency, that is minus pi by 3. So yes, the phase is minus pi by 3. So in case of phase, always look at the positive frequency. Okay, well and good. That's it. This is the end of this video. In this video we just studied about, you can call it filter or you can call it LTI system, whatever you want to call it. But if there is a system given, impulse response could be given, input could be given, how will you analyze YT? This is what we studied, and different questions we solved. I hope you enjoyed this lecture. Now there is something called eigenvector and eigenfunction and eigenvalue. Okay, there is something called eigenfunction and eigenvalue. Basically the concept is, this is your LTI system. If you apply a signal xt and your output yt is equals to some constant value into xt, okay, some constant value into xt, then this is known as eigenvalue and this is known as eigenfunction of this LTI system. So this concept in detail we will study after the Laplace transform. Mostly it is taught in Fourier transform only, but I will relate Fourier transform and Laplace transform there. That's why I thought that this should be picked after studying Laplace transform. So after studying Laplace transform, we will be studying this particular concept. So if you are waiting for this concept, those who are studying it again, like those who are droppers, so dropper student might be thinking that, sir, why we did not study eigenvalue and eigenfunction? So for them I am telling that we will be studying it after Laplace transform, and those who are studying for the first time, they don't need to care about it because they don't even know what is the topic, right? So this is only for the dropper student. They will be texting me, sir, when we will study eigenvalue, eigenfunction. So for them I just write it down that after the Laplace transform we will be studying it. All good, all fine. So I hope you enjoyed this lecture. I hope you enjoyed these kind of problems which are not usually taught. You will not find these questions in many of the notes. So these kind of problems, like, and then these kind of filter type problems. So these are very good problems. Okay, and hopefully they will be coming in your examination in near future. And the last one was very important. From here it became very important that filter response is given, which frequencies will pass. First thing, that is the frequencies will pass, and the another thing, you need to see the amplitude. So this is a very straightforward problem. There is no phase spectrum, so nothing is there. This was simple h of omega. But in the next question, what we did, we introduced different magnitude spectrum and phase spectrum. So this was giving a different phase at different frequencies, it was giving a different phase. Then we got to know that wherever our sinusoid or cosinusoid is present, that is our matter of concern. So at 5 pi and 15 pi, that was our matter of concern. At both we were getting, in positive frequency we were getting the phase of 3 pi by 2 and 3 pi by 2. In negative frequency we were getting the phase of minus 3 pi by 2 and minus 3 pi by 2. and in that manner the same phase will be introduced in the output as well. So when I talk about sinusoid and cosinusoid, I only look at the positive frequency phase. Okay, so plus 3 pi by 2 and plus 3 pi by 2, and then I saw the amplitude. So this was the amplitude 3, this was the amplitude 1 by 2, and from here only the concept of eigenvalue and eigenfunction comes out. Actually it comes out from here, e to the power j omega naught t. So that we will see when we study Laplace transform. All good, all fine. So let's meet in the next lecture. In the next lecture, some miscellaneous points we are going to study, like what is the meaning of baseband signal, what is the meaning of band pass signal. Very, very simple. Then we will study about Nyquist rate. So next lecture will be short only. I hope it will not take more than 1 hour. So in less than 1 hour, we will be able to complete the next lecture, and after that we will move to sampling. All good? Thank you. Yeah, welcome back. So now we need to study about baseband and band pass signal. Look, if I tell you that xt is a power signal, xt is an energy signal, xt is an even signal, xt is an odd signal, so you comment on the time domain analysis, right? Like xt is a power signal, so you are commenting on the time domain analysis. But if I say it is a baseband signal or band pass signal, that means you are talking about frequency spectrum. So these definition will be given based on the frequency spectrum. Are you getting this point? So whenever I say baseband signal or whenever you see band pass signal, in your mind frequency spectrum should click, right? Now second thing, when we were studying our LTI system, in the previous part of this video we studied about low pass filter, high pass filter, all pass filter. So all these kind of filters we studied. So at that time we were commenting on HT, that frequency spectrum of your impulse response could be like low pass filter, it could be like high pass filter. So we were commenting on HT. Based on your HT, you are getting low pass filter, high pass filter, band pass filter, band reject filter, all pass filter. But now you are commenting on the signal. This is HT is not a signal. This thing I have said again and again in a lot of videos when we were studying about LTI system. HT is not a signal. HT is the impulse response of LTI system, right? So HT is not a signal, but now we are commenting on a signal. The signal could be XT, signal could be YT as well. So now baseband signal and band pass signal, these are defined with respect to a signal, and filters are defined with respect to impulse response. Are you able to understand this point? So that's why here signal word is written. But in the filters you don't say low pass signal. Okay, low pass filter you say. Filter means you are commenting on HT. Signal means you are commenting on XT or YT. Okay, well and good. So baseband signal is known as low pass signal as well. Baseband signal is known as low pass signal as well. This is the other name, right? So signal whose frequency component ranges from 0 Hz to a certain frequency. So now you do not know what could be the frequency spectrum. The frequency spectrum could be like this, but it would be band limited to, the word that is used, band limited to. Band limited to. What I am saying? Band limited to. What is the meaning of band limited to? That means the maximum frequency is Fmax. So what we are saying, the signal whose frequency component ranges from 0 Hz to a certain maximum frequency, which is Fmax. So from 0 to Fmax, it will throw some non-zero frequency value, some non-zero value. Okay, and since these are real world signals, so we have to make symmetric here as well. So this is the frequency spectrum of a baseband signal. This is how you can show, or like any way you can show. You can show something like this as well. How I show? Something like this as well also you can show. You don't know what is the value it is throwing. You just know one thing. When we are commenting on baseband signal, we are just commenting on the frequency. So you know one thing, that it will be starting from 0 and it will be ending at Fmax. Similarly, I need to make in the negative side as well. So this is the meaning of baseband signal. Usually how we will show it? So this is how we will show it. Usually we will study it in communication system, we will study it in signal system as well. So whenever I say baseband signal, so this is how I will be showing it. In the textbook you can get this form as well. In the examination you can get this form as well. But this is how we will be showing it. And mostly in the examination, this is the form you will be getting it. Okay. So this is how a baseband signal will be shown. Minus Fmax plus Fmax. Okay. Any amplitude would be there, that we don't care. So from 0 to Fmax it is non-zero. Now the other one is band pass signal. So what do you think what should happen in band pass signal? So its frequency range will be from ascertain lower frequency to ascertain higher frequency. So this is how its frequency spectrum would look like. From ascertain lower frequency to ascertain higher frequency, it will be non-zero, otherwise it will be zero only. So any kind of pattern could be there, but symmetric, same kind of pattern I need to make in the negative hand side as well. So any kind of pattern could be there. I am just making it like this. So it is not starting from 0. If it was starting from 0, it would have been band, baseband. It would have been baseband, or you can say low pass. But the frequency component is non-zero between two particular frequency value, f1, f2. This would have been minus f1. This would have been minus f2. We can show it something like this as well. That it is non-zero between two frequency ranges. Right? Or usually we will show it like this, usually, or any way you can show it. This is also it is, this is how also it is shown. So it is non-zero between a certain frequency range. So this is known as band pass signal. Okay, very simple definition. Again and again these words will be used. That's why I wrote it down here. A baseband signal is band limited to 5 kHz. Draw its frequency spectrum. So how will you draw it? Band limited to 5 kHz. What is the meaning of that? Band limited to 5 kHz. That means it will be non-zero between 0 to 5. Band limited to 5 kHz. So this is how you will show it. Okay, you can show it as x of f. A band pass signal is band limited between 5 kHz to 7 kHz. So what will be its frequency spectrum? 5 to 7. So this is how I can show its frequency spectrum. Any way you could show. Usually we will be using these kind of spectrums. Five kilohertz to 7 kilohertz, minus 5 to minus 7. You can call it M of f. M stands for message signal. Okay. MT means message signal. So again and again in the next lecture or from this lecture only we will not be using XT. Mostly we will be using MT. MT means message signal. So any message signal will be there. This message signal we will be sampling sometimes. All these kind of things we will be doing. So we are just building up the base for sampling. Okay, we are just building up the basics of sampling here. Nothing else. Now if MT is a baseband signal, this is what I am telling you. So just let me know what will be MT dot cos omega naught t. Will it be baseband? Will it be band pass? What do you think? So I am saying that my MT is band limited to this much frequency. MT is a baseband signal. MT is a baseband signal. That means it is band limited to F max. It is band limited to F max. Now I am multiplying with cos omega naught t. So now you should have the habit. What is the meaning of multiplying with cos omega naught t? It will be shifted rightward. It will be shifted leftward. Right? So if you multiply with cos omega naught t, this was your MF. Now you have multiplied this signal I am calling as PT. Okay. So now what will be my P of F? Shifted here. the center will be shifted to f naught, right? Center will be shifted to f naught. I hope this is clear to you, right? Because we have seen it again and again. Mt dot cos omega naught t, you will write it down, e to the power j omega naught t plus e to the power minus j omega naught t divided by 2, and then you will calculate the Fourier transform, right? Mt e to the power j omega naught t plus mt e to the power minus j omega naught t divided by 2 divided by 2. If mt was having a Fourier transform of m of f, if mt was having a Fourier transform of m of f, so mt multiplied with e to the power j omega naught t will have the Fourier transform of m of f minus f naught divided by 2 plus m of f plus f naught divided by 2. Is that clear to you? So this process is clear to you. Again and again we have seen it, like 10 times we have seen it, and every time I am deriving it as well. So this center is shifted to f naught, right? And this center is shifted to minus f naught. It was having f max from 0 to f max away it was. So from f naught to it will be away f naught plus f max, right? And behind it will be f naught minus f max. Is that clear to you? Right? Now this part will be just negative of this one, that means it will be minus f naught plus f max, and this part will also be negative, so it would be minus f naught minus f max. Well and good. So this will be your P of f. Are you able to understand this point? But what if your f naught was equals to f max? What I am saying, your f naught was equals to f max, then this point would have come to 0, right? This point also would have come to 0. So if your f naught was equals to f max, then it would have become a baseband signal only. Like here you see it feels like it is bandpass signal. Say yes or no, it is a bandpass signal. Surely it looks like it is a bandpass signal, but you don't know the value of f naught. If your f naught was equals to f max, then the problem would have been that this would have been 0 and this would have been 0. So this is how the response would look like. So it is going from 0 to a certain value which is equals to 2 f naught, because f naught is equals to f max, so it is going from 0 to a certain value which is equals to 2 f naught, right? So it would have become a baseband signal only. As of now it is a bandpass signal, but if f naught is equals to f max, then it would become a baseband signal only. So here I am writing it is baseband, it is bandpass signal, but f naught is not equals to f max, because if it is equals to f max, then your frequency spectrum would be starting from 0, and if it is starting from 0, then surely it will be called as baseband signal. All good, all fine. Okay, so let's move to our next topic, which is known as Nyquist rate. So if you have already studied Nyquist rate, then forget about whatever the definition you have studied. No matter whatever the definition that you have studied, you need to forget that definition. Okay, now new definition you are going to study. So if I am saying that my message signal MT is having its maximum frequency component of FM, like here it was having a maximum frequency component of f max, it is having a maximum frequency component of f naught plus f max, this is having a maximum frequency component of 5 kilohertz, this is having a maximum frequency component of 7 kilohertz. So similarly your maximum frequency component of MT is FM. So what will be the Nyquist rate? It will be twice of FM. That's it, twice of FM. So whenever they are asking you Nyquist rate, what will be your target? That sir, I will find out the maximum frequency component. If I have find out the maximum frequency component, I just need to double it. That's it. So this is known as Nyquist rate. There is another term which is known as Nyquist interval. Nyquist interval. So Nyquist interval is 1 by Nyquist rate. So always first I will find Nyquist rate and then I will find out Nyquist interval if they are asking. So a baseband signal is band limited to 7 kilohertz. A baseband signal MT is band limited to 7 kilohertz. You need to find its Nyquist rate. What does that mean? The maximum frequency component is 7 kilohertz. So what will be its Nyquist rate? Nyquist rate will be 2 into FM. That would be 2 into 7 kilohertz. So Nyquist rate would be 14 kilohertz. There you go. Okay, next question. Now the same baseband signal is multiplied with the sinusoid of 10 kilohertz fundamental frequency, a new signal xt is generated, what will be the Nyquist rate of xt? What I am saying, a new signal xt is generated by multiplying your message signal with sinusoid of some frequency. So omega naught is equals to 2 f naught, 2 pi f naught, where f naught is given as 10 kilohertz. So this is what they are doing. They are multiplying xt with the sinusoid. Sorry, they are multiplying mt with the sinusoid. Basically, they are multiplying this signal with the sinusoid of 10 kilohertz frequency. So what will happen? The center will move to 10 kilohertz, right? How will your x of f look like? X of f. Mt multiply with sinusoid, so same process is happening. M of f minus f naught, m of f plus f naught, right? So same process will happen. Or you can derive it as well. Again, I am deriving it for you. Since this is a recorded lecture, so I have to do everything, right? I cannot keep anything on the student because different people can have different kind of aptitude. So from here, what you will get? M of f minus f naught, m of f plus f naught divided by 2j divided by 2j. So 1 will be shifted here. The center will be moved to f naught. Amplitude will be divided by 1 by 2j, but I don't care about that. Your amplitude, whatever the amplitude, let's just say here the amplitude was a. So now the amplitude will be a by 2j. But I don't care about the amplitude. As of now, I am only talking about the frequency content. So center was at 0. This has moved to 10 kilohertz because f naught value is 10. So now this point was minus 7k, this point was plus 7k. So 0 has moved to 10k. So 7k plus 10k will be 17k. And 10k minus 7k would be 3k. So this point would be 3k. Now the similar thing would be happening to the negative side as well. Similar thing would be happening here as well. Why I am drawing it on the negative side? Because there is a negative sign in between. That's why. So this point would be just negative of this one, minus 3k. This would be minus 10k. And this point would be just negative of this one, minus 17k. So what is the maximum frequency component? 17k. So what will be your Nyquist rate? 2 into 17k. 34. Okay. This would be your Nyquist rate. Here it was. This was the Nyquist rate. All good? Okay, so this important discussion we will do, but I need to drink some water. So we will do it. You can try on your own. MT is a baseband signal, band limited to FM. You need to find the maximum frequency component of m of minus t, m of at, m square t, m cube t, m to the power kt, d by dt of mt. So try doing it on your own. Think about it. What should be the answer? Think about it. Okay. Okay, so let's get started. So MT is a baseband signal, band limited to FM. Look, whenever we are talking all these things, that means we are talking about real signals. Right here, I am taking that mirror image. So we are talking about real signal. It might happen in the examination hall that they will not write that MT is a real signal, real baseband signal, band limited to FM. They will just write MT is a baseband signal, band limited to FM. So that means you need to consider it is real only. Okay, so it has to be real. Now find out the maximum frequency component of m of minus t. M of minus t. So MT is having a frequency spectrum of MF. So what will be the frequency spectrum of m of minus t? That would be m of minus f. So basically you need to take the mirror image. You make any frequency spectrum, you just need to take the mirror image. This was your m of f. I am saying this is your m of f. This is fm. This is minus fm. Now if you take m of minus f, it will be the same only, no? Maximum frequency component will be fm only. So for m of minus t, maximum frequency component will be fm only. Taking the mirror image will not change. The frequency spectrum will not change. Like it has to be already symmetric about the origin, no? It has to be already symmetric about the origin. Or it might happen that it is something like this. It might happen that the frequency spectrum is looking something like this. Again you take the mirror image, so maximum frequency component will be again fmax only. This was fmax, this was minus fm. So if you take the mirror image, it will not change. So m of minus t will have the same frequency component, same maximum frequency component. So here maximum frequency component will be f of m only. What about m of at? What about m of at? So if mt is having mf, So m of at would have m of f by a, and then in the outward 1 by mod of a would also come out. Say yes or no, right? So basically this was your mf, this was your mf having fm. Now what will happen? Now what will happen? This is your frequency domain is divided by a. That means your frequency axis will be multiplied with a. So here your maximum frequency component will become AFM. There you go. So what is the maximum frequency component? AFM. So for m of at, what is the maximum frequency component? That is AFM, right? Here it is AFM, here it was FM only. Or how you can remember, like if MT is having a fundamental frequency of omega naught, let's just say MT is periodic, it is having a fundamental frequency of omega naught. So what will be the fundamental frequency of m of at? A omega naught only. So similar thing is happening with the maximum frequency component, right? And what would have been the time period? T naught by E. Time period becomes divided by A, and here surely mode should come, right? A could be negative as well, so here mode should come. Mode of AFM. Maximum frequency component will be mode of AFM. That is, say m is minus 2. M is minus 2. So MT was having a maximum frequency component of FM. So m of minus 2 will have the frequency component of 2FM. Basically, minus sign doesn't change the frequency component. Maximum frequency component remains the same if there is a minus sign. So who changes? Only this guy changes. Okay. So there are multiple ways to remember, and you will be able to remember m of at. That means frequency will be divided by a. Frequency domain will be divided by a. That means frequency axis will be multiplied with a. So AFM, maximum frequency component will be AFM. Mode of AFM, you should say. Third one, I guess time shift would be there. No, square. So let's see the H. First, let's see the option H. M of T minus T naught. So you are shifting in time domain. So in frequency, what will happen? E to the power minus j omega T naught m of f. Or here if I am writing in terms of f, so here I should write e to the power j 2 pi f T naught m of f. So frequency spectrum remains as it is, just the amplitude will be multiplied with this particular factor. Are you able to understand this point? Just whatever it was here, that would become a e to the power minus j 2 pi f T naught. So actually your frequencies, actually your magnitude spectrum is not changing, only your phase spectrum is changing. This will change only the phase. So your phase spectrum is changing, but your magnitude spectrum remains the same. So basically m of f remains the same, only in place of a, what you will get? A into e to the power minus j 2 pi f T naught. So what is the maximum frequency component? Maximum frequency component is FM only, right? Directly you can see that shifting in time will not change the maximum frequency component. So m of T minus T naught will have the maximum frequency component of FM. GHG. So what do you think, what will be the answer of this one? Who will change? Time shift will not change, negative sign will not change, only this A is the responsible. M of minus 80 plus B. In M of minus 80 plus B, only who is responsible? Only this A is responsible, right? Or you can find out its Fourier transform. How will you find out its Fourier transform? So from M2 you will first go to M of minus T. That means M of minus F. Then you will go to M of minus 80. It will become M of minus F by A 1 by A. Then you will go to M of minus A T minus B by A. Because I need to make minus 80 plus B. So in place of T, what you have put? In place of T, you have put T minus B by A. So e to the power minus j 2 pi f T naught. So basically, this will have a Fourier transform of 1 by A e to the power minus j 2 pi f B by A. m of minus f by a. So this is the Fourier transform of this particular signal m of minus at plus b. So the thing is, time shifting, no issue. Inverting, no issue. But time scaling, you are multiplying your time domain with a. So yeah, there is an issue. That means your maximum frequency will also be multiplied with a. So here what will be the maximum frequency? F max. That would have been AFM, right? So only this factor is responsible, AFM. Well and good. So the last one, these we have seen. Now let's move to m square t. Let's move to m square t. So m square t can be written as mt multiplication with mt. Say yes or no? And mt multiplication with mt can be written as, in the frequency domain, it can be written as mf convolution with mf. So what you are doing? You are convolving mf with mf. mf with mf. So you are convolving these two. This is minus fm plus fm minus fm plus fm. I need to do the convolution. Then I will get the final answer. Now one thing I know, that I don't know the structure. Like what will be the structure, I don't know. After the convolution, what kind of structure I will get, that I don't know. But one thing I am pretty sure, what will be my limit of convolution. So how do I define the limit of convolution? Lower limit I did. Higher limit I did. So this will be my, and I don't know what kind of structure I will get. So just making it something like this. Whatever the structure you get, you don't know, but surely you know that lower limit will be added, higher limit will be added. So what will be the maximum frequency component? So m square t is having a maximum frequency component of 2fm, right? What do you think, what will be the answer for m cube t? That can be written as mt multiply with mt multiply with mt. This will have a Fourier transform of, multiplication will result in convolution. If we were doing the convolution in omega domain, then amplitude will be multiplied with 1 by 2 pi as well. But we are doing the convolution in f domain. So mf convolution with mf. So these three kind of signal will be convolved. So what will be the lower limit? So all lower limit will be added, minus fm minus fm minus fm. So lower limit will be minus 3fm, right? Minus fm minus fm minus fm. So lower limit will be added. It will become minus 3fm. And then higher limit will be added. It will become 3fm. So this kind of, some kind of structure I would be getting, that I don't know, but I know that my maximum frequency component here, my maximum frequency component will be 3fm, right? So this also I have seen. What does that mean? If there was power k, so what would have been your maximum frequency component? Kfm, right? And if this was the scene, m of kt, then what would have been the maximum frequency component? That was also kfm only. So kind of whenever you see the power, you just put it inside. This is the way to remember, nothing else. Whenever you see the power, put it inside. So kfm. In that manner, you will be able to remember. Okay. F. Differentiation and then integration. So what about differentiation? D by dt of mt. What will be its Fourier transform? J 2 pi f j omega mf. Basically j omega m of omega. So this m omega can be replaced with mf, omega can be replaced with 2 pi f. So basically nothing is happening to the frequency domain, nothing is happening to this Fourier transform. Only amplitude will be multiplied with j2 pi f. Amplitude will be multiplied with j2 pi f. Nothing else is happening, right? Amplitude is multiplied with j2 pi f. That means maximum frequency component remains the same. So what is the maximum frequency component? That is fm only. Maximum frequency component here is fm only. Same goes for running integration. Minus infinity to t m of tau d tau. This can be written as mt convolution with ut, which will be written as mf 1 by j omega plus del f, right? Because what we write down, what is the Fourier transform of ut? 1 by j omega plus pi del omega, right? So here del f by 2. So 2 pi f would come out, so del f by 2. This we would be writing. So what we will be getting, mf by j2 pi f plus m of 0 del f by 2. If you have seen the integration property, then you would know what I am doing. M of f into del of f. So that would be equals to m of 0 into del of f divided by 2. So what is happening here? This is some del of f, some impulse is there which is there at f equals to 0 only. Now m of f remains as it is, just the amplitude is multiplied with 1 by j2 pi f. So m of f is there as it is, nothing else is happening to this m of f. So there is no shifting, nothing, there is no scaling, nothing. That means what is the maximum frequency component? So from here if you see, what is the maximum frequency component? That is Fm only. This maximum frequency component is Fm only. Is that clear to you or not? Okay, so we can write it down everything in conclusion. So what is the maximum frequency component of Mt? That is Fm. So Nyquist rate would be 2Fm. What is the maximum frequency component of M of At? That would be AFM. That means what would be the Nyquist rate? Twice of AFM. M of minus T will have Fm only. What will be the Nyquist rate? 2Fm. M of minus At plus B will have A of Fm. What will be the Nyquist rate? 2AFM. M to the power Kt will have Kfm. What will be the Nyquist rate? 2Kfm. Differentiation, no issue. Integration, no issue. There you go. Okay. We will solve some problems, but I hope the concept is clear to you. Well and good. Let's see this question. M1T is a baseband signal band limited to f of Fm. Mt is a baseband signal band limited to Fm1. Okay, and M2T is baseband signal band limited to Fm2. That means maximum frequency component in Mt is Fm1 and maximum frequency component in M2T is Fm2, where Fm1 is greater than Fm2. You need to find the maximum frequency component of M1T plus M2T, M1T dot M2T and M1T convolution M2T. So let's start. Plus minus here, plus could be there, minus could be there. So can I draw M1T? Surely you can draw M1T. And you can draw M2T as well. So we will just draw the frequency spectrum because our target is to find the maximum frequency component. So band limited to Fm1 and Fm2. Now what I need to do? Fm1 is more than Fm2. You need to add them. Let us say here the amplitude is 5, but here the amplitude is 0 because Fm1 is more. So when you add both of them, what will be the limit? Till what point it will be non-zero? Till Fm1, no? Are you able to understand this point? If I add these two graphs, this point is minus 4, this point is 4, this point is minus 2, this point is minus 2. This is 3, this is 2. So what will happen? Between minus 4 to minus 2, this is non-zero. So 3 would come. Then between minus 2 to plus 2, this is 3, this is 2, then 5 would come. Then again between 2 to 4, this is 3, this is 0, so 3 would come. So 3, 5, 3, in that manner it would come. So minus 4 to 4. So what is the maximum frequency component? Maximum frequency component is Fm1 only. Same goes here. Same thing is here. Just adding or subtracting. Oh, you could have subtracted as well. 3 minus 0 will be 3. 3 minus 2 would be 1. So this point would have become 1. And then again 3 in that manner. So when you add or subtract, the maximum one which is having non-zero value, non-zero plus 0 would be non-zero. And non-zero minus 0 would be again non-zero. So what will be the maximum frequency component here? So just I am writing down here what would be the f max. F max will be fm1, or better what should write? Maximum of fm1 and fm2. So what is the maximum of fm1 and fm2? Because fm1 is more, so maximum of fm1 and fm2 is fm1 only. So this is the answer of first one. Second one, multiplication. Multiplication means convolution, right? m1t multiply with m2t. That means it will be convolved. So when you convolve both of them, lower limit will be added, upper limit will be added. So minus f1 minus fm1 minus fm2, lower limit added, and upper limit added. Right? So this is your m1t dot m2t, or you can write down whatever it is. So basically, what is the maximum frequency component? That is fm1 plus fm2. What is the maximum frequency component? That would be addition of both of them. What do you think here? What will be the maximum frequency component? Convolution. Convolution in frequency domain. Sorry, convolution in time domain. Convolution in time domain will result in multiplication in frequency domain. So you are multiplying both of them. So non-zero multiply with 0 will be 0, but non-zero multiply with non-zero will be non-zero. So when you do the multiplication of both of them, then multiplication would come in between minus fm1 to fm2. Are you able to understand this point? Same example we can take. Minus 4 to 4, 3. Minus 2 to 2, 1. If I need to multiply both of them, so between minus 4 to 2, between minus 4 to minus 2, this is 3, this is 0. So 0 into 3 will be 0 only. Between minus 2 to 2, this is 3, this is 1. So answer will be 3. Now between 2 to 4, this is 3, but this is 0. So the limit will be from minus 2 to 2 only. So the lower limit would come, right? So here what would be the maximum component? That would have been fm2. So here what is the answer? fm2, or what you can say, minimum of fm1 and fm2. Do you need to mug it up? Absolutely not. No need to mug up anything, right? You are not going to mug up. You just need to solve the problems with good amount of patience. Okay, convolution in time domain, multiplication in frequency domain. That means lower limit would come into action. So yes, minimum of fm1, fm2. Multiplication in time domain, convolution in frequency domain. Convolution means lower limit will be added, higher limit will be added. So addition of both of them. Now addition in time domain, that means in the frequency domain as well there will be addition, and in addition non-zero value will come into action. That means higher limit will come into action. Is that clear to you? So this is how we will be solving it. Let's see some questions. This is the question. This is the like highest limit which can be asked. So first xt is given, then ht is given, then yt is given. You need to find the Nyquist state of yt. So first we need to find the Nyquist state, means you need to find the maximum frequency component. So here you need to find the maximum frequency component. So first you see this one, sinc t by 3. So let's talk about sinc function. Sinc t by 3. Sinc t by 3 is there. That means sine pi t by 3 divided by pi t by 3. Now I don't care about the amplitude. I only care about sine 80 by pi t. So I only care about a here. I only care about a. I don't care about here pi t. I don't need to make it pi t. Sine 80 by pi t, whatever the amplitude I get, I know that the limit will go from minus pi by 3 to plus pi by 3. So I only care about a now, sine 80 by pi t. So limit should go from minus a to a. That means this is having a maximum frequency component of pi by 3. But that will be multiplied with 2 because square is there. Square is there, no? So it will be multiplied with 2. Square, m square t was having 2fm. So same thing is happening here. Sinc pi t by 3 square. Square means convolution in frequency domain. Convolution means lower limit will be added, higher limit will be added. So this was having pi by 3 but into 2. What about this one? sinc 2t, that means sinc 2 pi t divided by 2 pi t, then cube. Only thing I care about this one, minus a to a, that means 2 pi is there, but power 3, that means maximum frequency component would be 2 pi into 3, right? And what about this one? Sampling of 3t, that means sin 3t divided by 3t to the power 4. So sin 80 by pi t, this is what I care. I don't care about pi t here, so only I care about a. That means it would be going from minus 3 to 3. Multiply with 4. So 3 into 4. Now look here. Multiplication in time domain. That means convolution in frequency domain. And what is the meaning of convolution? Lower limit will be added, higher limit will be added. So here the higher limit is 2 pi by 3. And here the higher limit is 6 pi. So lower limit will be added, higher limit will be added. So higher limit and higher limit will be added. So 6 pi plus 2 pi by 3. 6 pi plus 2 pi by 3. What I will be getting? 6.66 pi, right? 6.66 pi. 6.66 pi. This is what I am getting from this step. Now, two functions are being added. One is having a maximum frequency component of 6.66 pi. Another one is having a maximum frequency component of 12. This is also in radian. This is also in radian only. So 6.66 pi, which is 6.66 into 3.14. So surely it is greater than 12, right? It is greater than 12. You will be adding both of them. Whenever you add m1t plus m2t, in the frequency domain as well it will be added. So non-zero part is important here. That means this frequency is higher. Basically this particular part will be band limited to 6.66 pi. 6.66 pi. And this part will be band limited to 12. So when you add both of them, then this part would come into action. That means the final addition will be band limited to 6.66 pi only. So here xt is band limited to 6.66 pi. This is the conclusion that we have made. So in the xt, maximum frequency component is 6.66 pi. All good, all fine. What about ht now? What about ht? So sinc 10 by 3t. Sinc 10 pi by 3t. So sin 10 pi by 3t, right? And divided by 10 pi by 3t. Whatever it is, I don't care about that. I only care about a. So it is band limited to 10 pi by 3. And this is band limited to 5 pi, right? Because sinc 5 pi t divided by 5 pi. So this is band limited to 5 pi. Convolution in time domain will result in multiplication in frequency domain. Convolution in time domain will result in multiplication in frequency domain. So 10 pi by 3 and 5 pi, which is larger? 5 pi is larger. But in the multiplication, only then non-zero value will come into action. Basically here it is minus 5 pi to 5 pi and the other one is 10 pi by 3. So if you multiply both of them, in the frequency domain there will be multiplication. So 10 pi by 3 will be throwing non-zero and here also it will be throwing non-zero. After that everything would be 0. So what is the maximum frequency component? That is 10 pi by 3. So maximum frequency component is 10 pi by 3. So in the second one, so here I can write down 10 pi by 3 and here I can write down 5 pi. Convolution in time domain will result in multiplication in frequency domain, multiplication in the frequency domain, that means 10 pi by 3, which is lower because it is 3.33 pi. So your ht is having a maximum frequency component of 10 pi by 3, which can be written as 3.33 pi. Now what is your yt? Yt is xt dot ht. So what will be the maximum frequency component? Multiplication in time domain will result in convolution in frequency domain, and in the convolution lower limit will be added, higher limit will be added. So 6.66 pi plus 3.33 pi. Although we are writing omega max here, right? We are not writing f max, we are writing omega max. These are not f max. So please take care of this thing because these kind of questions will come in numerical answer type. So these are omega max because omega domain analysis we have done, no? So these are the omega max. So multiplication in time domain will result in convolution in frequency domain. So these will be added. So answer would be 10 pi here. So what would be your Nyquist rate? Nyquist rate would be 2 into 10 pi, that would be 20 pi radian per second. But if you need to write down kilohertz, so 10 kilohertz. So this is the answer. Okay, well and good. Do the next one on your own. Mt is given as sampling 3t. Yt is given as m square t cos 2t whole square convolution with m of minus 80 plus 3 whole square. You need to find the Nyquist rate of Yt, and then you need to find the Nyquist interval as well. Okay, Nyquist rate of Yt in radian per second they are asking. So mt is band limited to sampling of 3t. So sin 3t divided by 3t. So mt is band limited to minus a to a, that is 3. So mt is having a maximum frequency component omega max of 3. M square t will have 6. M square t will have 6. What will be the maximum frequency component of cos 2t? 2 only, right? Cos 2t. At 2 you will have something, at minus 2 you will have something. This would be pi, this would also be pi, right? So maximum frequency component is 2. Multiplication in time domain will result in convolution in frequency domain. So that means they will be added. Convolution means high limit will be added, low limit will be added. So they will be added. 6 plus 2, 8. And then you are doing the square. Square means multiplication in time domain. So convolution in frequency domain. So again they will be added only. So 6 plus 2 into 2. 6 plus 2 into 2. So with Yt what is happening? The first part we have solved, that is 6 plus 2 into 2. This is the first part. Then convolution we are doing. So forget about this convolution, but first let's find out the maximum frequency component for this one. What that would be? This is having 3. Mt is having maximum frequency component of 3. So m of minus 80 plus 3 will have a maximum frequency component of 8 into 3, because only this will come into action. So 8 into 3. Now there is a square, that means you need to multiply with 2, right? 8 into 3 multiply with 2. So this is the maximum frequency component of this particular thing. So let's find out this value. This value is 6 plus 2, 8, 16, and this value is 48. Now convolution in time domain will result in multiplication in frequency domain. So what you will book? Minimum 1, right? Convolution in time domain will result in multiplication in frequency domain. So this is band limited between minus 16 to 16, and this is band limited between minus 48 to 48. So what is the minimum one? This is the minimum one, right? So what is your omega max? 16. So your Yt is band limited to 16. So maximum frequency is 16 here. I cannot say band limited. It could be band limited between something like it could be band pass signal. It could be baseband signal. I don't care whether it is a band pass. It is a baseband. If you need to find out the Nyquist rate, then only thing you care about, that is the maximum frequency. So it might happen that this signal is band pass. It's not necessary that it will be baseband. This was a baseband signal, right? Sin 80 by pi t. It would be rectangular. So this is a baseband signal. No issue about that. Now it could be band pass as well. I don't care about that. Only thing I care is what is the maximum frequency component. So here the maximum frequency component is came out to be 16. So what will be our Nyquist rate? Our Nyquist rate would be 16 into 2. That would be 32 radian per second. And what would be our Nyquist interval? So Nyquist interval is always defined in second. Okay. So first you need to convert it to hertz. So 16 by pi hertz. Now what will be your Nyquist interval? That would be 1 by 16 pi. You cannot directly write down 1 by 32. That would be wrong. So answer would be pi by 16 second. So first convert it to hertz, and hertz has been converted. So 1 by 16 pi. So hertz has been converted. So pi by 16 is the answer. So this is the Nyquist interval in the seconds, and this is your Nyquist rate. Okay, so it was an easy lecture only. In those questions, everything has been covered as well. That first sampling 3t, it was having 3, then m square t 6, cos 2t 2, multiplication means convolution in time domain, so 6 plus 2 8, then square 8 into 2 16, then convolution sign is there, but let's drop it. Then here I got to know that 8 into 3 24 into 2 48. Now what is the meaning of a convolution? Convolution means multiplication in frequency domain. So minimum I need to pick, that would be 16. So that is my omega max. So what would be my Nyquist rate? That would be twice of that. So 32 radian per second, and then divided by 2 pi, that would be in hertz. So that would be 16 by pi hertz. And what will be your Nyquist interval? That will be 1 by 16 pi. So pi by 16 second, that would be the Nyquist interval. Well and good. So yeah, that's the end of this lecture. Only I wanted to talk about Nyquist rate, and also I wanted to talk about your baseband and bandpass signal. So that we have talked, and in the previous part of this video we have covered about filters. So I hope you found it helpful. In the next video will be our last video on this chapter, that is Fourier transform. So on this chapter, the last video will be sampling. So we are going to study about sampling now. Thank you very much. Hi everyone. So now we are going to start our final topic of this chapter, that is sampling. So a very important topic, like most important topic from complete signal system, that is sampling. And you can expect a very good question from sampling this year as well. Last year it was there, a year before it was there, it is always coming. So this year as well you can expect a very good question from sampling. Okay. So we will start that, but before that let's see some prerequisites. So this is the xt waveform given. What is this? This is known as impulse train. Can you write down the expression of xt? Yes. What will be the expression of xt? N goes from minus infinity to infinity, delta of t minus nts. Right? Because at every ts you can see that there is a impulse of area 1. What you need to find? You need to find x of omega and x of f. So I told you one thing, for a periodic signal, if you need to find x of omega, if you need to find the frequency spectrum, then first thing you need to find out C of n. So what you will find out? C of n. And for this particular signal, we remember C of n very easily. That is A by Ts. So here the area is 1, so it would be 1 by Ts. So Cn is 1 by Ts. So at every n, it would be 1 by Ts only. This we already remember. For an impulse train, always the Cn is A by T naught, where A is the area of the impulse, that is 1, and Ts is the, T naught is the time period of the impulse train, which is Ts. So it would be 1 by Ts, 1 by Ts, 1 by Ts, and so on. And it will be there for every n. That means all the frequencies will be present. All the frequencies will be present. Omega naught, 2 omega naught, 3 omega naught, everything will be present. So from Cn, if you need to go to x of omega, how will you go? These sequences will be converted to impulses. This n will be converted to omega, and your amplitude will be multiplied with 2 pi. So this is how we go to x of omega, right? I hope you remember this thing. Because for a periodic signal, how do you give the Fourier transform? This is how we give the Fourier transform. Right? Here omega naught is omega s. So this is how we give it. Or I told you one method. The method is all the sequences will be converted to impulses. If you have seen the diagram of Cn, then all the sequences will be converted to impulses. And the n axis will be converted to omega. Here you are having 1, 2, 3, that means you are having omega naught, 2 omega naught, 3 omega naught. So these frequencies are omega naught, 2 omega naught, 3 omega naught, and so on. Similarly here minus omega naught, minus 2 omega naught, and so on. What will be the area of this impulse? Whatever the area was there, 1 by Ts into 2 pi. 1 by Ts, whatever it was there, but into 2 pi. So 2 pi by Ts, 2 pi by Ts, 2 pi by Ts. 2 pi by Ts, 2 pi by Ts, 2 pi by Ts. So x of omega could be written as 1 by Ts I can write down as Fs, and in place of omega naught I should have written omega s. because here the fundamental frequency is omega s, right? Basically, what is your 2 pi? What is your omega s? Omega s is 2 pi by Ts only. And what is your Ts? Ts is 1 by Fs. So what we are getting? 2 pi by Ts, and then there is a impulse train, omega del of omega minus n omega s. Say yes or no? So this is your x of omega. And how do we write down x of f? So when you draw x of f, all the impulses here will be divided by 2 pi, or from here as well you can write down x of f. What you will do, all the sequences will be converted to impulses with the area being same, 1 by Ts only, area being 1 by Ts only, area being 1 by Ts only, and this axis of n will be replaced with omega. So this is how we make x of f, right? So when we are studying sampling, we will do all the analysis in terms of f only. Look, we studied the whole chapter in terms of omega, right? X of omega. But now when we are studying sampling, we will do the analysis in terms of f, because it will be easier for us. So all the analysis will be done in terms of f only. So in terms of f, what you will remember, that if your xt is given as n goes from minus infinity to infinity, Cn e to the power j n omega naught t. Basically, xt is a periodic signal. Then your x of f is given as n goes from minus infinity to infinity. Everything will be converted to impulses, but this Cn will not be multiplied with 2 pi. Cn will be multiplied with 2 pi only if you are writing in terms of omega. But if you are writing in terms of f, then Cn will not be multiplied with 2 pi. This will remain as it is. And everywhere you will get the impulses. At all the discrete frequency, you will get the impulses f0, 2, f0, 3, f0, minus f0, minus 2, f0, minus 3, f0. So this is how you write down your x of f. This should be remembered. Okay. So what was your Cn? 1 by Ts. Cn was 1 by Ts. So this remains, the area of impulse remains 1 by Ts only. And you are having the impulses everywhere. Say yes or no. So this is x of f. Why we are studying so? Why we are doing all this analysis? Because it will be used somewhere. Okay, so this should be remembered anyhow. This should be remembered anyhow. Along with that, if xt is an impulse train, then x of f would be 1 by Ts can be replaced with fs, right? 1 by Ts can be replaced with fs. So x of f would be, all the impulses are having the area of fs, and impulses are existing at every frequency. And in here I should have written fs, not f naught. So directly if you see the impulse train, at least this diagram should be clicking in your mind, that if I see that in my time domain I am getting an impulse train, then in the frequency domain as well you will get an impulse train, okay, with each area being 1 by Ts. Okay, time domain impulse train. So in the frequency domain as well you are getting the impulse train with each area being 1 by Ts, and the impulses will be existing at every discrete frequency, that is fs, 2fs, 3fs, minus fs, minus 2fs. Say yes or no, it should click to you. So directly from here to here you should be able to come, and this expression should be there in your mind very easily. Okay, because we will be using it again and again, so eventually it will stuck in your mind. Now there is something called aliasing. Okay, there is something called aliasing. What is the meaning of this aliasing? So you need to add these two frequency spectrum. There is a signal m1t having the frequency spectrum of m1f. There is a signal m2t having the frequency spectrum of m2f. You need to add both of those, or add both of these frequency spectrum. I am taking different condition. I am taking condition A where my FC is 2 kilohertz, and I will take condition B where my FC would be 4 kilohertz. Okay, so if your FC is 2 kilohertz, you need to add both of them. So M1F is non-zero between 0 to 3, and this is non-zero between 2 to 8. So what will happen? Between 0 to 2, this is non-zero but this is 0. So what will happen? Let's draw the addition. So between 0 to 2, this is non-zero, but this is 0. After that, what is happening? After that, 2 to 3, between 2 to 3, this is non-zero and this is also non-zero. So basically, this graph is rising something like this. The graph is rising something like this. So this is 2k and this is 8k. So between 2k to 3k, both are non-zero. That means both will be added. Both will be added. Basically, here it is, let's just say it is 4. This is 0. So 4 plus 0 will give you 4. What about this one? Let's just say at this point at 3k, this is 4 and this is 0. So 4 plus 0 will give you again 4. At this point, both are 2, 2. So 2 plus 2, again it will give you 4. So in between 2k to 3k, in between 2k to 3k, completely it will be 4. After that, what will happen? This is non-zero, this thing is non-zero, and this is 0, right? So I am just adding it up. So this is how I will add it up. So this kind of pattern we are getting, and the similar will be repeated this side as well. Basically, here there is an overlap, right? There is an overlap in the frequency spectrum of M1F to M2F. There is an overlap. So if there is overlap, if this kind of condition is there, so this would be 8k, and here you can write down the same thing. So if this kind of condition is there, if there is an overlap, this is known as aliasing. That means yes, there is aliasing. Why this is known as aliasing? Look, if I give you this particular frequency spectrum M1F plus M2F, and this I am calling as some alpha f. So if I give you alpha f and I ask you, can you get M1F out of it? What I am saying, I give you alpha f and now I ask you, can you get M1F out of it using any filter? You will say, sir, I will use this filter. I will use this kind of filter. So will you get M1F? No. M1F is something like this. Between 0 to 3k, it is non-zero between 0 to 3k, something like this. But if you use this kind of filter, you are not getting M1F. Because M1F's frequency spectrum and N2F's frequency spectrum have been added. They were overlapping, they have been added. So now using the filter, you cannot get M1F. So this is known as aliasing effect. So here aliasing is occurring because there is a common area. If there is a common area, that means both are being overlapped and both are being added. Since both are added, so now I cannot get M1F out of it. So this is known as aliasing. But if you take your FC equals to 4 kilohertz, if you take FC equals to 4 kilohertz, so this point is 4 kilohertz. So this is non-zero between 0 to 3 and this is non-zero between 4 to 10. So now there will not be any aliasing effect, right? Because both will not overlap. So if two frequency spectrums are overlapping, this is known as aliasing effect. Okay, if two frequency spectrums are overlapping. So if you add both of them now, so between 0 to 3 it is non-zero, then it is non-zero between 4 to 10. Zero, 3k, 4k, 10k, minus 3k, minus 4k, minus 10k. M1F plus M2F is equals to, this I am calling as alpha 1F, this I am calling as alpha 2F. Now if I give you alpha 2F and I ask you, can you get M1F out of it? You will say, yes sir, I can use this kind of filter. If I use this kind of filter, only this I will get, rest all will be multiplied with 0, rest all will be multiplied with 0. So using this kind of low pass filter, from sinc function we can make this kind of rectangular low pass filter. If we use this low pass filter, that means yes sir, I can get M1F out of it. And using a band pass filter, something like this, you can get M2F as well. So since there is no aliasing, that means no frequency spectrum is being overlapped. So you can get M1F and M2F using an appropriate filter. But here you use any kind of filter, using any kind of filter, you cannot get M1F and M2F separately. So this is known as there is no aliasing. So all these things we will be using somewhere, that's why we are studying it here. Okay. So what we have studied, first we studied the frequency spectrum of a pulse train. Okay, frequency spectrum of a pulse train, sorry, impulse train, not pulse train, frequency spectrum of a impulse train that we have studied, which will be impulse train only with the area of impulse being Fs, with area of impulse being Fs, and impulses will be existing at every discrete frequency Fs, 2Fs, 3Fs, 4Fs, and in the negative side minus Fs, minus 2Fs. And then we studied about aliasing, right? Let's move to sampling now. So what is the meaning of sampling? In lecture 1 we have studied the meaning of sampling. In lecture 1 of signals and system, what did I tell you there? That this is our continuous time signal. This is our continuous time and continuous amplitude signal. Now what I will do, I will give this signal to a system where the switch is being closed after every ts second. After every ts second, let's take the value of ts equals to 2. So after every 2 seconds, the switch is being closed. So first, let's just say I close the switch at t equals to 0 second. So if I close the switch at t equals to 0 second, and here I am connecting a capacitor, let's just say I connect a capacitor. So whatever the value is there at the input, the same value is being reflected here at the output. So I close the switch at t equals to 0. What was the value here? That was this m of 0. This value was m of 0, right? Now after next ts second, after 2 seconds, that means at t equals to 2 seconds, I will again close the switch. I will get some value. That value is m of 2, or you can write down m of ts. Then again after next ts second, that means at 4 seconds, I will again close the switch. I will get this value. That you can call as m value at 4 seconds, or you can call it m value at 2 ts second. In that manner, you will keep on collecting the value, right? Now you can collect the value in the negative side as well. You are closing the switch at 0 second, 2 second, 4 second. You could have closed the switch at minus 2 second as well. You could have closed the switch at minus 2 second as well. You could have closed the switch at minus 4 second as well. So what all values you will be getting? Some value like this and some value like this, right? These values are, so here this value I was getting, and here this value I was getting. Here I could have got this value. Here I could have got this value. So this switch was closed at 0, this was closed at ts, this could have been a bit nearer. This was closed at 2 ts, minus ts, minus 2 ts. So after every 2 seconds, I am closing the switch, right? So this kind of discrete values I am getting. Now using this discrete value, making a possible approximation, I can approximate that my continuous time signal would have been somewhat like this. My continuous time signal would have been somewhat like this. A kind of approximation I can take, right? If I join these dots, then kind of approximation I can take that my continuous time signal would have been somewhat like this. Say yes or no. So why do we actually use the sampling? Look, this is your continuous time signal. So here at every second there is some information. At 0 second there is some information. At 0.01 second there is some information. At 0.02 second there is some information. So at every second there is some information. And storing this much information will be a very hectic task. Like it will take a lot of storage. You cannot store all the values. Okay, you can store the value, but it will take a lot of more hardware. So what you thought, that I will store only some specific values. I will store the values at 0 second, then at 2nd second, 4th second, 6th second, 8th second, and same goes minus 2 second, minus 4 second, minus 6 second. So this is what you thought. And using these values, I can approximate that this is how my continuous time signal would have been there. And now in this one you have to store infinite values. But here you need to store 1, 2, 3, 4, 5, only 5 values. So it will take very lesser hardware. So in your design, if you need that I need to store only some values only, then you can use the process of sampling, right? When you make a video, look, let me give you a practical example. Let's just say I am moving my hand. Okay, I am moving my hand. Now you are clicking my picture. This is my hand. You click one picture. Then my hand goes like this, you click another picture, my hand goes like this, you click another picture, my hand goes like this, you are clicking continuously, you are clicking the picture. Okay, now you put all those picture in a slideshow. In a slideshow, you put all those pictures. Like after one picture, another picture is coming. After another picture is coming. Then another picture is coming. What I was doing, I was moving my hand, and you clicked the pictures. You took the pictures. Now you are putting these pictures in a slideshow. That means after one another, all the pictures would be coming. So that slideshow will look like a video, right? In the video, I will be moving my hand like this. Now let's just say some guy has taken 10 photos and some guy has taken 50 photos. So whose video will look better? This guy's video will look better, right? Because what this guy did, my hand was here, he clicked the picture. Then my hand was here, he clicked the picture. Then my hand was here, he clicked the picture. Then my hand was here, he clicked the picture. But what this guy did, my hand was here, he clicked the picture. It was here, again click the picture, 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 and again click the picture. So he collected more number of samples. More number of samples. Right? But he collected less number of samples. That means his sampling time was less. His sampling time was less. That means he was clicking the picture in lesser time. Let's just say he was clicking the picture after every 1 second. So he would have clicked picture after every 5 seconds. Say yes or no? Both were having 50 seconds, right? In 50 seconds, he clicked 50 pictures. That means he clicked every picture after 1 second. So he was collecting the sample after every 1 second. But he was collecting the sample after every 5 seconds. So whose picture was better? His picture was better, right? So you would want this time TS to be minimum. If you want to come near to this waveform, basically if you want to approximate this particular waveform, looking at the samples, looking at these samples, if you want to approximate your signal in the continuous time, looking at these samples, that means this TS time window should be very lesser. This TS time window should be less, because if TS time window is very large, let's just say some guy collected the sample here and the second sample he is collecting here. What was happening? First sample he collected here and the second sample he collected here. So can you let me know how the waveform would have gone in between? No. But what some guy is doing, he is collecting the sample here as well, then here as well, then here as well, here as well. So now he can predict that this is how the waveform would have been going. Are you able to understand this point? So this TS time window should be as less as possible. And this time window is known as sampling time period. Okay. What is this TS? Sampling time period. So this TS should be as minimum as possible. Although here we write down N. Okay. Here we write down N, but let's keep it T. So this explanation I have already given. Why do we write down N here? N means first sample. So this is your first sample. This is your 0th sample. This is your -1 sample. This is your -2 sample. So usually when we show a discrete time signal, what do we show? X of N versus N. Here we write down N equals to 1, 2, 3, -1. What is the meaning of that? This is the first sample. A discrete time signal would have always come from a continuous time signal. It would have come from a continuous time signal only. So this is the first sample, second sample, third sample, -1 sample, -2 sample. So this concept have been already taught in the first lecture itself, right? That how from a continuous time we go to a discrete time signal. So this has been already taught, right? So first sample, second sample, third sample. That's why we write down N here. But here I am writing down the time window. If I write down 1 here, what does that mean? TS second. If I write down 2 here, that means 2 TS second. If I write down -2 here, -2 TS second, right? So what is our target? The target is TS should be as minimum as possible. Okay. But this guy clicked 50 picture and this guy clicked 10 picture. Who would need more hardware? Who would need more space in his camera? The one who is having 50 pictures, right? He is having 10 pictures only. So he would need 1 GB. But he is having 50 pictures. So he would need 5 GB storage. So who needs more storage? The one who is having more samples. Some guy would have clicked 200 pictures. So he would need 20 GB. So he needs more storage. So more the sample, more the storage would be required. More the samples, more the storage would be required. So there should be an equilibrium. Like if you click too less picture, then you will not be able to predict the waveform. If you click too many pictures, then you would require larger space. So somewhere in between, if you click 50 pictures, then it would be good for you. That space is also in control and you will be able to predict the waveform as well. But in time domain, We will not do all these things. We will do all these things in frequency domain. So that we will see. But as of now, we have understood that there is something called sampling time period. So what will be the definition of sampling time period? Sampling time period will be time taken to capture one sample. So here you are taking TS time to capture one sample. In every TS second, you are capturing one sample. So time taken to capture one sample is known as sampling time period. And what will be your sampling frequency? That would be 1 by TS, or you can say number of samples per second. So in 1 second, how many samples are you collecting? That is known as sampling frequency, a very, very important term. Okay, sampling time period and sampling frequency both are very important. Mostly we will do the analysis in frequency domain. That's why sampling frequency will be highly used. So what do you mean by sampling frequency? Sampling frequency means number of samples per second. In 1 second, how many samples are you collecting? So by this example, we will be able to understand it. So in a sampling process, we are collecting 100 samples in 5 seconds. 100 samples in 5 seconds. So in 1 second, how many samples have been collected? 20 samples. Right? So what will be your sampling frequency? That would be 20 samples per second. 20 samples per second. So this is your sampling frequency. And what about sampling time? Sampling time period? So what do you mean by sampling time period? To collect one sample, how much time are you taking? So 100 samples are collected in 5 seconds. So in 5 seconds, you are collecting 100 samples. Or you can say 100 samples are being collected in 5 seconds. So one sample is being collected in 5 by 100. That means 1 by 20 seconds. So what will be your TS? That would be 5 by 100. So 1 by 20 seconds. So in 1 by 20 second, you are collecting one sample. Okay, so this is the basic meaning. Let's see the sampling process now. So what we will be doing? Look, this was the meaning of sampling. This was the meaning of sampling. But what we will be actually doing in the sampling process, that we need to see. So we will be having a message signal empty. This needs to be sampled. Okay, this needs to be sampled. Look, sampling is not our target. Our target is that we should take this message signal empty. So from the transmitter side, we need to send this message signal to the receiver side. This is our target. Our target is that we should get this message signal here. Now what was the challenge? The challenge was the empty is a continuous time signal, and continuous time signal means it will require more storage. So now from here to here, the signal needs to be sent. So that means it will be a very tough process. It will be like there will be a lot of noise, and if you store this much information, then noise will also come into action. So your signal may be distorted. Okay, your signal may be distorted. There would be some noise. All these things would be coming into action. So what you thought that I need to store it, so I will store it in the lesser amount. In the lesser storage, I will store it. And for that, what you are doing? You are doing the sampling process. So first you decided to do the sampling, then you will send the sample signal. Okay. First, what you thought that I will send the. First, you thought that I will send this empty signal, but sending this empty signal will take a lot of storage. So what you thought? First, I will sample it, then I will send this sample signal here. I will send this sample signal here, and now from this sample signal, I will try to get empty out of it. Are you able to understand this point? So what is our target? Are you able to understand? From empty, we will get MST, and this MST we will send to the receiver side, and from here we will try to get our empty back. Our target was to send empty from transmitter to receiver, but first we sampled it, sampled came here, and now we will try to get empty out of it. So how we are sampling it? How we are sampling this empty signal? So for that, what we are using? We are using a multiplier. What we are using? You are using a multiplier. So this is a multiplier. So your empty signal is being multiplied with some signal CT. This CT signal is known as sampling signal, and from there MST. What is this? Sampled signal. So you are getting your sampled signal as empty.ct. So what you are doing? You are multiplying your empty signal with a particular signal. What is this CT signal? That we need to see. What is our empty signal? This is our message signal, which was this one. Now it should be multiplied in the time domain. It should be multiplied with the particular signal. When you do the multiplication, you get your sampled signal. So what do you think? What should be CT? So empty should be multiplied with what? What do you think? Your CT would be an impulse train. because if you multiply your empty signal with an impulse train, what will happen? Impulse train is having a time period of Ts. So after every Ts second, these impulses will be multiplied with empty. So what you will get here? One impulse. What one impulse? What will be the area of this impulse? 1 into whatever the value was here, that was m0. So the area will be m0. Then after, now between 0 to Ts, this is 0. 0 multiply anything, 0 only. Now at Ts what will happen? This is 1. 1 multiply with mts, value of mt at Ts second. So 1 will be multiplied with mts. So again you will get an impulse with the area of mts. Then at 2 Ts second, what will happen? Again the area of this impulse is 1. It will be multiplied with m 2 Ts. It will be multiplied with m 2 Ts. So this is 0, this is Ts, 2 Ts. Basically you will get an impulse train only, but the area of these impulse trains will be monitored by the value of mt at those impulses. What I am saying, when you multiply a continuous time signal with an impulse train, at the output you will get an impulse train only. When you multiply a continuous time signal with an impulse train, at the output you get an impulse train only, but the area of these impulses will be monitored by the value of message signal as these time instants. At Ts time instant, 2 Ts time instant, 0 second, minus Ts, minus 2 Ts. Again let me repeat the statement. When you multiply a continuous time signal with an impulse train, the multiplication will result in impulse train only, but the area of these impulse train will be monitored by the value of message signal as those at those time instants, at the time instants of sampling. So you are sampling at after every Ts second, that means you are sampling at 0 second, Ts second, 2 Ts second, 3 Ts second, 4 Ts second. Right. So this is the value, like basically these are the values, whatever the value is there, you can make it. Yeah, so this would be m of minus 2 Ts and this would be m of minus Ts. So kind of from here you can predict that your waveform would have gone something like this. So this we have studied in time domain. Let's do the same analysis in frequency domain and let's see what is happening. Okay. So this is our MST. This is our MST. So now exact ditto the same analysis we are going to do in the frequency domain, and let's see what will be happening. So what will be the Fourier transform of MT? That will be MF. Fourier transform of MT would be MF. Fourier transform of MT is MF. And what will be the Fourier transform of CT? That I am calling as CF. But you know what will be the expression of CS? Surely you know it, right? So understanding the transmitter side of the sampling process in the frequency domain. So what I am assuming that my MT is a baseband signal band limited to FM. So you know the meaning of baseband signal. It is band limited to FM. That means its maximum frequency content is FM only. After that everything is 0. Before this everything is 0. So its maximum frequency content is FM. So this is our MT, which is a baseband signal. Now it will be multiplied with CT. So this is the frequency spectrum of MT. Okay, this is the frequency spectrum, or you can say Fourier transform of MT, which is MF. Now MT into CT you need to do. What you need to do? MT into CT. So in frequency domain what will happen? MF convolution with CF. I could have written M of omega convolution with C of omega as well, but I needed to divide by 1 by 2 pi. But all the analysis we will do in F domain only. So multiplication in time domain will result in convolution in frequency domain. So MT dot CF what will be the Fourier transform of empty dot CT? Empty dot CT. What will be the Fourier transform of that? MF convolution with CF, right? So MF I already know. What is my CF? My CF would be Fs, n goes from minus infinity to infinity, del of F minus NFS. Say yes or no. Right? Now I need to convolve this with this, right? So what is my CF? Can you draw the diagram of CF? You can surely draw the diagram of CF. Impulse train in frequency domain is also impulse train only. The impulses will be existing at every discrete frequency, which is Fs, 2Fs, 3Fs, 0 as well, minus Fs and minus 2Fs. The area being 1 by Ts, or you can say area being Fs only. Area being Fs only. So this is your impulse train. This is the Fourier transform, or you can say frequency spectrum of your impulse train. Now what is our sample signal? Our sample signal is empty dot CT. So what will be the Fourier transform or frequency spectrum of our sampled signal? That would be empty, that would be MF convolution with C of F. So I can write it down, MF convolution with, what is my C of F? Fs, n goes from minus infinity to infinity, del of F minus Fs, right? Now Fs, what is Fs? Fs is a constant value. Fs is a constant value. So Fs can come outward. So Fs is coming outward. Now M of F is being convolved with, now here put the value of n. So first put the value of n equals to 0. So del f you will get. Then put the value of n equals to 1. So del of F minus Fs you are getting. Then put the value of n equals to 2. So what you are getting? 2. In the same manner you will keep on putting it, but the negative value also you can put. So put the value of n as negative. So if you put n equals to minus 1, what you will be getting? Put n equals to minus 2, what you will be getting, and so on, right? So Fs is outward, Fs is outward. MF convolution with del f, what you will be getting? MF only, plus MF convolution with del f minus Fs. So whatever the shift that is there in your del, the same shift will be given to your M. This is the convolution property, right? Whatever the shift that is there here, the same shift will be given to M. I hope you remember this property, xt convolution with ht minus t naught. So what you will be getting? Let's just say this was yt initially, so yt minus t naught. Basically xt convolution with del t, what is that? Xt only. So xt convolution with delta t minus t naught, what that would be? X, this shift will be given to x. So this is the very basic convolution property which we have already studied. M of f minus 2fs dot 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 m of f plus 2f plus fs. Just we are doing the convolution. So whatever the shift is there, the same shift is given to m of f plus 2fs and so on. You know the frequency spectrum of MF. Can you draw the frequency spectrum of M of f minus Fs? If you know the frequency spectrum of MF, can you draw the frequency spectrum of MF minus Fs? Yes. The center will be moved to Fs and then same diagram will be coming. Then center will be moved to 2Fs, the same diagram would be coming. Center will be moved to minus Fs, the same diagram would be coming. Center will be moved to minus 2Fs, the same diagram would be coming. So this is our MSF. So let's draw the frequency spectrum of MSF. So what will be happening here? Fs will be multiplied with MF. What is our MF? This is our MF. Let's just say this point was A, or let's just call this point as 1 only. So this is our MS. This is our MF. So MF will come as it is, but multiply with Fs. So MF will come as it is, but multiply with Fs. It was non-zero between minus Fm to Fm. Now what will happen? It will be added. It will be added with Fs Mf minus Fs. That means center will be moved to Fs. Center will be moved to Fs, and the same diagram would be coming. So here your center which was at 0, that will be moved to Fs. The center will be moved to Fs. This center has moved to Fs. So Fs, this was at 0, so 0 minus Fm. So Fs minus Fm. This was at 0, so 0 plus Fm. So this would be Fs plus Fm. Now what will happen? The center will be moved to 2Fs. The center will be moved to 2Fs. The center will be moved to 2Fs. Now this point would be 2Fs minus Fm, and this point would be 2Fs plus Fm, right? The center is 2Fs. So 2Fs minus Fm. This was at 0, right? So 0 minus Fm, 0 plus Fm. So 2Fs minus Fm, 2Fs plus Fm, right? The similar thing will be happening to the negative side. So you can draw this kind of diagram on your own, right? Center is moved to minus Fs. So minus Fs plus Fm, minus Fs plus Fm, and then minus Fs minus Fm. So from here Fm backward, so minus 2Fs minus Fm. So from here from here Fm ahead, so minus 2Fs plus Fm, right? So this kind of diagram you are getting. So what really happened? There was this MF signal. You, in the time domain, you multiplied your MT with CT. In the time domain, you multiply your message signal with the impulse train. So in the frequency domain, what really happened? This was also impulse train only. In the frequency domain, it got convolved. So once you did the convolution, what really happened? A lot of MF have been created. This is also one MF only. This is also MF only, just shifted. 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 But the amplitude has also increased to Fs. Initially the amplitude was 1, but now the amplitude has increased to Fs. Now one thing we need to take care, what is that? That I need to avoid aliasing, right? I need to avoid aliasing. What I am saying, what if I added all these waveform, right? I added all these waveform. I made them separately. This is separate, this is separate, this is separate. But what could have happened? This condition could also have happened, right? They could have also been added like this. When you were adding these two, what really happened? There was a common area, there was an overlapping area. So here as well there could be overlapping area, no? Here as well there could be overlapping area. To avoid that overlapping area, what should be the condition? That this Fs minus Fm should be greater than Fm, should be greater than or equals to Fm. At the equal also it will work. This is just the boundary. So this is just the boundary. So Fs minus Fm should be greater than or equals to Fm. So from here what you are getting? Fs should be greater than or equals to 2Fm. So this is the condition to avoid aliasing. The same thing you can see here as well. That 2Fs minus Fm should be greater than Fs plus Fm, right? 2Fs minus Fm should be greater than 2Fs plus Fm greater than or equals to. So from here also what you are getting? Fs should be greater than or equals to 2Fm. You can see it anywhere. Let's see it here. Minus Fs minus Fm. Minus Fs minus Fm should be greater than minus 2Fs plus Fm. Minus 2Fs plus Fm should be greater than or equals to. So what, this 2Fs will go here. So Fs is greater than 2Fm. Again the same condition we are getting. So anywhere you apply. So what did you get to know? That your minimum sampling frequency should be 2Fm. To avoid aliasing. To avoid aliasing, your minimum sampling frequency should be 2Fm. To avoid aliasing. minimum sampling frequency should be twice of the maximum frequency of message signal. This is known as sampling theorem. Okay, this is your sampling theorem. So fs should be greater than or equals to 2fm. So minimum sampling frequency should be twice of the maximum frequency of the message signal. Right? From here you can get fs minimum. At least minimum you need 2fm, which is luckily equals to Nyquist rate. Luckily it is equals to Nyquist rate. In the last lecture we studied about Nyquist rate. So what did I tell you? What is Nyquist rate? Which is equals, Nyquist rate is equals to 2 into maximum frequency of the signal. So 2 into fm. Luckily it is equals to Nyquist rate. But Nyquist rate and sampling frequency both have no relation at all. What I am saying, there is no relation between Nyquist rate and sampling frequency. No relation at all. Someone will say that sir, minimum sampling frequency is minimum sampling frequency is called as Nyquist rate. But luckily it is coming out to be equal. But when Nyquist rate was defined, sampling was not into the action at all. Okay, Nyquist, that's why we studied Nyquist rate before sampling, so that people should not be relating it. There is no relation between Nyquist rate and sampling. If someone is saying that a signal is sampled over a Nyquist rate, what does that mean? That sampling frequency is 2fm. What I am saying, a signal is sampled over a Nyquist rate. Signal is sampled over a Nyquist rate, that means sampling frequency is equal to Nyquist rate. And what is the meaning of Nyquist rate? Twice of fmax. That's it. This is the meaning. This kind of statement could be there, that a signal is sampled over a Nyquist rate. And you know what is the meaning of Nyquist rate, you know what is the meaning of sampling frequency, so you just need to equate it. But there is no relation. There is no relation between Nyquist rate and sampling frequency. Okay. So now our first job is done. What we have seen? We have seen this particular side. We have generated MST, or we can say we have generated MSF. Now from this particular MSF, you again need to get out your MT, or basically from this MSF you need your MF. From this MSF you need your MF. So what do you think what you will do? You will use a filter. I can use a low pass filter here with a gain of 1 by fs. So what will happen? This 1 by fs will be multiplied with fs. So what will be the gain? The total gain will be 1, and only this part will be coming out. And what is this part? This part is MF only. And now for MF, I will take the inverse Fourier transform and I will get my MT. Are you able to understand this point? So now what is our target? We are having MSF. So from this MSF, I need to get MF. So at the receiver side, I am having MST. I need my output which is equals to YT. I need this output as MT. So I will pass it to some system, and any LTI system, I will pass it to some LTI system, and any LTI system can be characterized as filter. So what I will call it? In the frequency domain, I will call it a filter. So I will pass it through a filter whose frequency response or frequency spectrum is given by h of f. So the filter is having a frequency spectrum of hf. So what will be your output? That would be your y of f should be equals to mf. This is my target. My target is to get mf at the output. So what I will do? I will use a filter like this, which is having a cutoff frequency of minus fm to fm. I am making sure that my fs is greater than 2fm. The first thing to make sure that fs should be greater than 2fm. Why is that so? Because if fs is less than 2fm, then what will happen? There will be aliasing. So here only there will be some aliasing. So this kind of pattern we will be getting. No matter now what kind of filter you use, you will not be able to get MF out of it. So now I can get MF out of it, but making sure that my Fs should be greater than 2Fm. You will get this diagram only when your Fs is greater than or equal to 2Fm. So you have got this diagram now. Now this is the filter you are using, which is having the cutoff frequency of Fm. That means what it will pass, but here the amplitude is Fs, amplitude is Fs, amplitude is Fs, and the same thing is being repeated as well. Same thing is being repeated as well. Now this is the low pass filter you are using with the pass band gain. This is known as pass band gain. Okay, 1 by Fs is the pass band gain. Pass band gain of the filter is 1 by Fs. Why I am using 1 by Fs? Because now both of them will be multiplied. Basically, what will be your Yt? Yt will be MST convolution with HT. So what will be your YF? YF will be MSF dot HF, right? So here both of these spectrums will be multiplied. So 1 by Fs will be multiplied with Fs. So what I will be getting? 1. And now after Fm everything is 0. So all these will be multiplied with 0. So everything will be gone, only this part will be coming out. So this will be your output. This will be your output from minus Fm to Fm, and here this will be 1. So this is your Y of F. Rest everything would be 0. And this Y of F is actually equals to MF only, right? And now from here you take the inverse Fourier transform. Basically you are getting MT only. And you know how to design this filter, right? How to design this kind of filter. From a sinc function you can design this kind of filter, right? So this will have a, if I write down my HT, can you write down the HT for this? Surely I can write down sin 80 by pi t, sin 80 by pi t with the amplitude of Fs. So there you go. This time domain signal will give you this kind of frequency response. Absolutely not. Here should be written 2 pi Fm. This is A, no? This is A. In the omega domain, this is your A. So I hope you know that sinc function or sampling function will give you the frequency response of rectangular function. This you already know, right? So sin 80 by pi t. Sin 80 by pi t, what is the value of A here? Minus 2 pi Fm2 plus 2 pi Fm. Then that is in the omega domain. In the frequency domain it will be minus Fm2 plus Fm. So if you design this kind of filter, then your job is done, right? So this is very easy to design. This we are already having. So time domain analysis also we have done. Although we will see these kind of questions and it will be more clear to you. But it's not necessary that you are having this filter only. What if I am having this kind of filter? So what I am making sure? I am making sure that this filter is getting killed. Like basically its response is 0 before Fs minus Fm at least. Are you able to understand this point? Let's just say this Fm is 2 kHz and this Fs minus Fm is 4 kHz. So till this point it is providing a gain of 1. Till 2 kHz it is providing a gain of 1, not gain of 1, sorry. If this is Fs, this will also be Fs, this will also be Fs, and all these are being repeated. So this is providing a gain of 1 by Fs. So till this point, till Fm, it is providing a gain of 1 by Fs. After that, it is providing this much gain, but before Fs minus Fm, it is becoming 0. So that next part should not be coming in my final waveform. So in my final waveform of Y of F, I don't want any other part. I don't want these guys. I only want this one. So between minus Fm to Fm, the gain is 1 by Fs. So it will be multiplied with 1 by Fs. That means this is what I will be getting. So 1 by Fs into Fs, that would be 1 minus Fm to Fm. Now from Fm to Fs minus Fm, this is non-zero but this is 0. So anything multiplied with 0 will be 0 only. So anything will multiply with be 0. After that everything is 0 only. So 0 multiply with anything will be 0. Here also everything is 0. Are you able to understand this point? Look, I was not having this kind of ideal filter. Why I am calling it ideal filter? Because there is a sudden jump, right? Suddenly it was not taking any frequency. After that it is taking the complete frequency. So there is a sudden jump. So these kind of filters practically are not possible. Practically these kind of filters are possible. So what this filter is doing, basically slowly it is rising up and then it is giving a gain of 1 by fs. So what I am doing is that between minus fm to fm, it is passing the certain, between this frequency range, it is giving a gain of 1 by fs. So 1 by fs will be multiplied with fs. So this complete waveform I am getting. After that this is 0. Although this is non-zero, but non-zero multiplied with 0 will be 0 only. So after fm you are not getting anything. So from here you are not getting anything. From here you are not getting anything. So this waveform you are getting, which is equals to again mf only. So again you have received your mt at the output side, right? What if you are having this kind of filter? This kind of filter you are having, whatever the gain is there. So if you are having this kind of filter, what will be your output? This will come as it is, and let's just say the gain of this filter is 1 by fs. So this part will come till minus fm to fm. This part will come. Now this part will go till fs. So actually this part will also come. This part will also come. Are you able to understand this point? Let me make it better. So till fs everything would come. After that it will all be 0. And here as well, till minus fs everything would come. And after that it will, okay, sorry, till minus fs everything would come. So this is my minus fm, this is my fm, this is my fs minus fm, this is my fs, this is my minus fs, this is my minus fs plus fm. So this is your y of f. Is this equals to m of f? Absolutely not. So if you are having this kind of filter, then you are not able to get your message signal. Look, here you have made sure that fs is greater than or equals to 2fm. Here you made sure that there is no aliasing. There is no aliasing here, right? No aliasing. Aliasing. You have made sure that there is no aliasing. Still you are not able to retain your message signal. Why? Because of the filter. So if you just make sure that there is no aliasing, does that mean that you will be able to retain your signal? No. You need to design the filter as well. If you are not able to design the filter in a good manner, then you will not be able to get your signal. So first condition is aliasing. The second condition is filter. So if you are able to meet these two conditions, that means first condition is the sampling frequency and then there is a filter. So if both of these things are designed in a good manner, then only you will be able to get your message signal. So only aliasing is not enough to get your message signal, right? Are you able to understand this point? So fs greater than 2fm, fs greater than or equals to 2fm, this condition only tells that there is no aliasing. Aliasing. This does not guarantee proper recovery of message signal. Proper recovery of message signal. Are you able to understand this point? So this condition is only telling that surely there will be no aliasing, but doesn't mean that there will be, it doesn't mean that surely your message signal will be recovered, because even if you made sure that fs is greater than or equals to 2fm, yes, there is no aliasing, but my filter was something like this, right? My filter was something like this, and because of this filter I was not able to get my message signal, because I was not able to kill these frequency spectrums, right? So what is the conclusion here? To avoid aliasing, your fs should be greater than or equals to 2fm. Basically, how will you remember that, sir, this is my message signal, then another clone I will be having. This is known as clone. Basically, this is same as the message signal, no? This is also same as the message signal. So these are known as clone. So these are known as clone. So sir, here it would be plus fm. So this point will be fm. And sir, this point will be, the center will be at fs. So fs minus fm. So fs minus fm should be greater than or equals to fm. So fs should be greater than or equals to 2fm. So very easy to remember, right? Center around 0 minus fm plus fm. Then center around fs, fs minus fm. So fs minus fm should be greater than fm. So fs should be greater than 2fm. So this is the condition to avoid aliasing. Now for the proper recovery of the signal, the first condition is that your fs should be greater than or equal to 2fm. Because if you need the proper recovery, so first condition is that there should be no aliasing. What is the first condition? First condition would be there should be no aliasing. And what would be the second condition? Proper filter should also be there. Proper filter should also be there. So let's just say if I say the cutoff frequency of my filter is fc. So what will be the condition? That fc should be lesser than or equals to fs minus fm. Say yes or no. This cutoff frequency fc, let's just say this was my fc, this was my cutoff frequency fc. If this fc was lesser than fs minus fm, if this fc was lesser than fs minus fm or equals to fs minus fm, then only this much part you would have got. Rest all part would be 0. So there was no issue. In this question there was no issue because it was lesser, the cutoff frequency was equals to fs minus fm. So only this much part I was able to get. So there is no issue. Are you able to understand this point? So here if this cutoff frequency was equals to this one or lesser than this one, then there was no issue. But only lesser than this will not work. It should be greater than fm as well. Because what if it is lesser than fm? Let's just say it was here. Then only this much part you will be able to get. What if it was lesser than fm? Then only this much part you will be able to get. So that is also an issue. So your cutoff frequency should be greater than fm and lesser than fs minus fm. Are you able to understand this point? Okay. So all these points you don't need to mug up. Actually, you don't need to mug up anything. In the whole process, in the whole sampling process, you don't need to mug up anything. We will see the numerical and you will get to know that how to solve these numericals. So your cutoff frequency of the filter, should be lesser than or equals to fs minus fm, or it should be greater than or equals to fm. So these are the conditions. You don't need to mug up anything. You just need to follow the process. I hope you are able to follow the process. Now, if you are sampling very higher than 2fm, then it is known as oversampling. If you are sampling just at 2fm, it is known as critical sampling. And if you are sampling lesser than that, then it is known as undersampling. So which is desired? Oversampling is desired, right? Because if you keep sampling frequency very higher, that means time window is very lower. That means you are collecting the samples at very lesser time window. And if you are collecting fs is very greater than 2fm, what will be happening in frequency domain? If fs is very far away, that means there will be no aliasing and you will have larger window for cutoff frequency of a filter, right? You will have a very larger window of cutoff frequency of for the cutoff frequency of your low pass filter, right? Because if this clone is very far away, so this could be larger, right? This could be larger. Still everything you will get only this part. So we will see the numericals, it will be more clear to you, but the important part was the process should be clear. And here I am just writing that this is the desired part. And I hope the process is clear to you. What we are doing, this is the diagram. MT multiplied with CT. So MF convolved with CF. CF is impulse train only convolution. That means the same shift will be given to MF. So you will be getting a lot of clones. This is your MF, this is your CF, you are getting clones. Now at the receiver side, you need a low pass filter. From this low pass filter, you got this particular message signal out of it. And because of this message signal, we are able to recover. But the filter is playing an important role. If this filter was there, all okay. If this filter was there, still all okay. But if this filter was there, then there was an issue because these parts are coming into action. Okay. So there are two conditions to avoid aliasing. Fs should be greater than or equal to 2 FM. And for proper recovery of the message signal, first there should be no aliasing, because if there is any aliasing, then everything is gone. So first condition is there should be no aliasing. Second condition is your cutoff frequency of your filter should be greater than FM and should be lesser than Fs minus FM. So if you are sampling at a very higher frequency, it is known as oversampling. If you are sampling just as at 2 FM, then it is known as critical sampling. And if you are sampling lesser than 2 FM, then it is known as undersampling. This is the desired case. Fs very greater than 2 FM is the desired case. Now we need to solve the problems. So in the problems, nothing you need to mug up. These kind of diagram will be there in the examination hall. You will be asked these kind of questions. So I need to take a break, then I will come back and we will solve the problem. Nothing, zero thing you need to mug up. Okay, just follow the process, whatever that we have done. In the examination hall as well, you will be following the process and you will be able to get the final answer. Okay, so let me read this question for you and you try solving it on your own. So there is an MT, there is a multiplier, there is a CT. CT is the impulse train, this is the impulse train. Then you are getting your MST that is passed through an LTI system. This is an LTI system. LTI system having an impulse response of sin 10 pi t divided by Fs pi t, and you are receiving output yt. Fs is 1 by Ts. Okay. MT is band limited to 2 Hz. That means maximum frequency component is 2 Hz. So find the minimum sampling frequency Fs for avoiding the aliasing at MST. So that means here there should be no aliasing. You need to find the minimum sampling frequency. Then second question they are asking, find the minimum sampling frequency Fs for the proper recovery of message signal at the output. So two things you need to make sure. In the first question, you don't need to care about yt. Only you need to care about till MST. So there should not be any aliasing. For that, what should be the sampling frequency? And at the output, if you want to get the proper recovery of message signal, then what should be the minimum sampling frequency? So these things they are asking. All good. What people usually do? Sir, Fs should be equal to 2 FM. Minimum sampling frequency is equal to 2 FM. So answer will be 4 Hz. So in both of the cases, answer is 4 Hz. Absolutely wrong. So don't blindly solve these in this manner. Okay, I told you again and again here. I told you again and again that aliasing is a different thing. Proper recovery of message signal is a different thing. This and this both are different thing. So if you talk about aliasing, that means you only talk about MST. But if you talk about the proper recovery of message signal, then this filter is also coming into action. Right? So try doing it on your own. If you are not able to solve, then also it is fine. We will see it. Okay, I will take a pause. I will take a break. Then I will come back. You can also take a break or you can revise it. Yeah, welcome back. So did you try this question? So first there is MT which is being multiplied with CT. So MT is band limited to 2 Hz. That means you can draw its frequency spectrum. Now CT is an impulse train. So you know what will be its Fourier transform. So that also you know. Both are being multiplied. That means they will be convolved in the frequency domain. So you can do the convolution as well and you will get your MST. You will get your sampled message signal. So this is how you can draw your frequency spectrum of MT. This is the frequency spectrum of MT, band limited to 2 Hz, right? And what will be your CF? CF will be having the amplitude of Fs, where n goes from minus infinity to infinity. Basically, impulses will be there at all the discrete frequencies, Fs, 2Fs, 3Fs, in that manner. Both will be convolved. When both will be convolved, what will happen? The MF will get its clone, right? Clone centered at 0, Fs, 2Fs, 3Fs, minus Fs, minus 2Fs. So what will happen is that MF will get its clone which are centered at 0, centered at Fs, 2Fs, in that manner, 2Fs, then minus Fs, then minus 2Fs, and so on, right? Centered at 0, Fs, minus Fs. So 0, 2, minus 2. This point will be 2 ahead of Fs, 2 backward of Fs. And what this point will be? 2 ahead of minus Fs and 2 backward of minus Fs. So in that manner, this is the frequency response of your sampled message signal. So till this point, you already know everything. Now what is the first question that they are asking? Find the minimum sampling frequency to avoid aliasing. So you need to avoid aliasing. That means when you add all these frequency spectrum, that means there will not be any common part or there will not be any overlapping area. For that, what should happen? That fs minus 2 should be greater than 2. Fs minus 2 should be greater than or equals to 2. So fs should be greater than equals to 4 Hz. So this is the answer of first question, right? This is the answer of first question. So what is the minimum sampling frequency? The minimum sampling frequency is 4 Hz. So this is the answer. Second one, find the minimum sampling frequency fs for proper recovery of message signal at the output. So after this point, then there is a filter. There is a filter ht. This is what? This is a sync function, or you can say this is a sampling function. So in the time domain, in the frequency domain, it will be rectangular. Can you draw the frequency response of this ht? Yes, I can draw the h of omega. I can draw the frequency spectrum of ht. That will be h of omega that I can draw. And then I will receive my output yt. So what will happen? This message signal will be filtered by a low pass filter. This will be a low pass filter. And I will receive my message yt. Okay, so let's see. What will be your h of f? So let's see what will be your h of f. What is our ht? ht is given as sin 10 pi t divided by fs pi t. Sin 10 pi t divided by fs pi t. What does that mean? The frequency will be going from minus 10 pi to 10 pi, right? I told you sin 80 by pi t. So frequency will be going from minus 10 pi to 10 pi with the amplitude of 1 by fs, right? So band will be there. This will be the rectangular function. It will be a rectangular function which will be going from minus 10 pi to 10 pi with the gain of 1 by fs. But, and here also the gain was fs, right? If this was your m of f, so here the gain became fs. So fs should be multiplied here. So here also fs is multiplied. But this frequency is going from minus 10 pi to plus 10 pi in the omega domain. But you are writing down in f domain. So this will go from minus 5 to 5. Say yes or no, right? Now what do you want? Now what do you want? You want the proper recovery of message signal. That means no part of this clone should come. No part of this clone should come. What I am saying? Clone. So no part of this clone should come. No part of this clone should come. What does that mean? That means that your fs minus 2 should be greater than or equals to 5, because when this filter is being multiplied with this frequency spectrum, that means it should be multiplied till this point only. So fs minus 2 should be greater than or equals to 5. That means fs should be greater than or equals to 7 Hz. So for proper recovery, this condition should be satisfied. Along with that, this condition should also be satisfied. What condition we got? This condition should also be satisfied, because why is that so? Because if this condition is not satisfied, that means there is aliasing. So if there is aliasing, then there is no chance that you can recover your signal. So first condition is you need to avoid aliasing. After that, the condition for low pass filter will also come into action. So condition for filter also came into action. Is that clear to you? Right? So these two conditions are there, that your sampling frequency should be greater than 4 Hz and sampling frequency should be greater than 7 Hz. So what will be the final answer? What will be the final answer of option B? If I am saying that I will be happy if Virat score more than 10 runs, and you are saying that you will be happy if Virat scores more than 20 runs. So how much runs Virat should score so that we both are happy? 20, right? Or 21. Basically, if Virat is scoring more than 10 runs, then I am happy. If Virat is scoring more than 20 runs, then you are happy. So how much runs Virat should score so that both are happy? Both should be satisfied. So here this should be also satisfied, this should also be satisfied. So what should be the value of fs? That should be 7 Hz. So minimum value, what they are asking? The minimum sampling frequency. So minimum sampling frequency has to be 7 Hz. So never ever apply blindly, don't close your eyes and apply fs equals to 2 fm. That would be absolutely wrong. So answer of second one is 7 Hz and answer of first one was 4 Hz. So fs equals to 2 fm, that you don't need to apply blindly. For avoiding the aliasing, fs equals to 2 fm. That is fine. But for proper recovery of message signal, fs equals to 2 fm will not work. You need to analyze it. You need to see what kind of filter I am having. All good? All fine? Let's go to the next concept, you can say, or you can call it a question as well. So till this point, our MT was a baseband signal, which was band limited to 2 Hz or 3 kHz or 5 kHz or FM frequency. Now our MT signal is a cosinusoid or sinusoid, whatever you can call it. So now this MT signal and the same process is there. It is multiplied with the impulse train, then you are having a sampled message signal, and then you are passing it through a low pass, through a filter. Through any filter you are passing it, and then you are getting output YT. Now I am not saying that this is a low pass filter, it could be any kind of filter. So you are passing it through a filter and then you are getting an output YT. So same process is there. What they are saying, you need to take the sampling frequency in this manner, that sampling frequency is 1 Hz, 0.5 Hz, 2 Hz or 3 Hz. Then you need to comment on aliasing, and you need to find out a proper filter for proper recovery of MT at output. So basically I need YT equals to MT. So what kind of filter I will be using? These kind of things you need to tell. Basically we will be analyzing it. I could have taught it as a concept, or I could have taught it as a problem. So I decided to take as a question. So now I am taking it as a question. So I am having my MT. Can you draw the frequency spectrum of MT? Yes, which is a cosinusoid. I know that cosinusoid is having only one frequency, that is 2 pi. So here there is only one frequency, fundamental frequency is 2 pi, or in the Hertz if you need to write down, that would be 1 Hertz. So 1 Hertz frequency it is having. Okay, so positive frequency and negative frequency both will be existing. So this is my M of f. My M of f is, it will be having two impulses, one at omega naught and one at minus omega naught. What is the value of omega naught? That is 1 Hertz. So one at 1 Hertz, one at minus 1 Hertz. Do I care about the amplitude? In the last lecture only I told you we don't care about the amplitude of our signal. Why is that so? Because now everything whatever that is happening, that will happen with MT. Let's just say our MT is multiplied with Fs. So what I am doing? I am doing the analysis in frequency domain. So let's just say my MF is multiplied with Fs. So in the time domain as well, what I will get? Fs into MT. Are you able to understand this point? Let's just say my MF was being multiplied with some factor and some phase as well. So in the time domain as well, the same thing will be reflected, no? Are you able to understand this point? So here I will not be thinking that, sir, okay, it would be 1 by 2 and then multiply with 2. All these things I will not be caring about. I will not even caring about whether it will be a positive impulse or negative impulse. I just know the frequency content and I just know that the amplitude is A. That's it. There is some amplitude, the amplitude I don't care about. Because after this there will be sampling process. So whatever that is happening with this MF, the same thing will be happening in the time domain as well. Are you able to understand this point? So that's why here I don't care about any amplitude. This thing I told you in the last lecture as well. Now there is an impulse train which is having a time period of Ts. So same process is there. You can write down your C of f. What that would be? C of f. Each impulse will be having an area of Fs and impulses will be there at all the discrete frequencies Fs, 2Fs, 0, minus Fs, minus 2Fs and so on. Right? Then both will be convolved. Both will be convolved. And here NFS. Both will be convolved. So what happens? The center is moved to Fs, 2Fs, 3Fs and so on. Basically this center will be moved to Fs, 2Fs, 3Fs and then minus Fs, minus 2Fs, minus 3Fs. Right? Now what will happen to this frequency? Basically what I am saying is that here these were the two impulses. Now what will happen? This center will be moved to Fs. Right? So these impulses will also move in the same manner. So this impulse will be there at Fs minus 1 and this impulse will be there at Fs plus 1. The same thing that happened here. The center has moved to Fs. So Fs minus 2, Fs plus 2. So similar thing will happen here. This was 1, this was minus 1, this was 1. Now center has moved to Fs. So one backward of Fs, one ahead of Fs. Similar thing will happen here. center will move to 2fs. Center will move to 2fs. So one backward of 2fs and one ahead of 2fs. Right? So here there will be impulses. Are you able to understand this point? How I am making these impulses? Impulses are already there at -1 and 1. Now if I am multiplying with the impulse train, then what will happen? The similar kind of pattern I will be getting. Basically I will be getting the clones. I will be getting the clones of this frequency spectrum. This is centered at 0, but now it will be centered at fs. So one backward of fs, one ahead of fs. The other one 2fs, centered at 2fs. So one backward of 2fs, what that would be? 2fs minus 1. One ahead of 2fs, that would be 2fs plus 1. Similarly here as well, here what will be the same? Centered at minus fs. So one ahead of minus fs and one backward of minus fs. So what all frequency components you will be having? What I am saying, what all frequency components you will be having? So centered at fs. So one ahead and one backward. Centered at 2fs, one ahead and one backward. Centered at 3fs, one ahead and one backward. Centered at minus fs, one ahead and one backward. Centered at minus 2fs, one ahead and one backward. Centered at minus 3fs, one ahead and one backward. Basically you don't need to care about these negative values, because whatever the positive value that you are getting, the same clones will be there in the negative side as well. So only you can care about positive values only. Along with that, these will also be there at 1 hertz, at -1 hertz. So 0 plus -1 will also be there. So 0 plus -1, then fs plus -1, 2fs plus -1, minus fs plus -1, these all frequency content would be there. Let's take an example. Let's understand with respect to example. So first let's take the example of 3 hertz. Okay, first let's take the example of 3 hertz. So fs is equals to 3 hertz. This is what we are taking. So can you make MSF? That means can you make the sampled version now? Sampled message signal, frequency spectrum of sampled message signal. This is what we are drawing. So you are having impulses at -1 and 1, -1 and 1, -1 and 1. Now now what will happen is that the area will be multiplied with fs. This area will be multiplied with fs because of this. What you are doing, you are convolving mf with the cf, the same process we are doing. Here what was happening, the peak amplitude was multiplied with fs. So here also the amplitude is multiplied with fs. In the case of impulses, it is area. So it will be multiplied with fs. Now what is your fs? Fs is 3 hertz. So center will move to 3 hertz. So one backward of 3 hertz and one ahead of 3 hertz. There will be 2 impulses. Then center will be moved to 2fs. What will be 2fs? 6 hertz. So one backward of 6 hertz and one ahead of 6 hertz. There will be impulses. Are you able to understand this point? All will be having the area of AFS, 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 AFS. Let me know, are you able to understand these points or not? So this process is happening here. This was your FS, right? This was your 2FS. We are getting the clones of MF centered at 0, FS, 2FS, 3FS, FS, minus 2FS, minus 3FS. So similarly, the same thing will be happening at the negative side as well. So you will be having the clones at -2, -4, -5, -7. These kind of clones you will be having. Just let me know, is there any aliasing? No aliasing is there. No aliasing. If you want to retain your message signal again, if you want to retain from here, you will use a filter and you want to retain your message signal again, what kind of filter you can use? This kind of filter I can use. Basically, what kind of HF you require now? What kind of HF you require? I can use a low pass filter now. Say yes or no. I can use a low pass filter. This kind of low pass filter I can use. This will be my h of f. Okay. So here this frequency is minus 1, 1. So what I can do? I can keep this frequency as minus 1.5 and 1.5. And what area I will keep? 1 by fs. So no, not area, what amplitude I will keep or what gain I will keep, that will be 1 by fs, because I need to multiply afs with 1 by fs so that this a I again get. Right? So extra term fs I am having, that's why I kept the gain here as 1 by fs. So this kind of filter I can use. So what it will do? It will filter out everything else. It will filter out everything else. It will only keep these two impulses. So this filter I can use. Can I use this kind of filter as well? Can I use this kind of filter as well? Did you? अरे यार. So this frequency I am keeping as minus 1.5, minus 0.5, 0.5 and 1.5. And again this amplitude we are keeping as 1 by fs only. So this amplitude is 1 by fs only. Because what do I need? I need only these two impulses, which are centered at minus 1 and 1 only. I should not say centered at, these impulses are there at minus 1 and 1 only. So I just need to pass these impulses. I just need to pass these impulses only, nothing else. Basically, I need to pass only minus 1 hertz frequency and I need to pass only 1 hertz frequency. That's it. So for that, can I use this band pass filter as well? Yes, band pass filter can also be used. But here in this question, can you use band pass filter? No, because here you don't need to pass impulses. That means you cannot say that, sir, I need to pass only minus 2 hertz and 2 hertz. No, you need to pass everything between minus 2 to 2. What I am saying, you need to pass everything between minus 2 to 2. So you don't need to pass only minus 2. You don't need to pass only plus 2. You need to pass everything. That's why you have to use this low pass filter. But here if I use band pass filter, which is having a very less bandwidth, here I put the bandwidth equals to 1. I could have put the bandwidth as something like this, that this is your 0.999999 and this is your 1.000001. Still this frequency will pass. So a very lower bandwidth, a very lower bandwidth band pass filter will also work, right? The band pass filter having a very low bandwidth, that will also work. What is the bandwidth of this one? 0.00001 only, no? Very low. So that will also work. Are you able to understand this point? Okay. So although let's keep it as 0.5 to 1.5 only. So in case of sinusoid sampling, you can use band pass filter as well for proper recovery of message signal. This is the first point. This is the first question. D option we have done. So there was no aliasing. Let's see the C question. Not C, let's go to A now. Fs equals to 1 hertz. Fs equals to 1 hertz. So now you just let me know one thing, what all frequency content will be present. So basically plus minus 1 hertz will surely be present. Basically these plus minus 1 hertz will surely be present. What I am talking about? I am talking about in your sampled message signal, in the frequency spectrum of sampled message signal, what all frequency component will be present. So minus 1 plus 1 will be present. Minus 1 plus 1 will be present. Now center will be moving to Fs. Center will be moved to Fs. So one backward of Fs, one ahead of Fs. Those will also be present. What is the value of Fs? That is 1. That we can put. Center will move to 2Fs. Center will move to 2Fs. So one backward, one ahead. Center will move to 3Fs. One backward, one ahead. All these frequency component will be present. And similarly in the negative side as well. What is the value of fs? That is 1. Value of fs is 1. Value of fs is 1. So this will be 2, this will be 3. So basically what you are getting? Plus minus 1 hertz. Here 1 if you put 1, what you will be getting? 1 plus 1 is 2, 1 minus 1 will be 0. So 2 and 0. Here if you put 1, what you will be getting? 3. This will be 2. So 2 plus 1 is 3, 2 minus 1 is 1. 3 and 1. Here what you will be getting? If you put fs equals to 1 here. So 3 plus 1 is 4, 3 minus 1 is 2. 4 and 2. So what kind of frequency component you will be having? 1 minus 1. Negative side you ignore. I only take the positive side. So you are having the frequency component at 1, 2, 0, 3, again 1, 2, again 2. That means this is being overlapped. This is being overlapped. And then more 3 will also be overlapped. If you write down 4 fs plus minus 1 here, then what is the value of fs? That is 1. So 4 plus 1 is 5, 4 minus 1 is 3. So 3 will also be overlapped. After that what will come? 3 and 5. So that will be also overlapped. So here you can see that yes, there is aliasing. Are you able to understand this point or not? Let's make the diagram. I am making the diagram of MSF. What I am doing? I am making the diagram of MSF. So from here a very good point will come out. Minus 1, 1. What will be the area? A into Fs, right? A into Fs. If I am saying that this area is A, so when you multiply it with the impulse train, so A into Fs. Now what will happen? The center will move to Fs. Center will move to Fs. And what is the value of Fs? That is 1 hertz only. So center will move here. Now 1 backward and 1 ahead. That means 1 backward and 1 ahead. 1 backward and 1 ahead. So these two I will be getting AFS, AFS. 1 backward and 1 ahead. Now what will happen? Center will move to 2Fs. So that means center will move here. So 1 backward and 1 ahead. 1 backward and 1 ahead. So at 1 only, at this 1 only, again I am getting another AFS, and here I will get AFS 3. Now center will move to 3, because 3Fs plus minus 1. And the similar thing is happening that side as well. Similar thing, what I am doing is that whatever that I am making on this side, here secondly what happened when Fs plus minus 1 we made, that our center moved to 1, then 1 backward, 1 ahead. So now the center will move to minus 1 as well. So 1 backward and 1 ahead. That process will happen. So basically in the green pen, center could move to minus 1. So 1 backward, basically this clone will be copied here as well. Are you able to understand this point? 0, it will be again copied. At 0, 2 times you are getting the same thing. And here, this whatever that was happening here, the same thing has happened here as well. So I hope you are able to make this diagram. Now we said that my center will be moving to 2Fs. That means my center will be moving to minus 2. So 1 backward and 1 ahead. So this red and red that we got, so same red and red we will get here as well. So sorry. 1 backward and 1 ahead. So 1 backward and 1 ahead. So whatever that is happening on the positive side, the same thing is happening on the negative side as well. Now what will happen? 3Fs. Center will be moved to 3, and here center will be moved to minus 3. So 1 backward and 1 ahead. What will happen? 1 backward and 1 ahead. So here also the same thing, 1 backward and 1 ahead. Then center will move to -4. Are you able to understand this point? What is happening here? 4 and -4. Now center will be moved to 4fs. Here amplitude you can write down AFS. Again AFS is coming into action. Here also AFS and here also AFS. Then the center will move to 4. So 1 backward, 1 ahead. Center will move to -4, 1 backward, 1 ahead. So what do you think what is happening here? Aliasing is there, right? Surely there is aliasing. Because frequency spectrums are being added. AFS is being added. AFS is being added. These frequency spectrums are being added. So aliasing is there. But one interesting thing is there. What is that? Still you can recover your signal. Still you can recover your sinusoid signal. Why is that so? Because two impulses got added here. AFS plus AFS. What it will become? 2AFS. Here also AFS is there. 2AFS. Look, what will be the resultant? What will be your resultant MSF now? What is your resultant MSF? AFS plus AFS. What it will become? 2AFS. AFS plus AFS. 2AFS. AFS plus AFS. 2AFS. This AFS you only see once, but when your center move to 4FS, at that time this will also become 2AFS. So basically everything will become 2AFS. Everything will become 2AFS. Everything will become 2AFS. So in that manner the same process is going on. 2AFS, 2AFS. So what you will be getting? Area being 2AFS. 2AFS, 2AFS. Centered at 1, -1, 0, 2, 3, 4, -2 and so on. 2AFS, 2AFS and so on. You can still recover your message signal from here. Because what do you want? You want impulses of area A. That's it. This is what I want. So what I will do? What kind of filter I will make? Directly you can think you will make a band pass filter which is centered around. You will make a band pass filter which is centered around -1. Centered around -1 means center will be -1. Rest all whatever the width could be there, that I don't care, but it should be centered around -1 and here it should be centered around 1. Whatever the width is there, that I don't care. And what will be the height I will be keeping? 1 by 2fs. 1 by 2fs. Gain or height, whatever you call it. This will be my h of f. So this is how I can design it. Okay. 2AFS will be multiplied with 1 by 2fs, 1 by 2fs. Here this point I will keep as -1.5. This point I will keep as -0.5. This point I will keep as 0.5 and this point I will keep as 1.5. So 1 by 2fs multiply with this one, 1 by 2fs multiply with this one. After this, what will be the output you will be getting? You can directly see it. There will be impulses of area A, and impulses of area A you are having in your MF only. So you are able to recover the message signal again, even though there was aliasing. So what was your sampling frequency here? Here your sampling frequency, in this case your sampling frequency was equals to FM only. Fs was equals to FM, because what was your FM? Let's call it FM only. So what was your FM? 1 Hz. So sampling frequency was Fs equals to FM. Even if Fs is equals to FM, even though there is aliasing, still you are able to recover your message signal. So some people says that for recovering the message signal, the minimum sampling frequency should be equals to 2 FM. Absolutely wrong. Doesn't make any sense. Okay. Your minimum sampling frequency should be Fs should be greater than or equals to 2 FM to avoid the aliasing. That's for sure. And if you have avoided the aliasing now everything depends on the filter. So what do I say is that don't mug up anything. In sampling, don't mug up anything. There will be a process of solving the question. Especially in case of sinusoid, this thing will be occurring, because in case of sinusoid, your frequency spectrum have the impulses. But in case of baseband signal, there are no impulses. It is a continuous frequency response. This is a continuous frequency response, right? There are no impulses. This is not a discrete. This is a continuous. So here the condition has to be satisfied that Fs is greater than or equals to 2 FM First you need to avoid the aliasing, then you need to design your filter. But here, even if there was aliasing in Fs equals to Fm, yes, there was aliasing, but still, anyhow we managed that, we got our message signal back. Are you able to understand this point? So the only conclusion is, don't mug up anything. That's it. If there is a question on sampling in the examination hall, you will just solve it, nothing else. In the examination, you will just follow the process and you will solve it. In the next one, what we are keeping, Fs equals to Fm by 2. Try doing it on your own and let me know, are you able to recover the message signal or not? Think about it. Will you be able to recover the message signal or not? And will there be any aliasing or not? So let's check. Fs is equals to 0.5 Hz. So what all frequency components will be present? What all frequency components will be present? So surely plus minus 1 Hz will be present. Now what will happen? Your center will move to Fs. So Fs plus minus 1. Then center will move to 2Fs plus minus 1. Center will move to 3Fs plus minus 1. What is the value of Fs? 0.5. So 0.5 plus minus 1. Then 1 plus minus 1. Then 1.5 plus minus 1. So from here what we are getting? 1.5 and minus 0.5. From here what you are getting? 2 and 0. From here what you are getting? 2.5 and 0.5. Till this point you don't see any aliasing here. And from here you are getting 1, only 1. I would say only 1, because this is the positive side I am writing down. These impulses are coming because of the positive side. Now because of the negative side minus 1 would come, and then minus Fs plus minus 1. Minus 2Fs plus minus 1. Because center will be moved to minus 3Fs plus minus 1. Fs value is minus 0.5. I hope I am doing the calculation correctly. 2.50. Minus 1. Minus 0.5 plus 1. What that would be? 0.5 only and minus 1.5. From here what we are getting? Minus 1 plus 1. That would be 0. And here I got the aliasing. Because this 0 and this 0 both are coming into action. So I got the aliasing, right? Because Fs value is 0.5, so this will become minus 1. So minus 1 plus 1, minus 1, minus 1, so minus 2. Here Fs value is 0.5, so minus 1.5 plus 1, what that would be? Minus 0.5. And minus 1.5 minus 1, that would be minus 2.5. So you can see that this is common. So here there will be aliasing. Aliasing will be there because of when your message signal is moving towards 2Fs. Because of that there will be aliasing. So let's make MSF. Let's make MSF. Centered at centered minus 1 1, right? Minus 1 1, minus 1 1. Gain will be AFS. Now the center will be moving to 0.5. Center has moved to 0.5. Now in 0.5, 1 ahead, 1 backward. So 0.5, 1 ahead, that means at 1.5, and 1 backward, that means at 0.5. So you will be having the impulses at 1.5 and 0.5. So 0.5, 0.5 and 1.5. Are you able to understand this point? I have moved my center to 0.5. So 1 ahead and 1 backward. So this is your 0.5, 1 ahead, 1.5, and 1 backward will be minus 0.5. All these are coming because of Fs. Now because of minus Fs, the same thing will come. My center will move to minus 0.5. So 1 ahead. 1 ahead means minus 1.5. 1 ahead and 1 backward. What that would be? 0.5. Minus 1.5 and 0.5. 2Fs plus minus 1. 2Fs plus minus 1. So center will be moving to 1. Center will be moving to 1. So 1 backward and 1 ahead. 1 backward and 1 ahead. 1 backward and 1 ahead. So here you will be reaching. And here the center will be moving to -1. For this one, what is the value of -2fs? -2fs value is -1. So center will be moving to -1. So 1 backward and 1 ahead. So here you can see that there is aliasing again. 1 backward and 1 ahead. So this point is -2, this point is 2. Right. So yeah, frequency spectrums are being added here. So in that manner you can keep on making. So you can see, yeah, there is aliasing, here there is aliasing. But still you can recover your message signal. How will you recover your message signal? You can design this kind of a band pass filter, right? You can design this kind of band pass filter with the pass band gain of 1 by fs, and you will get your message signal. So what we can do, design band pass filter centered at 1 Hz with the pass band gain of pass band gain of 1 by fs. Say yes or no, right? Because 1 by fs will cancel the fs and you will get the same. Hopefully there will not be any aliasing with this particular sinusoid. I hope, what I hope is that when we write down these things, 4fs plus -1 and then -4fs plus -1, so another sample will not come at 1. This is what I am thinking. So let's check. Here it will come, no? 2 plus -1. So what will happen? 3 and 1. The samples will be at 3 and 1. So another sample at 1 will come. In this process, what will happen? Your center would be moved to 4fs. That means your center would be moved to 2. So 1 backward and 1 ahead. When your center is moved to 2, 1 backward, that means another sample would come here and 1 ahead. So here you can see that again there is aliasing. This one and this one, right? And here also the same thing will be happening. -4 plus 1, that means -3. Sorry, not -4. This is -2. -2 plus 1, that means -1. And -2 minus 1, -3. So this -1 and this -1. Yes, there is aliasing. So here what will happen? AFS will be added with AFS, so it will become 2AFS. So what should be the gain? 1 by 2FS. Here what was the gain? 1 by 2FS. So here also the gain should be 1 by 2FS. So yes, there is aliasing for sure. Aliasing is there. But still we can recover our message signal. How we can recover our message signal? Using a proper band pass filter centered around -1 and 1 and with the gain of 1 by 2FS. Right? Because here there is aliasing, because of that AFS, AFS, and this was also your AFS and AFS. These will be again added and added. Because of that it will become 2AFS. Whatever the process that was happening here, the same process is happening here. So just the point is, I don't know how this question can be asked in your examination. Till this point, these kind of questions are not asked in the examination. But the thing is, when your Fs was, this was your Fs. What was your Fs? 3 Hz. So this is greater than 2 FM, right? 2 FM. FM value is 1. So this is surely greater than or equals to 2 FM. So when your Fs was greater than or equals to 2 FM, there was no aliasing. And properly you can use your low pass filter. Properly you can use your low pass filter. Can you use low pass filter in this case? No, you cannot use a low pass filter. Let's just say I use the low pass filter like this. So what will happen? This extra impulse will come that I don't want. I only want these impulses. So I cannot use low pass filter. Here also I cannot use low pass filter. Here also I cannot use low pass filter because these extra impulses will come that I don't want. Are you able to understand this point? So I have to use band pass filter here. But if your Fs is greater than 2 FM, Fs is greater than or equals to 2 FM, at that time, what is the surety that you are having? That you can use your low pass filter for sure. Here you can use your low pass filter. Here you have to use band pass filter. Here also you have to use band pass filter. Here what is the scenario? Fs is equals to 2Fm. So can we use low pass filter here? Let's check. Here we can use low pass filter, along with that we can use band pass filter as well. But we cannot use, sorry, here we can use both. But here we cannot use low pass filter. Here also we cannot use low pass filter. What about this one? Band pass filter surely we will be able to use, there is no doubt about that. Will you be able to use low pass filter here? Let's check that out. Page should be added. See, Fs is equals to 2 Hz. So let's see the frequency component. 1 minus 1 centered at Fs. Fs is 2 here. Centered at Fs. 1 ahead, 1 backward. Centered at 2 Fs. 1 ahead, 1 backward. Centered at 3 Fs. 1 ahead, 1 backward. Right. In that manner we will be going. And what about the negative one? Centered at minus Fs. 1 ahead, 1 backward. Centered at minus 2 Fs. 1 ahead, 1 backward. Centered at minus 3 Fs. 1 ahead, 1 backward. 2 plus 1, 3, 1, 5, 3, 7, 5. Aliasing is there. Even when Fs is equals to 2 Fm, still there is aliasing. So Fs equals to 2 Fm. Why this is the case? Because this is the boundary, no? Fs equals to 2 Fm, this is the boundary. 1 and minus 1. Now what will happen? The center will move to 2. So 1 backward and 1 ahead. 1 backward and 1 ahead. Then center will move to 4. 1 backward, 1 ahead. So yes, aliasing will occur. This is 3. This is 5. Then center will move to 6. 1 backward, 1 ahead. So in this manner it will keep on occurring. And in the negative side as well, center will move to minus 2. 1 backward, 1 ahead. Center will move to minus 3. 1 backward, 1 ahead. So in that manner it will keep on occurring, and what will be the final one? AFS, AFS, so it will become 2 AFS. But the beauty here is that I can use low pass filter. So aliasing is still there. So to avoid the aliasing, this has to be there, that it should be greater than only. You cannot use the equal sign here, because at equal sign there will be aliasing in case of a sinusoid signal or in case of any periodic signal. Why is that so? Because the Fourier transform of periodic signal will be impulsive. This we have already seen. Fourier transform of any periodic signal will be impulsive. And when there are impulses, they are there at that point only, at that specific point. Let us say at 1 and minus 1. And if you put Fs equals to 2 Fm, then what will happen? The center will move to Fs. Center will move to Fs. But what will happen? It will throw back Fs minus Fm. And Fs minus Fm is equals to Fm only. So here what will happen? 2 impulses will be added. So if you are sampling a periodic signal, to avoid aliasing, Fs should be greater than 2 Fm. Are you able to understand this point? And if you are sampling a baseband signal, then Fs could be equals to greater than or equals to 2 Fm to avoid the aliasing. So here also there is aliasing. You can directly see aliasing is there. But this kind of a frequency response would be there for sampled message signal. And now I can use my low pass filter here with the gain of 1 by 2 Fs. Right? I can use my low pass filter. Here you can see 3 and 3 will be added. Then 5 and 5 will be added. The same kind of process is happening. This kind of process is happening here. Right? But here the issue was there that another impulse was there at the origin. This was the issue. That at the origin as well there was some impulses. Because of that we couldn't use our low pass filter. But now in this case there is nothing else in between. At the origin or here, no impulses will come into action. Only the impulses will be there at 1 and minus 1. Okay? And if that is the case, then surely we can use band pass filter. We can use low pass filter as well. Are you able to understand this point? So this, all the things we are going to write down now. And aliasing is still there. In the next cycle, what will happen? 8 plus minus 1. So 9 and 7. So here 7, this 7. The same thing is happening here as well. Minus 1 and minus 3. Here minus 3 and minus 5. Here minus 5 and minus 7. So this minus 1 and this minus 1. Aliasing is there. Minus 3 and minus 3. Aliasing is there. Minus 5, minus 5. This aliasing is there. In the next cycle, minus 7, these things will come. But proper aliasing, like no extra impulses are coming into action. So low pass filter you can use. Low pass filter with, what should be the cutoff frequency? Low pass filter with the cutoff frequency of 1.5. 1.5 hertz. I can use 1.5 hertz. Why is that so? Because between minus 1.5 to 1.5, these impulses will come. And next impulses will be there at 3 and minus 3. So these should not come. Right? So I want to avoid the next impulses. So between minus 1 and 1, whatever the impulses are there, that I will take. So low pass filter with cutoff frequency 1.5 hertz and pass band gain of 1 by 2 fs. Right? 1 by 2 fs. And surely you can use band pass filter as well. Band pass filter centered at 1 hertz with the pass band gain of 1 by 2 fs. Okay, and how that is happening, that I have explained roughly. Okay, so this was the motive, that when you are sampling a sinusoid signal, even if you are sampling at, even if you are doing undersampling, still there are chances that you will be able to recover your message signal again. But if you are doing undersampling in case of baseband signal, if you are doing undersampling, then there is no chance that you will be able to recover your message signal because of the aliasing. But in case of sinusoid signal, even if there is aliasing, still there is a chance that you will be able to recover your message signal, because here impulses will be added and you can use your band pass filter, or in these cases you can use your low pass filter as well. So I am not writing down any conclusion here. I am not going to write down any conclusion that this thing fs equals to 2 fm. So those conclusion I will not be able to write down, because you will not be able to remember all these conclusion in the examination hall. So what is the tip here? What is the only conclusion? The only conclusion is that you should be able to analyze all these things in the examination. I don't know how they will ask the question. They can give this particular thing, then they can give the sampling frequency, and then in the statement they can write down that I can use a low pass filter of pass band gain 1 by 2 fs to recover my message signal. I can use a band pass filter centered around 1 hertz of gain 1 by 2 fs to recover my message signal. Then pass band gain they will change, center frequency they can change. In that manner they can frame 4 options, and then they can ask you which of the following option is correct. These kind of questions they can frame. So whenever a sampling of sinusoid and cosinusoid is coming, you just need to take care of one thing, that even if there is aliasing, still I can recover my message signal. Okay, there you go. Next one. Now we are going to sample our message signal with any random periodic signal. Okay. Previously what we were doing, we were sampling with respect to impulse train only. This was the impulse train. We remember C of f, and then we were sampling. Now nothing you need to remember. You are remembering nothing. This question is coming in front of your computer screen in the examination hall, and have the temperament to solve it on your own. Message signal is there, multiplier is there, CT is given. How do I get to know that it is periodic? Because it is written in terms of complex exponential with the particular omega naught frequency. So this is a periodic signal with what you are sampling it. Or forget about sampling. I am not even using the word sampling. In the whole process, I am not using the word sampling. I am just giving you a block diagram that MT is multiplied with CT, and then I am getting MST, which is passed through a LTI system, which is having an impulse response of HT, and you are getting output YT. Now I am saying that you need to design H of omega in a manner that YT is equals to MT. Then you need to design H of omega such that yt is equals to 2mt cos 16 pi t. So just think about it. Multiplication in time domain will result in convolution in frequency domain. I know how to do the convolution. Then I can get MSF. If I have the MSF, I know how to retain MF. But this time you don't need to retain MF. Along with this time they want you to retain this particular thing. So can you find out the frequency spectrum of this one? So you will get to know that what they want you to retain. And if you understand what they want you to retain, then it will be easy for you. So try doing it. These kind of questions will surely be asked in the future. As of now, they are not asked, but surely these kind of questions can be asked. They will ask you, you need to design H of omega. So they will frame 4 options where they have designed H of omega on their own, and they will ask you which of the filter is correct. Which of the filter will result in yt equals to mt? Which of the filter will result in yt equals to 2mt cos 16 pi t? So try doing it on your own. I have to take a break again. Okay. Then we will see this question. Okay. This is also good, and then we will solve gate PYQs. So I guess another 1 hour it will take. So let me take a break, drink some water, and then I will come back. We will solve this question. Yeah, welcome back. So did you try this question? So let's start. MT is band limited to 2 Hz. So I can draw the frequency spectrum. I have already drawn it here. So I will just copy it. I will just copy the frequency spectrum here. And then this is my CT. So my CT is not a impulsive train this time. CT is something else, having a Fourier series coefficient of Cn e to the power j 8 pi and t, right? What is the task? Both needs to be multiplied and then MST will come out. So basically I need to do the frequency domain analysis, that's for sure, because time domain analysis doing the then MST will be convolved with h of t. So it will be tough. You cannot understand anything from the time domain analysis. That's why we do the frequency domain analysis. So let's do the frequency domain analysis. Before that, let's open up CT. What will be a CT? Put n equals to 0. What you are getting? C of 0. Then put n equals to 1. Then put n equals to minus 1. Then put n equals to 2. Then put n equals to minus 2. Then put n equals to 3. Then put n equals to minus 3. And so on. Can you find out C of f from here? Surely I can find out. C of f. If you remember, what is the Fourier transform of 1? 2 pi del omega. But in case of f, it would be del f only. So what will be the Fourier transform of e to the power j 2 pi f naught t? That would be del of f minus f naught. So what you will write down here? C naught del f. Fourier transform of 1 is del f. So Fourier transform of C naught will be, I should multiply C naught here. So here also it will be multiplied with C naught. So C naught into del f plus C1 as it is. Here what is the frequency content? Here what is the value of f naught? Value of f naught is 4, right? Value of f naught is 4. Basically, what is the fundamental frequency here? That is 8 pi. So what is your f naught? That is 4. This is in radian per second. This is in hertz. E to the power j n omega naught t. So this is the value of omega naught. So del f minus 4 plus c of minus 1 del f plus 4 plus c2 del f minus 8, right? So you guys would have understood what is the sampling frequency here, right? Surely would have understood what is the sampling frequency. Del f plus 8, c of 3 del f minus 12, c of minus 3 del f plus 12. Now I can draw the frequency spectrum as well. I can draw C of f as well, but that is not required. What I need to do, my MSF would be MF convolution with the C of f. So whatever the MF I am having, that will be convolved with this particular thing. So C naught MF plus C1 MF minus 4 plus C of minus 1 MF plus 4 plus C2 m f minus 8 plus c of minus 2 m f plus 8 plus c3 m f minus 12 plus c of minus 3 m f plus 12 and so on. So you are getting the clones again, but this clone is being multiplied with c naught. Then centered at 4, clone multiply with c1. Centered at minus 4, clone multiply with c of minus 1. Centered at 8, clone multiply with c2. Centered at minus 8, clone multiply with minus c2. Sorry, c of minus 2. So all this process will not take much time in the examination hall. I am telling you guys. It will not take that much of time. You will be able to do it very quickly. If you have good enough concept, then you will be able to do it very quickly. You will be understanding what is actually happening here. So you will not have to write down every step there. Once you write down 1 or 2 steps, you should be able to understand what is actually happening. So centered at 0, 0, 2, minus 2. This was your m of f. What you are doing? ms of f. Centered at 0, 2 and minus 2. Right? This will be multiplied with c naught. Then centered at 4. Centered at 4. 2 backward, 2 ahead. That means it will be there at 2 only. 2 backward and 2 ahead. Then centered at 8. 2 backward and 2 ahead. 2 backward and 2 ahead. But I don't know about the amplitude. I am not saying that this amplitude C1, C2 all are same. They can be different. I don't know if C1 is greater than C0 or if C2 is greater than C0. I don't know that. Here I assume that my amplitude is 1. So this 1 is multiplied with C0. This is multiplied with C of 1. This is multiplied with C of 2. The same thing will be happening towards the negative side as well. Minus 2, minus 6, minus 10, minus 8, minus 4. The same thing is happening here. This is C of minus 1. This is C of minus 2. This is your ms of f. Right? Now what you need to do? You need to design h of omega such that yt equals to mt. What you need? Yt equals to mt. In A, you need yt equals to mt. That means your y of f should be equals to mf. So what kind of filter you will design? Directly I can see here. I will design a low pass filter. I will design a low pass filter with minus 2, 2 and the amplitude should be 1 by C naught. This is the h of f I will be designing. Now they can ask you the expression of ht as well. Can you write down the expression of ht from here? When I write down the expression of ht, I always write down in terms of omega. This we have already seen. So this will be 4 pi. This will be minus 4 pi. So sin at by pi t. But the magnitude is C naught. Sin at by pi t. So this kind of spectrum you will be getting. But magnitude is 1 by C naught. So multiply with C naught. So this will be your h of t. Second one is more interesting. What you need? Yt equals to. Look, if you just follow the process, you are able to solve it. And these kind of questions I am telling you, not more than 50 people will be able to solve it. Not more than 50 people combined. Okay, so these kind of questions are very good. 2mt cos 16 pi t. 2mt cos 16 pi t. This is what you need. I told you whenever you see cos in the multiplication in time domain, in the frequency domain, the analysis will be very easy because you know that what cos does in the frequency domain, it will be just shifting it. Why is that so? Because this is your 2mt e to the power j omega naught t plus e to the power minus j omega naught t divided by 2. So this is your 2 pi f naught t. Mt is having Fourier transform of mf e to the power j 2 pi f naught t dot mt will have a Fourier transform of m of f minus f naught. So this is your 2 pi f naught t. That means it is 8. F naught value is 8, right? So this will 2 and 2 is getting cancelled out. So this will have a Fourier transform of y of f will be m of f minus f naught plus m of f plus f naught. Are you able to understand what did I do here? I just calculated y of f. What is my y of f? This 2 and 2 is getting cancelled out. So mt e to the power j 2 pi f naught t. F naught value is 8 here. So m of f minus f naught, m of f plus f naught. So what is my mf? This is my mf. What I require? This is something that I require. So first I am making, what do I require? This is the yf that I require. Basically your mf is centered at 8. mf is centered at 8. And what was the bandwidth? Bandwidth was 2 here. So 8 plus 2, 8 minus 2. This is something that I require, and similar thing will be happening to the negative hand side as well. So this is my yf that is required, and this is my msf that I am having. This is the msf that I am having. So let's copy it on the next page. So what do you think, what kind of filter I should use? What do I require? What do I need? I need this particular thing. This is what I need. Okay. Here I need to tell that your xt is even, because what will happen? What is the issue here if I don't say xt is even? Sorry, this ct is even. This in the question it should be mentioned that it is even. It is even. ct is even. Why is that so? Because if I am designing my band pass filter, if I am designing my band pass filter, then what gain I will keep here? The gain I should keep 1 by c2. Not band pass filter, yeah, band pass filter only. Because this is the part that I require, right? This is the part that, here the gain is 1 only. Here also the gain is 1. But here the gain is c2. So c2 should be multiplied with 1 by c2. And this should be multiplied with 1 by minus c2. And both could be different. c2 and c of minus 2 could be different. Are you able to understand this point? They could be different. But I need c of 2 is equals to c of minus 2. So what I am saying, my ct is even. So from there, what you will understand, what is the exponential Fourier series coefficient of ct, that is cn. What it would be? C of minus n. That means c of 2 would be equals to c of minus 2. So now you can see that what will be your h of omega. The h of omega will be a band pass filter with the pass band gain of 1 by c2. Centered around 8 with the bandwidth of 4. What is the bandwidth? Bandwidth is 4, right? And pass band gain of 1 by c2. Pass band gain of 1 by c2. Centered around 8 with the bandwidth of 4. So this kind of filter you require. So this is the h of omega that I require. Can you write it down in terms of time domain? What I am saying, what will be the time domain expression? What would be your h of t? If you have studied this chapter in a good manner, then you will be able to write down. Surely you will be able to write down. What do you think? What should be the time domain? I am writing it down, okay? You just agree to my point or not. So I am writing it down. So your h of t would be sine 80. Here what we wrote down? The same thing, sine 80 by pi t. Okay, multiply with cos 16 pi t. Okay, multiply with 2 divided by with C2. This should be your HT. How did I write it down? Did you understand? Look, first what did I assume? That at the center I am having some filter. I am having a low pass filter. In the last lecture I told you from low pass filter how do you get a band pass filter. That I told you in the last lecture only. From low pass filter how do you get a band pass filter. So I assumed that there is a low pass filter of bandwidth 2. Low pass filter of bandwidth 2. This it was, right? And then I shifted it. To shift in the frequency domain, what I need to do? To shift in the frequency domain, I need to multiply with cosinusoid. How much I need to shift? I need to shift it by 8 because center was at 0, it should come to 8. So shift it by 8. That means in the omega domain, shift it by 16 pi. So shifted by 16 pi. But whenever you multiply cos, what will happen? By 2 will also come, no? Here divided by 2 will also come. Cos 16 pi t. That means e to the power j 16 pi t. So in the frequency domain, e to the power j 16 pi t divided by 2 plus e to the power j minus 16 pi t divided by 2. So in the frequency domain, del f minus f naught divided by 2, del f plus f naught divided by 2. So gain is divided by 2. So here, if I assumed the gain of low pass filter as 1, so now in the band pass filter, the gain would become 1 by 2. So that's why I have to multiply by 2. So that 2 and 2 get cancelled out. And then divided by C2 because I need the gain to be 1 by C2. So this is the low pass filter that I am having. This is how I need to think. Otherwise, if I am not able to think, then what I will do? I will check all the options and then for all the options, I will draw the frequency response. What I will do in all the options, I will draw the frequency spectrum. And then I will draw the frequency spectrum and then I will match that which of the option is matching with this one. Okay, so this option will match. So this is the final lecture of our Fourier transform. That's why I am bringing everything, whatever that I could. Okay, so we are not going to learn in the conventional way that sampling fs equals to 2fm. Those things don't work. And I will deal the questions of previous year 2024 and 2025 and then you will realize that just fs equals to 2fm, this is what they are not asking from sampling. And every year the question is coming. That's why I thought that this is the topic where I should spend the time. Okay, let's see this question. So this is also not that straightforward, but use your brain, you will be able to solve it. So here I did not draw the block diagram, but in the examination hall, there is very high chance that a block diagram would be there. So MT multiply with CT, you are getting MST and that is going to a filter, you are getting YT. So this is the diagram. MT is given, cosinusoid it is. CT is this waveform. This is CT waveform. Okay. Then you are getting your sample signal and you are getting your YT. So which two questions they are asking? Which of the following frequency component will not be present in the sample signal MST? So first they are talking about MST. So MT is having frequency component of 2 Hz and minus 2 Hz. You can directly see here what is the value of omega naught? 4 pi. I can call it omega m. Okay, because FM I will be writing down. So FM is 2. So MT, that means M of F, is having 2 and minus 2. And minus 2, right? Whatever the amplitude is, I don't care because in the first question what they are asking, they are only asking that they are only talking about frequency, so I don't care about the amplitude. Amplitude I am writing down A only. It is being multiplied with the CT. That means you need C of F. What will be your C of F? CT is a periodic signal. CT is a periodic signal that will have some Cn. So what will be your C of F? Your C of F would be n goes from minus infinity to infinity. How to write down the Fourier transform of a periodic signal? How to write down Fourier transform of a periodic signal? Cn, and it will have the impulses at discrete frequencies. Here what is the time window? Here what is the time period? Time period is T naught. So here I should write F naught. So at all the discrete frequency, it will have the impulses of area Cn, right? But what is the value of Cn for this one? that I need to calculate. Will I apply the differentiation property? Absolutely not, because I told you, you can find out using Fourier transform, you can find out the Fourier series coefficient Cn as well. For that I told you a trick. What was the trick? What was the trick? Trick was you write down your Fourier transform of this particular signal in one time window. In one time window, in this time window, minus t naught by 2 to t naught by 2. In this time window of t naught, what kind of signal you can see? Triangular signal. So that signal is 2 triangular t minus center upon width of one side. So it will have a Fourier transform of a2 sampling of omega 2 by 2. Then what did I tell you? For finding Cn, what you need to do? Divide by t naught, and omega should be replaced with n omega naught. Right? So what we are getting? 2 by 3 sampling of n pi by 3. So this is the value of Cn for this particular waveform. What is the value of Cn? 2 by 3 sampling of n pi by 3. This is the value of Cn. So here we will put this value, right? But here there will be some absent frequencies, no? In this Cn all the frequencies will be present. No. What I mean to say is that here there will be some absent frequency. Basically f0, 2f0, 3f0, 4f0, 5f0, everything will be present. No. Because C of n could be 0 as well, no? What will be your CF? Your CF is, put n equals to 0 here, C0 del f, C1 del f minus f0 plus C2 del f minus 2f0 plus C3 del f minus 3f0. In that manner it will keep on going. C of minus 1 del f plus f0, C of minus 2 del f plus 2f0. Then what will happen? C of f will be convolved with m of f. So what I will get? Ms of f would be C of f will be convolved with m of f. So what I will be getting? Everything same. These expression only I will be getting. Just del will be replaced with m. Nothing else. Same expression I will be getting. Ditto same expression I will be getting. So ms of f. So what will happen? This dial will be replaced with m. Or you can say C of minus 3 m f plus 3 f naught. Then you are thinking that clone of mf should be there, centered at f naught, centered at 2 f naught, centered at 3 f naught, centered at minus f naught, minus 2 f naught, minus 3 f naught. But what if this is 0? Then that clone will not be present. What if this is 0? When we were sampling with impulse train, in the impulse train you notice one thing. What is that? That in the impulse train, where is the impulse train? Yeah, in the impulse train all the frequency components are present. Fs, 2fs, 3fs, 4fs, 5fs, 6fs, 7fs, everything is present. But it's not necessary that in every periodic signal all the frequency component would be present. We have solved these kind of question. What all are the absent frequency component? So in this particular waveform, the absent frequency components could also be there, no? And what all frequency components are absent? For that I need to find the value of Cn, and that I find out. And from here I can get to know that when this will become 0, when this is a multiple of pi. So that means C of n will be 0. C of n is 0 when your n is equals to 3, 6. If you put 6 here, it will be 2 pi. If you put 3 here, it will be pi. So sampling of pi will be 0. Sampling of 2 pi will be 0. Sampling of 3 pi will be 0. So 3, 6, 9, and in that manner. That means C3 is equals to C of minus 3 is equals to C of 6 is equals to C of minus 6 is equals to C of 9 is equals to C of minus 9, and so on. All these are 0. So basically what you expected, that MF will come as it is. Yes, C0 is non-zero, C1 is non-zero, C2 is non-zero, C of minus 1 is non-zero, C of minus 2 is non-zero, but this term is gone. This term is gone. So what you initially expected, that what all are the components? 2 and minus 2. So 2 would be there, then center will move to F0 plus minus 2. Center will move to Fs, 2 backward, 2 ahead. Center will move to 2Fs, 2 backward, 2 ahead. Then center 2 backward, 2 ahead. Then center will move to 3Fs, 2 backward, 2 ahead. But this component is not even there. The clone will not even be there. When you were sampling with the impulse train, at that time you did not care about the clone because you know that all the clones will be present. But now you are sampling with respect to this particular waveform. And in this particular waveform, when you find out the Fourier series coefficient, you got to know that 3F0 component is not even present. 6F0 component is not even present. So what all components will be present? This 2 Earth will be present. F0 plus minus 2 will be present. 2F0 plus minus 2 will be present. 4F0 plus minus 2 will be present. 5F0 plus minus 2 will be present. 7F0 plus minus 2 will be present. 8F0 plus minus 2 will be present. And then 10F0 plus minus 2 will be present. Say yes or no. What is the value of F0? What is the value of F0? T0 is given as 0.2 seconds. So what is the value of F0? F0 will be 1 by 0.2, that means 5 Hertz. So F0 value is 5 Hertz. So 5 plus minus 2, that is 7 and 3. Here, what is the scenario? 10 plus minus 2. Here, what will be the scenario? 20 plus minus 2. Here, what is the scenario? What is the value of F0? 5. So 25 plus minus 2, 35 plus minus 2, and so on. So what you are getting? 7, 2, 7, 3, 12, 8, 22, 18, 27, 23, 37, 33. So what all are not present? 8, 17, 28 is not present, I guess. 28 is present anywhere. 17 is also not present. 17 is not present, will not be present. 8 is present. 8. Can you see 8? Yes, 8 is present. Can you see 17? 17 I cannot see. 28 can you see? 28 also I cannot see. 38 can you see? Till 38 we did not reach. Till 37 only we are there. Then what is the value of F0? F0 is 5. So 40 plus minus 2. So what we are getting? 38, 42. So yes, 38 is also present. Right? But we have reached the point of 28 and 17 because we have gone ahead. 37, 33 we have gone to till this point. So what does that mean? Here 6F0 plus minus 2 would come, no? So what is the value of 6F0? F0 value is 5. So 30 plus minus 2. That means from here you would have got 32 and 28. Which would be present if you are sampling with impulse train. But you are sampling with this particular thing. So 28 will not be present. So both of them will not be present. 32 will also not be present and 28 will also not be present. And from here what would come out? 3F0 plus minus 2. What is the value of F0? 5. So it will be 15 plus minus 2. That means 13 and 17 both will not be present. But if you are sampling with impulse train, they will be present. But here 13 and 17 both will not be present. Are you able to understand this point? So if you are sampling with the random periodic signal, so you need to take care of Cn. That if Cn is not there, that means that particular frequency component is not even there. And if that particular frequency component is not even there, what does that mean? That means the clone will not be made. The clone of MF will not be centered about that particular frequency. And if clone is not even there, then in MSF, that frequency will not even come into action. Right? Next, what they are saying, for the recovery of MT, you are using a low pass filter. What should be the pass band gain of that filter such that Yt is equals to MT? This is my MF, right? This is my MSF. So can I draw the diagram of MSF? Draw the diagram of MSF. Because MSF will be passed through a low pass filter. This is what they are saying. So in MSF, what you are having? C0 into MF. C0 into MF. C0 into MF. Then centered around F0. And it is there from 2 to minus 2. 2, 2 minus 2. What is the value of f naught? F naught is 5. So this is centered around 5. 2 backward and 2 ahead. 2 backward, that means 3, and 2 ahead 7. 2 backward is 3. 2 ahead is 7. Two backward is 3, 2 ahead is 7. The same thing is happening here as well. Now you need to use a low pass filter to get your MF. This was your MSF. This was your MSF. Now to get your MF, you need to use a low pass filter. So this point is actually minus 3. So what kind of filter I can use? This kind of filter I will be using. Minus 2 to 2. But they are not asking about the cutoff frequency. What they are interested in? They are interested in this amplitude. What will be this amplitude? That would be 1 by C naught. The pass band gain should be 1 by C naught. This will be your low pass filter. The pass band gain should be 1 by C naught, because C naught should be multiplied with 1 by C naught, so that you get your MF back. Because MF was having, okay. This was actually, this was not band limited, no. This was not band limited. They were having the impulses at 2 and minus 2. So this was not band limited. Really sorry for this error. They were having the impulses at 2 and minus 2. 2 and minus 2. Then they will have the impulses at 3 and 7 as well. So they are just having the impulses, nothing else. So I only care about this one. Initial area was A, but that was multiplied with C naught. Initial area was A, but that was multiplied with C naught. Initial area was A, but that was multiplied with C1. Initial area was A, that was multiplied with not C1, C of minus 1. But I have made sure that C1 and C of minus 1 are same. So C of minus 1, C of minus 1. Here C1, C1. But I don't care about all these things. I only care about these guys. So initial area was A here. Initial area was A, and that I require. So that means this pass band gain should be 1 by C naught. So this pass band gain should be 1 by C naught. So what should be the pass band gain? That should be 1 by C naught. But I need the numerical value. So from here I can find out the value of C naught. What will be the value of C naught? So directly you can see that value of C naught is 2 by 3. Because sampling of 0 is 1. Sampling of 0 is 1. Because sin t by t at t equals to 0, it will throw 1. So what is the value of Cn? What is the value of C0? That is 2 by 3. So here it would be 3 by 2. So what is the answer? 1.5. So pass band gain should be 1.5. Those who are able to solve this question, congratulations to them. They are doing very good. And even if you are not able to solve, still it is okay. But these kind of questions could be coming in your future. Okay, in the future, certainly these kind of questions can be introduced in your examination. So always take care. It is not necessary that always impulse train would come. Any periodic signal can come. Any periodic signal. Look, this is not a general process of sampling. Okay. Mostly we can use square wave. Square wave is used. But triangular wave is not used. But who knows, theoretically they can make the question. No? Theoretically they can any way make the question. Right? Okay then. This is the gate question. And this is also a gate question. Two good questions are there. This is easy. I would say this is easy. But in this question, we will make one good conclusion and we will see something very intuitive as well. So I guess you will be able to solve this one if you have watched the previous video. So here two concepts will be used. The LTI system one along with that sampling concept. Both concepts will be used here. Okay, and then you need to find out the expression of x naught t and then go to this one. You try doing it on your own. Think about it. What should be the answer? A, B, C, D. I gave the solution of this particular question wrong. Okay, when this came out, but in the whole gate industry, everyone gave it wrong. and I was the first one to bring the correct solution. So I don't really feel bad about it. Although I feel bad about it, but no one else gave the correct answer. So I was the first one to bring the correct answer. And when the answer key came, people were saying that we will challenge it. Okay, we will challenge it. They were saying at the end. At that time, I had already made the solution, but it was disappointing that in the first go I solved it wrong. So what is the new thing here? The whole process is same. Just there is a shift. Your impulse train has been shifted. So what do you think? This is my empty, and I sample my empty with the shifted impulse train. So initially I used to collect the sample at 0, TS, 2 TS. Let's just say I shifted it by TS by 2. So now I am collecting the samples at TS by 2, 3 TS by 2 and 5 TS by 2. So when I recover my message signal from these samples, will my message signal will be shifted? This is my message signal. Initially I was collecting the sample here, here and here. Now I shifted my impulse train. That means now I am collecting the samples here, here and here. Now when I try to recover my message signal, I will recover in this manner only. So it can never be shifted. It can have some different phase, phase can be changed, but your empty can never be actually shifted. Are you able to understand this point? There is no chance that it should be shifted. That means these options are gone. Only two options are left, FT and TS of FT. But they are having these different frequencies, sampling frequency. So a sampling frequency you already know, Fs should be equals to FM, because here they are using the ideal filter, so there is no problem of the filter. So Fs should be greater than or equals to 2 FM, so you will be able to write down the answer, option A. But we will see the complete process in the frequency domain analysis. We will see just the intuitive way I have told you, that even if you shift your impulse train, so that doesn't mean your message signal will be shifted. Are you able to understand this point? So there is no chance that you can get M of t minus 2, or here it is Ft. So there is no chance that you can get F of t minus 2. If you want F of t minus 2, that means something you need to do with your filter. Then only you can get your M of t minus 2. But just by shifting your impulse train, that doesn't mean you will shift your message signal as well. That will not happen, because it is very simple. Even previously you were calculating your samples here, so the same kind of message signal you will get. And if I am calculating the sample after shifting a bit, that means if I calculate my sample at 0.5 second, 1.5 second, 3.5 second, 2.5 second, that doesn't mean I will receive some different signal or shifted signal. No. Yeah. So this was the question which we will do, which we will solve. Surely we will solve. Try this one. Here the concept of filter will also be used, and here the concept of sampling will also be used. So try doing this one as well. Here two possible answers are there. This one and this one. So try doing it on your own. I will take a pause and then I will come back. Yeah, welcome back. So did you guys try this one? Continuous signal xt is there, sampled at a rate of 15 hertz. And so what is really happening? So here they have given xt sampled at 15 hertz. Sampled with what? They did not give it, right? So by default you have to assume that it is impulse train. By default you need to assume it is an impulse train. Look, you can sample with any random periodic signal, but impulse train is the most conventional one. Like impulse train only is used for sampling, so you have to assume it is impulse train only. Even though they did not give it, still you have to assume this is impulse train. So they are sampling with impulse train. Sampling frequency is 15 hertz. Then you get your xst. So basically your xst would be, sampling means you are multiplying your xt with ct. Then you need to find your xs of f. That would be x of f convolution with c of f. Then this signal will be passed through a LTI system, or you can say this signal will be passed through a filter whose impulse response is given. Then you will receive your output x naught t, right? So that output x naught t you need to find. So this is the simple process. Like whatever the conventional process is there, everything you are doing the same. So you know everything about it, just you need to solve it. The important part is this time there is a shift in the input, along with that there is a shift in the filter. So just by looking at the expression of the filter, can you tell what kind of filter it is? Band pass filter, right? Sine 2 pi t divided by pi t. So this is a rectangular pulse. I should not say rectangular pulse. In the frequency domain, it will be rectangular, and then multiply with cos 38t. That means it will be shifted left and shifted right. That means it will become a band pass filter. This we have already seen in the previous video. So there is a band pass filter. The important part or the different part is there that you are having a shift here, nothing else. Only there is a shift of pi by 2, nothing else. Okay, so you will be feeding x s of f, then h of f would be there, and it will give you x naught of f. So what will be this x naught of f? That you need to find. So what is our simple process? We will draw the frequency spectrum of x of f. So what will be the frequency spectrum of x of f? So can you draw the frequency spectrum? Surely I can draw the frequency spectrum. So in the frequency spectrum, I will be having impulses at the fundamental frequency. What is the fundamental frequency? From here you can see that fundamental frequency is 4 Hz, right? Fundamental frequency is 4 Hz. How I can see it? 8 pi. 8 pi is omega naught. Omega naught is 8 pi. So what will be your f naught? That would be 4 Hz. So f naught will be 4 Hz minus 4 Hz. Do I care about the amplitude? Absolutely not. I don't care about anything else. I don't care about the amplitude. I can see the shift. Phase shift is e to the power j pi by 3. And here it would be negative. So this I already told you. Whatever the shift that is given, that you need to give to the positive frequency. And in the negative frequency, just the negative shift would be there. Whatever the shift that is here, it was plus pi by 3. So here to the positive frequency, I will give plus pi by 3 shift. And to the negative frequency, just negative of this I will give. In place of pi by 3, if minus pi by 3 was given, so here I would have put a minus sign and here I would have put a plus sign. But this time it is plus pi by 3 is given, so plus pi by 3 I have put. So this we have already proved in the last lecture. Then it is sampled with the impulse train with the sampling frequency of 15 Hz. Okay. So what will happen? The center will move to 15. Center will move to 15. So these impulses will come as it is. These impulses will come as it is at minus 4 and 4. These impulses will come. Then center will move to 15. So 15 minus 4, 11. 15 plus 4, 19. Right. Similarly, here also this process would be happening. So this is 0, 4, minus 4, 11, 19, minus 11, minus 19. And surely your amplitude will be multiplied with fs. So fs into a e to the power minus j pi by 3, fs into a e to the power plus j pi by 3 plus j pi by 3. Now this part would have been shifted here. That means this part would be of 11 Hz frequency. Basically center would have moved here. That means this minus 4 would have moved to plus 11. So this would have been fs into a e to the power minus j pi by 3, fs into a e to the power plus j pi by 3. Right. Similarly here as well, you can just see it will be carbon copy, nothing else. Right. So here what you will get at minus 11, you will get fs into a e to the power minus j plus pi by 3, and at plus 19 what you will get, minus 19 what you will get, fs into a e to the power j pi by 3. Now what is happening after that? There is a filter. So you need to make the frequency spectrum of this ht. Right? Can you make the frequency spectrum of this ht? Yes, surely you can make it. So first I will look at this particular. Let's write down the expression. This is your ht, right? I am calling this as pt. What I am calling? I am calling this as pt. So what I can write down? pt into e to the power j 38 pi t e to the power minus j pi by 2, right? Then divided by 2 plus pt into e to the power j minus 38 pi t e to the power j pi by 2 divided by 2. Are you able to understand this point? E to the power j theta plus e to the power minus j theta divided by 2. So j theta, so this come as it is minus j theta divided by 2, right? So what you are getting? This is a constant phase which is coming out. So e to the power minus j pi by 2 divided by 2. This is a constant phase that is coming out. P of f minus f naught. What is the value of f naught? 19 plus e to the power j pi by 2 divided by 2 P of f plus 19. Is that clear to you? Have the patience in these kind of questions and you will be able to solve. Can you draw the frequency spectrum of sine 2 pi t divided by pi t? Yes, I have told you. Sine 80 by pi t. Sine 80 by pi t. So it will go from minus 2 pi to 2 pi with the gain of 1. But this is in terms of omega. So in terms of frequency, it will be divided by 2 pi. So actually it will go from minus 1 to 1. Minus 1 to 1. But actually what will happen? It will be shifted. Actually it will be shifted. So it will be shifted at the center being 19. So at the center being 19, it will be shifted. So 19, this point will be 18 and this point will be 20. So from 18 to 20, it will be non-zero. So it will be non-zero between 18 to 20. So what kind of filter you will be getting? This kind of filter you will be getting. I hope all these process is clear to you because we have solved a lot of questions. So now everything should be clear to you. Here the important part was what should be the magnitude? What should be this magnitude? That was the important part. Now question has just become a cakewalk, nothing else. So this was 19, 18, 20. How did we get to know that? This will be going from minus 1 to 1 and now it has been shifted to 19. That means center has shifted to 19. So 19 minus 1, 19 plus 1 and with the gain of e to the power minus j pi by 2 divided by 2. So e to the power minus j pi by 2 divided by 2 and here you are having e to the power j pi by 2 divided by 2, right? This point is minus 19, minus 18, minus 20. H of f multiply with x of f because what is your what is your x naught f? That is x of f multiply with h of f. So this signal will be multiplied with this signal. So what do you think which frequency component will pass? This frequency component will pass and from here this frequency component will pass, right? Are you able to see which frequency component is passing? This frequency component is passing and from here which frequency component is passing? This frequency component is passing, right? So let's see what will be your x naught f. So in x naught f you can see that x naught f is fs into a e to the power j pi by 3 into e to the power minus j pi by 2 divided by 2. Fs into a e to the power minus j pi by 3 Fs into a e to the power plus j pi by 3 actually. The phase shift is plus j pi by 3 and here it is minus j pi by 2. Into e to the power minus j pi by 2 divided by 2, right? And what about here? This point is 19, this point is 19 and this point is minus 19. So Fs into a divided by 2 e to the power minus j pi by 3 plus e to the power j pi by 2. This is e to the power j pi by 2 divided by 2 and here also the same thing is happening. So initially I am saying that my amplitude was a. Now the amplitude has become fs by 2 into a. Along with that, what is the shift? Pi by 2 minus pi by 3. Here pi by 2 minus pi by 3 and here pi by 3 minus pi by 2. So what do you think what should be your x naught t? X naught t. Initially whatever the amplitude was there, that was there into fs divided by 2. Cos frequency 38 pi t. 38 pi t. Now I told you whenever you write down the phase, always look at the positive frequency only. So what is the phase? Plus pi by 3 minus pi by 2. We have proved this point in the last lecture. In the last lecture, I told you that whatever the phase is given, that you give to the positive frequency. And from here, if you need to write down your signal, how will you write down? A cos frequency 8 pi t plus pi by 3. There you go. So 8 cos pi t plus pi by 3. And this amplitude A was 2, right? So here A was actually 2. Basically, this point will not be 2, right? Because here actually the amplitude is 1 by 2. So that will be multiplied with 2. Whatever that is happening, I don't care. Are you able to understand what I am saying? Why I wrote A here? Because this is my input signal. Now something is happening with the input signal. What is happening? Input signal was multiplied with Fs. Initially my input signal was multiplied with Fs. So same thing will be happening in the time domain. Now after that it is multiplied with 1 by 2. Along with that it is given a phase of minus pi by 2 as well. Right? So initially it was having a phase of pi by 3. It is given the phase of minus pi by 2 as well. It is multiplied with Fs into Fs by 2. So initially whatever the amplitude was there, that amplitude have been multiplied with Fs by 2. So here instead of writing A, I should have written whatever the initial amplitude was there, that has been multiplied with Fs by 2. So whatever the initial amplitude was there, which was 2, has been multiplied with Fs by 2. So 2 has been multiplied with Fs by 2. So what is the value of Fs? That is 15 only. So what you are getting? 15 cos 38 pi t minus pi by 6. This is your x1 of t. So are you able to understand? We have used the last lecture here. A very, very important concept. Look, it's not that important, but it has just solved a few steps. This you would have to derive. In the examination, if you don't know the process, that whatever the shift is there, that shift you need to give to the positive frequency. If you don't know it, then you need to derive it. Within 50 to 60 seconds, you will be able to derive it as well. After that, it is simply sampling. Simply we are sampling it. Then there is a filter, simple filter. Here we derived it only because here we don't remember any expression. Okay. So this I already know. This was a low pass filter which have been multiplied with cos. That means low pass filter have been shifted right and shifted left. What does that mean? That means surely it will become a band pass filter. Then I know that it is centered around 19. It is giving us a phase of e to the power minus j pi by 2 to the positive frequency. To the negative frequency, it is giving a phase of plus pi by 2. So now in the positive frequency, already there was a phase of pi by 3. Now we are getting minus pi by 2 as well. So 60 minus 30, it would be, 60 minus 90, it would be minus 30. So this is what we are getting. One thing we already know, sine 90 plus theta is equals to cos theta. So this can be written as, so basically whatever the theta is, that can be replaced with 90 plus theta when I write down sinusoid. So when I write down sinusoid, whatever the theta was there, that can be replaced with 90 plus theta. Okay. So 15 sine 38 pi t plus pi by 3. So this is also a possible answer. So which answers are possible? A and C. Okay, very simple process. Just follow the process and you will be able to write down the answer. And these questions are considered one of the finest question of the question paper. One of the finest problems. Okay, one of the best problem of the GATE examination. Like of the GATE 2024 examination. So this was a very good question and you are very easily able to solve these kind of questions. Everything is coming from the class note itself, right? What about this one? Again, there is a standard process, D2 standard process. Nothing new is there. Just whatever the new is there, what is that? In place of impulse train, usually we have an impulse train starting from t equals to 0. But now this is starting from t equals to tau because there is a right shift of tau. So this used to be our impulse train. This used to be our impulse train. But now this is our impulse train. So this I have already told that if it is sampling an empty signal, it doesn't mean that empty will be shifted. surely MT will not be shifted. It is just that initially I was collecting the sample at 0 second, 2 second, 4 second, minus 2 second. Now I am collecting the sample at 1 second, 3 second, 5 second, minus 1 second. So phase of MT can change, but MT cannot be shifted. So MT will not be shifted here. So that means surely B and C will not come. So let's understand it with the frequency domain analysis. So I can draw the what is written, a continuous time finite energy ft signal is there whose Fourier transform vanishes outside the frequency interval minus omega c, where omega c is in radian per second. That means ft is band limited to omega c. This is what they are saying. Now it is sampled with the pulse train or impulse train pt, which is given by delta t minus tau nts, with delta being the direct delta function, ts is greater than 0, tau is greater than 0. Sampled yt is passed through a low pass filter. So this is the low pass filter. So again a very standard low pass filter where omega c is the cutoff frequency and ts is the pass band gain. Very standard low pass filter it is. You need to find the output of the filter and also you need to find the sampling frequency as well. So let's draw the diagram of filter here only. So filter is very standard. This is the filter. Look, they have mentioned everything in omega c, so let's make it h of omega only, because they have mentioned in omega c only, so let's make it h of omega. So sin at by pi t, what is the value of a? Omega c. So sin at by pi t, omega c is getting, omega c and omega c is getting cancelled. So what is the pass band gain? That is ts, and this they have already written. The pass band gain is ts and cutoff frequency is omega c. This they have already written. Now usual process is there. What is the usual process? That you get a sample signal which is xt, this time it is ft. So you get a sample signal fst, which is the multiplication of ft with ct, and then you get your output yt I am calling, that will be fst convolution with ht, right? So first let's find out fst. So what will be fst? Fst will be ft dot ct. In the frequency domain, what it will be? fs of f would be f of f convolution with c of f. F of f I can easily draw, it is band limited to omega c. What will be my c of f? So that I need to draw. In place of c of f, this time they are using pt. What they are using? They are using the term pt. So p of f. So this is my f of f, pt is given. I am assuming another signal ct, which is our standard signal. This is our standard signal, right? This is our standard impulse train. And I know what will be c of f for this one. That would be fs, n goes from minus infinity to infinity, delta of f minus fs. Say yes or no, right? Ts is given, so Ts is 1 by fs. Basically Ts is 1 by fs. What is your pt? Your pt is ct minus 2. Do you agree to this point? In place of t, if you put t minus 2, then you get your pt, right? What is your pt? C of t minus 2. So what will be your p of f? P of f would be e to the power minus j omega 2 c of f. So what you will be getting? Fs into e to the power minus j omega 2, or you can write down 2 pi f 2 minus infinity to infinity del of f minus nfs. This is what you will be getting. What is the next task? Next task is to do the convolution. So what will be your f of f, fs of f? That would be f of f convolution with p of f. Now this is a function of f, right? This is also a function of f. You cannot take this outside. what I mean to say is that I will convolve f of f with fs e to the power minus j 2 pi f tau, and then this summation. Can I write down this in terms of c of f? I am writing it down as c of f. If I write it down as c of f, that means this fs will be 1. So basically this is the scenario, right? What is your pf? Pf is e to the power minus j 2 pi f tau c of f. You are convolving, if I say I convolve gt convolution xt dot ht, if this is the process, can I take this xt outside? No. This is a function of f. This is also a function of f. They are being multiplied. After that they are convolved. So first I need to solve this multiplication. A very important part of this question. If you don't think it intuitively, if you have thought of intuitively, then you will be able to write down the answer A. But if you are going through the complete process, so what did you understand here? That you need to multiply e to the power minus j 2 f tau with c of f. This is the first task. After that you will do the convolution. And here only everyone did the mistake. Even the AIR1 also did not attempt this question. I asked him whether he attempted it or not. So he also left this question. Rank 1 I am talking about. So I don't think any other guy got this question correct. Any guy in the examination all got this question correct. It might happen by luck he would have got it correct, but conceptually I don't think anyone got it correct. So what is the scene here? E to the power minus j 2 pi f tau is being multiplied with c of f. So first you need to do the multiplication. So let's do the multiplication. So this multiplication I need to solve. So basically what is p of f? So my p of f is fs, common part is there, whatever it is I don't care. So let's put this fs downward, because this is the constant value. fs is a constant value that I don't care. So now e to the power minus j 2 pi f tau, e to the power minus j 2 pi f tau. Let's open this impulse train. So this impulse train is del f plus del of f minus fs plus del of f plus fs plus del of f minus 2fs plus del of f plus 2fs and so on. If you multiply any function with del f, x of f del f minus f naught, what will happen? This is equals to x of f naught del f minus f naught, right? This goes here. So similar thing will happen here. E to the power minus j 2 pi f tau will be multiplied with del f. So e to the power minus j 2 pi f, in place of f what you will put? F minus 0 tau into del f, plus e to the power minus j 2 pi, in place of f what you will put? fs del f minus fs, plus e to the power j 2 pi fs tau del f plus fs, and so on. In this manner it will keep on going. So what you are getting? Pf is equals to fs into, this would become del f plus what this would become? Del f, because e to the power 0 would be 1 only. Then you are having e to the power minus j 2 pi del of f minus fs plus e to the power j 2 pi fs tau del of f plus fs, then e to the power j 4 pi. Basically here in place of f you will put 2fs, in place of f you will put 2fs. So e to the power j 4 pi fs tau del of f minus 2fs plus e to the power minus j 2 pi 2fs, that means again 4 pi fs tau del f plus 2fs and so on. Now what is the scenario? Your f of f, that will be the convolution. Look, it might seem like, sir, this is very big, but in the examination all these steps will not take time. If you have just come here directly, you will write down this step, right? Del f convolution with f of f, what that would be. So fs is common, so what you will be getting, f of f plus, is this a constant value? Surely it is a constant value. Shift is constant, phase is constant, pi is constant, 2 is constant, everything is constant. It is a constant value only. Are you able to understand this point? E to the power minus j 2 pi fs tau, it is a constant value. Why is that so? Because fs has been shifted here. No, it was a function of f, but in place of f you are putting a constant value of fs. You are putting a constant value of fs. You are putting a constant value of 2fs. You are putting a constant value of minus 2fs. So this has become a constant value now, right? So e to the power minus j 2 pi fs tau, this is a constant value. Now your m of f will be convolved with del f minus fs. So what you are getting, f of f minus fs. So basically what is the scenario here? The same process is happening. Ditto the same process is happening. Nothing new is happening here. If you draw the diagram, what we are getting the clones only. Same clones we are getting, nothing new is there. But the difference is, this time I am assuming sampling frequency to be fs. So this is 0, and it was band limited to fc, right? It was band limited to fc. It was band limited to fc minus fc. Now what is happening? Centered at fs, fs minus fc, fs plus fc. Centered at 2fs, 2fs minus fc, 2fs plus fc. Centered at minus fs, so minus fs plus fc, minus fs minus fc. But now this is having a 0 phase, only the multiplication here will be of fs, but here this will be multiplied with this factor. This clone will be multiplied with e to the power minus j 2 pi fs tau. Next clone will be multiplied with e to the power minus j 2 pi 4 pi fs tau. Basically here what will happen, e to the power negative frequency, so negative, it would be negative, no, here it would be positive. This phase would be positive, this first phase would be negative only, because e to the power minus j 2 pi f tau is there. So 2fs will be put here, 2fs will be put here, so it would be positive only, sorry, it would be negative only. So here what will come, e to the power minus j 2 pi fs tau. Here what will come, fs into e to the power j 2 pi fs tau would come. So this is the scenario now. Now what you are using, you are using this low pass filter, right? And then you are getting your final output. So what you are using this low pass filter, which is having a gain of Ts. So this particular function, which I should have made already on next page only, this will be passed through a low pass filter, which is having a frequency response something like this, frequency spectrum something like this. Minus fc, and here amplitude is Ts. So now what will happen? H of f will be multiplied with x s not x, it is fs of f. So what will be your output? Output of the filter. So output frequency response will be given as fs of f dot with h of f. So both will be multiplied. So what will come out? This thing will come out, which is same as m of f only. Are you able to understand this point? What will come out? This will come out. Fs into Ts will be 1. So this will be minus Fc, this will be plus Fc. Fs into Ts will be 1, minus Fc plus Fc. This is your output of F versus F. Right? This has come out. But important part is filter is good. Filter is good. It is taking minus Fc to Fc. So filter is fine. No issue with the filter. But we need to avoid the aliasing. That means Fs minus Fc should be greater than Fc. So Fs should be greater than 2Fc. But what they are asking us to find? Ts. That too in terms of omega. So what I will do? 1 by Fs should be less than 1 by 2Fc. This I took the reciprocal. What is 1 by Fs? That is Ts only. Should be less than 1 by 2 omega c by 2 pi. So what we are getting? Ts should be less than, here equal sign would be there, less than or equals to pi by omega c. So this answer I would have already got. So what we are getting? F of t only. So what is this? What will be the inverse Fourier transform of this one? That is f of t. Inverse Fourier transform. That is f of t only. Now some people will be having the doubt that, sir, what if the filter was something like this? What if it was a band pass filter? Will we be getting m of t minus 2? Answer me. Will we be getting f of t minus 2? Here we are getting ft, no doubt about that, because here there is zero phase, but here there is some phase. So will we be getting f of t minus 2 if there was a band pass filter? Absolutely not. What will be the Fourier transform of f of t minus 2? What I am saying, what will be the Fourier transform of f of t minus 2? That would have been f of f e to the power minus j 2 pi f2. 2 pi f2, function of f. This is not a function of f, this is a constant phase. This is a constant phase, nothing else. Are you able to understand this point or not? This is a constant phase, nothing else. So if I was using a band pass filter, what I am writing? If this was your h of f, centered fs, so fs plus fc, fs minus fc. This point is minus fs, so minus fs plus fc minus fs minus fc, right? And what if this was h of f with the gain of ts only? What we will be getting? We will be getting these two clones with the peak value of 1 and with the phase of e to the power j 2 pi fs2, e to the power j minus 2 pi fs2. So what we will be getting? what would have been our output? So this is here, this is having a phase of e to the power minus j 2 pi fs2, e to the power minus j 2 pi fs2, right? This is centered at fs, fs minus fc, fs plus fc, and here you are having e to the power j 2 pi fs2, fs minus fs plus fc minus fs minus fc. What will be its time domain value? This would have been your output f. What would have been its time domain value? What do you think? F of t into cos 2 pi fc, sorry, cos 2 pi fs t minus 2 pi fs 2 into 2. This would have been your output. How did I write it down? I assumed there was this thing at the origin that has been shifted to fs. That means it would have been multiplied with, surely it would have been multiplied with cos 2 pi fst. Then only it would have been shifted. No? Along with that, there is a phase as well. Along with that, there is a phase as well. Here, in the last question, in this particular question, what was your h of t? At the origin, there was something that has been shifted to cos 38 pi 3. That means that has been shifted to 19 frequency. Along with that, there is a phase of minus pi by 2. So only at the positive frequency I looked. Same thing I did here. Same thing I did here. F of t shifted to, basically this would have been your fs, no? This would have been your f of f. This would have been your f of f. This would have been your f of f. So f of f have been shifted to fs frequency. F of f have been shifted to fs frequency. That means cos 2 pi fs t. Along with that, there is a phase of minus 2 pi fs2. Minus 2 pi fs2. But because of the cosinusoid, 1 by 2 factor would come. Because of the cosinusoid, 1 by 2 factor would come. So here, if I don't multiply with 2 here, so here the amplitude will be divided by 2, divided by 2. So multiply by 2 also I need to do. So that this 2 gets cancelled. So that this 2 gets cancelled. Are you able to understand this point? So there is no chance that you will be getting a shift. Here also you are not getting a shift. You are getting 2f of t multiplied with the cosinusoid. So again you did not get any shift. F of t minus 2 you can never get. How you can get t minus 2? What you can do is that in this filter, this was your h of t, no? Where was your h of t? This was your h of t. In this h of t, in place of t, you put t minus 2. Basically, if your filter is h of t minus 2, then only you can get the shift. Because what do we know? What will be happening? Fs of t convolution with h of t is happening. But if I put t minus 2, then what will happen? Fs of t convolution with h of t minus 2. So whatever the result previously you were getting, that result will be shifted by 2, no? Let's just say here fs t convolution with h of t, I was getting some yt output, and that I have already seen what yt output I was getting. That was equals to ft only. But if I need f of t minus 2, so f of fs t as it is, h of t minus 2, that would be y of t minus 2, because whatever the shift that is happening, the same shift would be exposed to output as well. This property we have already seen. So you need to give the shift in the time domain of your filter. So in the filter, if you are giving the shift, then only you will have the shift in the output. If you are just shifting your impulse train, that doesn't mean your output will be shifted. And intuitively, very easily, you are able to think that if I am calculating the sample at different time instant, initially I was calculating at 0, 2, 4, 6. Now I'm calculating at 1, 3, 5, 7. That doesn't mean my input will be shifted. That doesn't mean my message signal will be shifted. Message signal will be there as it is. Message signal is not shifted. Only my impulse train is shifted. I am just calculating the sample at different time instant. Are you able to understand this point? Right? So yeah, everything regarding this question we have seen. Every possible thing, whatever that could be asked, that we have seen. This was a very good question, and I still regret that I matched it up when I was making the solution, because if within I guess 10 hours I made all the solution, all the questions I collected. Like collecting the questions from a student first, that is a very typical task, that you need to collect the question. So from the students you collect all 65 questions and then you make the answer. So our channel was the only platform who came up with the next day only, who came up with the all 65 questions and answers, and only this question was correct. Rest only this question was wrong. Rest all 64 were correct. Right? So only this platform was there, only this platform, and other platform are having, what do I call them? Forget about it. This question I matched up at that time because I did not think that phase should be shifted. But next day somehow I got to know that I have matched it up, and next day only I made the solution. So one day I did it wrong and the next day I made the correct solution. But the question paper came after 20 days of examination. Question paper came after 20 days of examination, and some big institutes were giving the solutions of question paper, and there also they did it wrong. Like after the 20 days of examination that has taken place, right? Examination has taken place 20 days back, and now they are making the solution, and still they are doing it wrong. Even after 20 days they are not realizing their mistake. That is something disappointing. Not saying that they are doing it wrong or whatever, I'm not commenting on that, but just telling that if we have matched it up, then other people also have matched it up. I should not be proud of it, but if something that is making me feel a bit better, then it could be that thing only, that at least everyone matched it up, not only me. Okay. Yeah. So in the examination as well, I would have matched it up. I would have think that okay, the phase shift is there. In the impulse train there is a phase shift. So in the frequency domain as well, the same phase shift would come. So in the output as well, the same phase shift would be coming. But if you think in terms of time domain, empty impulse train, in the time domain, no shift would be there. There you go. Right? Yeah. So this was the question. This was the flow. That first I need to multiply this particular signal with my impulse train. So when I multiply my signal with the impulse train, then this is something that I am getting. Constant phase I am getting. With the impulses, with the impulse train, I am getting some constant phases. So these constant phases would come out here. So now on the clones, I am getting all the clones, but clones are having an amplitude of fs. Along with that, there is a constant phase of e to the power minus j 2 pi fs 2. So that phase will be reflected in the output as well. But here there is nothing. Here the phase is 0. That means this is as it is coming out. What if there was some constant phase e to the power minus j theta? So that would have come out directly. So it would have been, output would have been f of t e to the power minus j theta. Doesn't mean the input will be shifted. Input can be shifted only if there is a shift in the impulse response ht. So you need to make the shift in ht, then only your input will be shifted. Otherwise it will not be shifted. Your message signal will not be shifted. If you need to shift your message signal, then your ht has to be shifted. Right? There was no phase, nothing. Here there was extra phase. So then we saw the condition that if what if we were using band pass filter. So if we were using band pass filter, so this is what we would have got, and now this is the shifted version of your f of t. So f of t multiply with cos, that means it should be shifted to fs. So it should be multiplied with cos. Along with that, there is a phase of e to the power minus j 2 pi fs 2 as well. So this would have been your output if this was the case. Let's see some easy question now. Most of the part is already done, like 98% part of sampling is already done. Now we will see just some questions. So xt is given, it is sampled at 2 samples per second. That means this is the value of fs. Fs is given as 2 samples per second. So what will be your Ts? Ts will be half second, right? You need to find the discrete signal x of n. So what did I tell you? In the basics of signal in the first chapter, I told this thing that t should be replaced with nts. T should be replaced with nts. Four plus 3 sine 3 pi by 5 into nts. So what we will be getting? 4 plus 3 sine 3 pi n divided by 10. So this would have been your x of n. So sine 3 pi n divided by 10. Okay, in place of t, what you are putting? nts. What is the value of ts? What is the value of fs? 2 samples per second. What is the value of ts? That is 1 by 2. So in place of t, you put nts, n into 1 by 2. So here what you are getting? 3 pi n divided by 10. So 4 plus 3 sine 3 pi n divided by 10. X of omega is given. Xt is sampled at the intervals of 2 pi by 5 seconds. You need to draw mode of x s of omega versus omega. Okay, so sampling time is given. Sampling time period is given, which is this. Everything is there in terms of omega. So let's understand it in terms of omega only. So what will be your omega s? That would be 2 pi by ts. So that would have been 5 radian per second. So it is being sampled at 5 radian per second. So what will happen? Clones will be made. In x s of omega, what will happen? Clones will be made. So clones will be made. So what is the scenario? This is the scenario. Two, 3, minus 3, minus 2 and 0. Now what will happen? This 0 will move to 5 radian, because what kind of clones will be made? 0 frequency, then center will be at omega s, then center will be at 2 omega s, then center will be at 3 omega s, similarly center at minus omega s, minus 2 omega s. So this 0 will move to omega s. What is the value of omega s? 5. So this 0 will move to 5. This is 0, 1, 2, 3, 4, 5. So this 0 will move to 5. This minus 3 will move to 0 is moving to 5. That means 0 plus 5. So minus 3 plus 5 will be 2. Minus 2 plus 5 will be 3. 0 plus 5 is 5. 2 plus 5 will be 7. And 3 plus 5 will be 8. So what kind of structure you will be getting? This kind of structure you will be getting. And similar thing will be happening this side as well. So what do you see? Again, this kind of clones will be there. So again and again, like now the center is moved from 0 to 5, then center will be moved from 0 to 10. So now what will happen? 0 is moved to 10, minus 3 will move to minus 3 plus 10, that means minus 3 will move to 7, minus 2 will move to 8. So between 7 to 8, this is something that is happening, right? Basically, aliasing is there. Aliasing is there. So now what you need to do? You need to add them up. They will be added, no? M of f plus M of f minus fs plus M of f plus fs. So all will be added. All these will be added, right? So let us say this point was a. So a plus 0 will be a only. This point was a. A plus 0 will be a only. And both of the graphs was a by 2. So a by 2 plus a by 2 will be a by 2 only. At this point, let us say it was 3a by 4. But this would have been a by 4. So 3a by 4 plus a by 4 would be a only. So basically between 2 to 3, it will become a straight line. And after that, it is already a straight line. Are you able to understand this point? This graph actually did not become much clear. I should have made it better. Both are already having the same height, no? Height will not change. They are having the same height. So actually I need to add them up. I just made it on one graph. In actual, I need to add it up. So I need to add them. So they are being added. So a plus 0 will be a plus 0 will be a by 2 plus a by 2 will be a. Here 3a by 4 plus a by 4 will be again a. Here 3a by 4 plus a by 4 will be a only. Here also the same thing is happening. So everywhere the amplitude will be constant. So what will be your mode of x s of omega? Mode of x s of omega. It will be just a constant line. Right? This will just be a constant line. That means it is becoming all pass. But this is not a filter, this is a signal. So you cannot call it all pass filter. What I am saying, you cannot call it all pass filter because this is not a filter, this is a signal. So all pass it is becoming, right? All are added, so it is becoming like a all pass. Xt is band limited to fm. It is sampled at thrice of its Nyquist rate for 2 seconds. If total 48 samples are required, then find the value of fm. So read it with good amount of patience. So xt is band limited to fm. Okay, maximum frequency band limited to fm. It is sampled at thrice of Nyquist rate. What is the Nyquist rate? 2 into maximum frequency 2 fm. It is sampled at thrice of Nyquist rate, 3 times of Nyquist rate. That means 3 into 2 fm. So your sampling frequency is 6 fm. Now what they are saying, it is sampled for 2 seconds. And if total 48 samples are required, that means in 2 seconds you require 48 samples. In 2 seconds you require 48 samples. That means what will be your sampling frequency? In 2 seconds you require 48 samples. So 48 by 2 samples per second. So your sampling frequency would be 24 samples per second. Right? Just 1 second. AC बंद करना पड़ेगा. Yeah. So what I was saying, your sampling frequency is 24 samples per second. How did I get to know this particular thing? What they are saying, it is being sampled for 2 seconds, and in 2 seconds you are getting 48 samples. That means in 1 second you would have got 24 samples. That means your sampling frequency would have been 24. So 24 is equals to 6 fm. So what is the value of fm from here? 4 hertz. There you go. Very simple thing. Okay. So these kind of easy question can also come, but mostly setup based question are coming. Like this was a setup based question, no? Complete setup is given. Here also the complete setup is given. So theory question can also come. Not theory, I would say. These kind of simple numerical can also come, which you will be able to answer very easily. And setup based question can also come. So you should have the aptitude of answering the setup based question as well. Right? Okay. And we have done enough practice, you will be certainly able to answer. Now this is not an important point, not an important topic, but still in 90s some question have been asked, so that's why we are seeing it, because in test series you can see some question. So till now we were seeing the sampling of sinusoid signal and baseband signal, like band limited to fm, then clones were being made, right? Or sinusoid, cosinusoid, then clones were being made. Clones were, some aliasing was there, aliasing was not there. All these things we have seen. Similarly, we can see for bandpass signal as well. This is known as bandpass signal, right? What is the process of sampling? Ditto same process is there. Exactly the same process is there. But for avoiding aliasing, the condition will be 2fh divided by k. fh should be greater than or equals to 2fh divided by k, where k is fh divided by fh minus fl, greatest integer. What is this? This is your greatest integer. This bracket is greatest integer. What is the meaning of greatest integer? Just a small integer would come. If I write down 3.5, what will be the value? 3. If I write down minus 2.5, What will be the value? Minus 3. Just small integer, just backward. Minus 2.5, minus 2 and minus 3. The value will be minus 3. And if I write down 3, what will be the value? 3 only. And why I am putting bracket here? Because the same integer would come. If integer is there, then there is no meaning of this bracket. And if integer is not there, that means just small integer you need to take. So this is the meaning. So here the sampling frequency is given by fh should be greater than or equals to 2fh by k to avoid aliasing. Okay, and what kind of filter you will use here? What kind of filter you will use? Band pass filter, right? You will use the band pass filter here. So to avoid the aliasing, for baseband signal, what was the condition? For baseband signals, the condition was fs should be greater than or equals to 2fm, right? But here what is the condition? 2fh divided by k, where k is greatest integer function of fh divided by fh minus fl. So let's write it down in a better and writing k is equals to fh upon fh minus fl, greatest integer function. Okay, and why is that so? We will prove it with respect to one example. So let's find out fs here. What will be your fs? Fs should be greater than or equals to 2fh divided by k. So fs should be greater than or equals to 2fh. What is the value of fh? 150 divided by k. What is the value of k? fh upon fh minus fl. So how you can remember? Maximum frequency upon the bandwidth. So maximum frequency is 150 upon the bandwidth will be 40. So what will be 15 by 4? 3 point something, 3.75. So what will be its value? 3 only. So here fs should be greater than or equals to 2 into 150, that would be 300 only, divided by 3. So fs should be greater than or equals to 100. That means fs minimum should be 100 only, 100 hertz. But if you just look at the maximum frequency and you say 2 into 150, 300. So that is also fine, but minimum frequency 100 hertz will also work. What I am saying, 100 hertz will also work. How it will work? Let's check it. So sampling process is same, right? Sampling process is same. What will happen? Clones will be made and those clones will be added. So what will happen? This 0 will move to fs. What is my fs? 100 hertz. So I am making the another clone. I am not making MSF. I am not making MSF. I am making another clone only. So what will be my clone? 0 have moved to 100 hertz. So this minus 50 will move to plus 50. Minus 50 will move to plus 50 and this minus 110 will move to plus 10. So from 50 to 10. And then this 110 will be moving to 210 because 110 plus 100. What is the scenario? This 0 has moved to 100. So center has moved to 100. So everything is moving plus 100. So 0 plus 100, minus 50 plus 100, minus 100 plus 100, 110 plus 100. What that would be? 110 plus 100. That would have been 110 plus 100 would have been 210. And 150 plus 100, that would have been 250. So this you would be getting. This is another clone only. This is another clone. Now this clone will be added with this clone. So let's make this clone here. Minus 152 minus 110. Minus 52 minus 110. Sorry. Minus 152 minus 110. So it is there between minus 152 minus 152 minus 110 minus 152 minus 110, and then it is non-zero between 110 to 150, 110 to 110 to 150. So only one clone I take. One is the original signal. This is the original signal. Okay, actually this is not looking good actually, because this is minus 110, this is 110. This is not looking that good. But this was the original signal and this was one of the clone. There is no aliasing. You take another clone, you take third clone, fourth clone, fifth clone, you take the clone in negative side as well, minus fs, minus 2fs, you will see that there is no aliasing at all. So yes, even at the lower frequency, you don't need to, what will be its Nyquist rate? If I ask you what will be its Nyquist rate? So Nyquist rate would have been 2 into maximum frequency component, that is 150. So it would have been 300 Hz. So here you are sampling below Nyquist rate. What you are doing? You are sampling below Nyquist rate, and still you are able to avoid the aliasing. Okay, to avoid aliasing, still you are able to avoid the aliasing even if you are sampling below the Nyquist rate. But at least this you would require. In this condition, no matter how many clones you take, there will never be aliasing. Although gate examination will not ask question on this particular concept. What they can ask, only one thing they can ask, but it can be asked only in PSU examination. In gate, there will not be any question on this particular concept. Even if it is asked, what you will do, fs should be greater than or equal to 2fh by k. K value you know, greatest integer function of fh upon fh minus fl. So from there you will get the value of k and you will get the value of fs as well. Okay, that's it. The only thing they will ask, what is the minimum sampling frequency? You will be able to tell. And why this is the minimum sampling frequency, why 300 is not the minimum one. Even at 100 Hz, we are able to do our job. There is no aliasing, there is no common area, or there is no overlapping area. So to avoid the aliasing, even 100 Hz is working for us. So that's it. This is the end of sampling and this is the end of our Fourier transform chapter. Next we need to study about Laplace transform. So I hope you enjoyed it. I hope you understood the depth of sampling here, okay, which was required, and I wanted to teach in this manner only because sampling is mostly taught on surface level, which is not that straightforward. It should be taught in this kind of that depth as well. So I hope you have understood everything, and now no matter whatever the question is coming in the examination, you will be able to solve it. Thank you very much.